your power, falling in love, falling hard.
Please enjoy.
Thank you, Mary. And again, yeah, thanks also to Mary and also organizing team for this conference, for everything. So hopefully you are awake. You spent a nice night. Yesterday evening was very nice. And thanks again, Oscar, to not only to offer the first drink, but also for the idea to meet, for the network. It was really nice. Unfortunately, not all of us could join, but several. It was really nice evening. So yesterday we touched already many topics, and yeah, I don't know if you still have any questions pending from yesterday that we should touch, but today we're going to have again a quite busy schedule, a bit less as yesterday. We actually have one presentation less, and the potential target is to close today by around 5 o'clock. So yeah, I think most of us has to maybe catch a flight as well. So we should be enough time on time. But today, yeah, we have many topics of really big challenges, let's say, like artificial intelligence. So we started yesterday some discussions. What can we do with this? Is it safe? Is it not safe? Open software, predictive maintenance. So many of the new topics coming up now that, yeah, I would not say we have already a solution, but yeah, it's good to discuss and share ideas. Okay, I think I will not really talk too much now, and I would like to already start with the first presenter. So the first presenter is Hans Blume, functional safety professional from FEV Itamax. And the topic again is artificial intelligence enhancing functional safety in automotive system. That's the heading. And the topic is automotive safety focusing on neural network training. Thank you. So you have okay, Mike, you have everything here.
Okay. Hello, good morning, everybody. Thank you for your attention. Automotive safety focused neural network training is the topic. It's a very complicated title. I tried to think of a better name, but I didn't come with it. But that should be fine for now. Before we get into this. Yeah, thank you. Okay. First, a little bit about my background, because it's the first time here and nobody knows me or my company. So I'm an electrical engineer. I studied here in Berlin, actually my bachelor thesis. Then I moved to Munich and did my master thesis. Then I worked as a hardware developer in the space domain, and I'm an engineer for functional safety at FEV Itamax GmbH for 4.5 years now. Mainly, I'm working as a safety manager, but a small part is also focusing on AI. I'm sorry, Carter, I had to include 2 marketing slides because to get to know FEV a little bit. FEV.io is I'd say the cool part about the FEV group. We are focusing about all the new stuff. So ADAS, software integration, software platforms, and functional safety. And functional safety and it is moving closer together. And that's why I'm also here for this topic today. Just to give you a glance about how big we are, we are 1,100 experts globally. As I said, this is the IO part of the FEV. The FEV entirely has about 7,400 employees. And that should be it for the boring stuff. Now let's get into the topic. So to show my motivation, I want to set a few boundaries. which we think are necessary to understand our motivation. So the first is we need AI at least to implement L4, L5 autonomous vehicles. This should be also true for L3, but maybe there are solutions in the future to allow L3. One key task is the classification of objects in the environment. Only if we know where the vehicle is and how the environment is, we can act accordingly and safely. Misclassifications may lead to severe accidents. So if we misclassify something wrong, the vehicle might act in a dangerous manner, and there might be fatalities. Accuracy of neural networks will never reach 100%. And last but not least, customers demand safe vehicles. So these are the foundation, which is why the motivation why we focused on neural networks in this case. So the common approach is, when we want to have safer neural networks, we need more data, we need better sensors, we need larger models, everything more and more and more. But the problem with this is that to get an accuracy of 80, 85, 90, 95%, this is okay. The effort is maybe not too much, but the better the accuracy should be, the more effort you have to put into generating the data and also updating the data. And of course, the costs increase exponentially. Yes, there are some efforts to collect data efficiently, but still the costs increase a lot. And we think, and not only the costs, also the demands on the hardware, on the vehicle itself, so the computing power itself and the energy consumption, it also increases. And so we thought, okay, is there a better way? Is there a more efficient way to make neural networks safe without pushing too much effort in? And I wouldn't be standing here if we didn't have an approach. Our approach is quite simple. We want to focus on safety. And this means that our statement is here, our claim is that not all misclassifications are similar safety critical. I want to prove that to you with a few examples. So taking now the traffic signs, if we have a stop sign and we misclassify it, for example, as a 120 km/h sign, then of course the vehicle would accelerate. Which is definitely safety relevant. On the other hand, if we take a 30 km/h sign and we misclassify it as a 20 km/h sign, then the vehicle would slowly decelerate and it's probably not safety critical. Now, moving this away from the traffic signs, if we take a child and we misclassify it as a banana, then the vehicle would not evade and of course it would collide and this would be safety critical. On the other hand, if we would have the same child and we misclassify it as an elderly person, the vehicle would still await. There would be no collision and this would not be a safety critical misclassification. So our idea is, okay, let's really focus on the safety critical misclassifications and hereby reduce the requirements we have towards the neural network. Okay. So that's what we did. We performed a hazard analysis and risk assessment for the example of the traffic signs. So we looked at, we took a few German traffic signs and we listed them here on the left-hand side. And those same traffic signs are on the y-axis and on the x-axis. And we asked ourselves, okay, if we misclassify, for example, the speed limit 80 as the speed limit 20, how safety critical would this be? And we assigned an ASIL level, so quite familiar for you. And what we can see here is that QM is white, ASIL A is yellow, B is orange, C is red, and the reds are very similar here on this projector. So I'm sorry for that. There are actually two different reds for C and D. But we can see that there are some traffic signs which are in general more safety critical, of course, but there are no traffic signs which are completely safety critical, and there are some which are only in very specific situations safety critical. So the next thing we did, we assigned safety weights. And the safety weights are nothing else than a definition how severe a misclassification is. So it's very similar to the ASIL. And for example, we assigned here for QM1, A4, B8, C16, and D32. These are example safety weights. I'm working with software developers. That's why we have this numbering, but it can be 10 potentions or any kind of so it's a definition. So and in this definition we said, okay, an ASIL C misclassifications is 4 times as bad as a ASIL A misclassification. So please don't challenge me on these numbers. These are example numbers. Okay. And these safety weights, they actually depend on the application. So here we have like the traffic signs, but you can apply this to any other domain and to any other misclassifications, and these safety weights may vary. But within this application, they remain the same. Okay. Then we, yeah, please.
Can we leave the question for
yeah. No difficult questions. Okay, then we chose a neural network. We did not choose a very special neural network. We used a standard one, which is an established architecture with around 123,000 trainable parameters, which is a very small neural network. The activation function is a rectifier linear unit, and the batch normalization is used after each convolutional layer. This is what it looks like. It has 8 layers, 5 convolutional networks. We used pruning to avoid overfitting, stride between 1 and 2, padding between 0 and 1, and the output size is 50 by 50. What does it mean? That means we're working with images of pixel size 50 by 50 pixels. Okay, that's it. And then we started the training, and we started, in total, we did 3 trainings. The first training is the baseline training, and the baseline training is, okay, we take these training weights, but we set them all to 1. So actually, we did not change anything. We say an ASIL D misclassification is equally bad as a QM misclassification. So no weighting inside, just to have a basis and to compare our results in the future. Okay, and what were the results? You can see here we had in total those misclassifications, QM5, A0, B1, C2, and D1. And yeah, I think it should be explained. So you had one here, and this is orange, this is the ASIL B, and yeah, you can see which misclassifications were here in this table. Okay, and then I have to introduce our concept of measuring the safety of a neural network, and this is called, or we call it, the safety score. Sorry, and the safety score is nothing else than taking the safety weights which were predefined, which are stable and constant for the entire setup here, and we multiply them by the amount of misclassifications. Then we get summons, and we add those up, and we get a safety score. So this safety score here is 100, but it's not a percentage. It's just by accident 100 here. Okay. Then the initial approach would be, okay, we have assigned here these safety weights. Why don't we just hand over those safety weights to our training, neural network training, and see what is the best result? And we did that. And looking at the result, it's here. So we have different misclassifications, something has changed, and we have 6QM, A2, B2, C0, but D also 2, which leads up to a safety score of 95. So it is a little bit better, but we were not happy, and we still had some budget, so that's why we wanted to continue. And we asked ourselves, okay, these safety weights, they were defined by humans because we think, I don't know, breaking a leg is X times more dangerous than having just some scratches. But is it really the best parameter for the neural network with many data sets, many data classes? Is it really the best parameters for it to train and get the base safety results? And this is the question we wanted to challenge. And as I said, we have dynamic risk analysis, we have dynamic model architectures. The safety critical analysis can change from case to case. So is it really that easy that we can just take the safety weights? And that's what we wanted to challenge, and want to automatically give the neural network the task, okay, please find out the best training weights in order to get the lowest safety score. So to get this best result, but feel free to use the training weights whichever you want. of course, within some boundaries. So how was this process? So at first we defined boundaries for the training weights, and in this case, between 1 and 128. This is example, it can be between 1 and 10, between 1 and 100 million. And then we chose an optimization algorithm. There are different optimization algorithms. We chose bias. We tried out different ones and gave the best results. And the optimization algorithm is basically you start with a set of training weights, and then you get a safety score, and then you have to change the training weights and have to improve your result. And the way of improving is actually the optimization algorithm. And then we trained 500 iterations with different training rates. So it could be that QM had a 27, A had a 4, B had a 111, and so on. We had 500 different sets of training weights. And each time we calculated the safety score. And we took actually the result with the best the training weights with the best safety score. For the software engineers among you, we trained 20 epochs, each of the 500 times. So we did in total 10,000 epochs, which was very demanding also for the hardware. We had an early stopping policy of patient 3, decaying learning rate of 0.01. We had an ADAM optimizer and our custom loss function from the safety analysis we did at the very beginning. And yeah, let's look at the results. These are the results. So we had the misclassification 32210, which lead to a safety score of 43, which is quite a good result. And looking at the training weights here, I think this was quite astonishing for us. So yes, ASLD has the highest training parameter, but what is up with B? Why is 1? So, but these are the best training weights among 500 different sets of training weights. So we didn't know this. This was the, how would you say, the magic of the AI. Yeah, putting this into perspective, at first we had the baseline, which is 100. Then we had the safety weights, which is the safety score 94, and the optimization here, it is slowly decaying to 43. You can see that at the very beginning, we already had better results than the safety weights. After 110 iterations, our safety score was already at 60, 46, and so on. And at some point, we just stopped because, yeah, the point was somehow proven. Okay. To sum up, we did, to look at the process again, we performed the risk analysis and we identified the criticality of each misclassification. Then we created this risk matrix and assigned the safety weights. Then we assigned the characteristics of the optimization. And then we performed the optimization to take the neural network with the best safety score. Now, what are the key takeaways for you? Our optimization improved the safety by 57% in brackets by the safety score. So this can definitely be challenged. The optimization has high demands for the computing power, as I said, because 10,000 epochs with a large data set, it cannot be done on a normal PC. We had to use Azure. The solution is flexibly adaptable to any AI classification task. So this example is based on the traffic signs, but you can apply it to people, road, and stuff like that. More optimization is definitely possible. And this does not solve, of course, every safety issue which we have with AI. And this is why I have one more thing for you, which is our guideline for AI and safety critical applications. This is free to download. And it's a set of 15 golden rules, which in our view has to be fulfilled in order to be able to use AI in safety critical applications. If you leave out one of these 15, then you're going to have a hard time implementing it in safety critical applications. They cover the entire life cycle, so from function specification, architecture, design, training, testing, and validation, implementation methods. And we wrote this actually about 1.5 years ago to reduce the aversion, because we were in contact with different customers and engineers, and they were really scared of using AI and like approaching this topic. And that's why we did research, we collected papers, journals, and stuff like that. We condensed it down to these 15 golden rules. And behind each of those golden rules, you also have an explanation and the sources why we came up with this explanation. Okay, that's it. Thank you.
Thank you. Interesting. So again, we had already one question here and one already.
Can I talk? Yeah. Hi, Pia Hammer from ZF. I don't know if I get it correctly, but do you combine all scenarios for the classification? So do you have all traffic signs combined to one integrity level then? Or is it scenario related?
It's scenario related, and we take the worst case scenario. So each of the classification here is actually quite a job to look, okay, where can this sign be actually be present in the world? What would the worst reaction of the worst behavior of the vehicle be, and then take the worst ASIL integrity.
So it would be then for all the same classification rating.
I didn't get that all the same. So
you just use then the worst case for all.
Yeah, for example, let's take the stop sign. The stop sign is in certain areas, and you would not expect a stop sign on a autobahn, for example, on a highway. So the worst case would not be that the vehicle approaches with 120 kilometers per hour, because it's always in the city, and the maximum speed in front of a stop sign is, I guess, 70 or 80 or probably 50 kilometers per hour. And this is you looked at these combinations. Okay, where's the signal going to be in the worst case? What vehicle behavior will be the worst case? And if we then misclassify it as all of the other traffic signs, what is then the worst case?
Thank you. I have another question. I'm allowed to.
Okay, we have time.
Wonderful. How do you work with corner cases? So from sort of point of view, I look to hazards which are might rated to QM only because they are pretty sheltered. So they would not be rated here, but they are still a hazard. How do you work with this?
Corner cases must be included here. It's not the corner cases are usually the ones where it is difficult for the AI to detect the signal itself. But it's the job of the functional safety experts to really think about, okay, is this the worst case scenario, or do we actually have a stop sign on the highway, for example?
Yeah.
But it's challenging. That's true.
Yeah, thank you. So my ASIL question has already been answered, but I'm still surprised from the weights you computed. So is ASIL B more important than ASIL C? So
yes, we are also surprised, but our explanation is, I will get quickly to this point. Yeah, our explanation is that this is depending on how many misclassifications are ASIL A rated, and if you have many or less, this has influence on the best parameters. So if we probably have in the misclassification matrix exactly the same amount of ASIL A, ASIL B, ASIL C, and we have them equally distributed around all the data sets, then probably we would get training weights which are similar to the safety weights. But we do not have this homogeneous behavior. We have very different amount of ASIL A, ASIL B, ASIL D, and ASIL D misclassifications or ratings. And this, we think this is the reason why the neural network did not come up with the safety weights as the training weights, because there might in this 500 different sets, there were also parameters which are very close to those ones. But it kept on trying, and it improved the safety score. But this is the magic.
And regarding compliance, you have your own 15 rules. So why didn't you look to any safety standard?
this guideline was written 2.5 years ago. It was published around 1.5 years ago. And we looked also at standards, but this is a little bit, sometimes a little bit more concrete and has a wider variety of sources.
Nice presentations. It's a good perspective. I'd not say that there are not standards being followed. I see standards is a way, but you also try to understand the SPI, like safety performance indicator, like yesterday, Phil was mentioning about that, and this is safety weight and training weight. You try to access to that. So you are pretty much following something.
Yeah, I mean, it's not rocket science. It's
and absolutely,
Yeah.
the standards should not be the solution, as you always say that.
Yeah.
But my question is, how much training data you consider? Can you give us some rough values for just this case?
We used the German traffic sign data set. We used these 42 classes. They have between 300 and 1,500 images. Yeah, this runs so maybe 10,000 images.
10,000 images.
Yeah,
you play
yeah,
across.
yeah.
And this is only case you apply, or do you also think for the road sign, road markings and any other?
No, this is the only thing we started for now. But the focusing on the traffic sign, this is not the key message here. The key message here is to having a safety score and having flexible training weights on each application. So this is the key message. The German traffic sign data set is also actually too small to use.
That's right.
And of course, if you want to have more classes, you need to have a better neural network. So 123,000 parameters will not be sufficient for this.
Any plan to extend further in future for other data?
We planned, but due to the situation, it is challenging to continue.
Just out of curiosity, have you tried adding false negatives as well? Mateusz Czerwienko at RSB, yeah.
We have looked at the accuracy at the moment, so a false negative was not a KPI which we followed here.
Okay. Wondering what would be the safety score then?
Thank you. My name is Juan Pimentel from Omnex. Very nice presentation. The only question I have, or maybe a comment, is that you used misclassifications as a way to measure or see how well your system is. However, the most used accepted ways to do comparisons is using things like safety, recall, area under the curve, or intersection over union. It would be great if you could use those, because those are more accepted ways in figuring out, the performance of your neural network. That's my only comment. Or have you done that, or do you plan to
Not
do
yet,
that?
but it is actually on the list to extend those KPIs. Yeah. Thank you.
Thank you.
Okay, more questions, maybe also online. Still everyone is shy. Okay.
Was it too quick?
No, it was okay. I mean, we are just a couple of minutes ahead of schedule, but actually we started also 2 minutes before, so it's okay. No, okay. If no more questions, I think we can already proceed. No, I think it's okay. Many thanks. It was very interesting. Okay, so the next presentation is Juan Pintel. We already know him. Principal consultant at Omnex. And again, the topic is AI and its challenges in implementing AI in automotive functional safety.
Thank you for the introduction. Again, my name is Juan Pimentel, and I am a consultant at Omnex, headquartered in Ann Arbor, Michigan. Just a few words about myself. I've been working in the functional safety area for a long, long time, starting off with topics in aerospace, actually, with many colleagues in France and Austria mostly. And then I did functional safety for process control systems, working in the Middle East, mostly in Dubai, applying functional safety for process control and chemical industries. And in the last 10 years, I've been working on automotive. Even though I was a professor at Kettering University, which used to be General Motors Institute, which is automotive. So I've been working with automotive all my career, basically on and off, on and off. All right. So the title of my presentation is Challenges in Implementing AI in Automotive Functional Safety. I'm very pleased that Hans preceded me because he already talked about some of the ideas or topics that we're talking about here. My presentation is going to be at a much higher level. Hans talked about a very specific technique using neural networks in general, but I will be talking about at a higher level and also talking about other issues in addition to neural networks, which is, I'm talking about basically the latest areas like generative AI and things like that. Large language models, which is the latest buzzwords or topics that people are not only talking about, but actually using it. Also, I'd like to mention that I did some work with neural networks a long time ago. Lately, I'm not doing so much work. I'm following the research, but I spent 3 years in Spain in a spree project, it's called. And all we did was basically use neural networks for mobile robotics. So we learned a lot during that project. We published about 15, 18 papers, something like that. In fact, I will mention one paper that I did way back. The only reason that I'm mentioning that is that some of the techniques that has been around with neural networking for a long time can still be used today. Okay? Many people think that these ideas of LLMs or AI is brand new. Some of them are new, that is true, but some of the techniques go back for a long, long time. Okay, so it's a good idea sometimes to take a look at what has been done in the 80s, 90s, or early 2000s. All right, so with that, basically, I just talked about the goals of my presentation, a fair introduction to the topic, some challenges, the way I see it. Hans mentioned about 15 guidelines. Some of that are probably here. I haven't looked at those. Again, this is from a very high level perspective. And also, I like to concentrate on some methodologies to achieve safety. Again, I've been working on safety all my life, safety critical systems. I live that idea, almost day to day. And then talk about the emerging techniques. I will touch a little bit about the current AI developments, and then obviously the summary. Okay. So the goals of this presentation are to discuss these topics. Safety, to discuss safety in the context of machine learning, but really I go beyond machine learning, even talking about LLMs and the latest issues or techniques in AI. To review some methodologies that's being used today for safety in automotive. Okay, because AI is so broad, so I'll just concentrate on safety in automotive, obviously. And then to discuss the interplays between these safety-related and non-safety related subsystems. In my opinion, that's the way to apply AI. In other words, I don't believe that you're going to have a humongous AI system that will solve every problem of our safety, especially. But rather, I think the way I see it, the solution is going to be into subsystems, which come from systems engineering. Some aspects of the subsystems are going to be AI related, and some aspects are going to be non-AI related. All right, so I think I mentioned some of this already. Basically, all of this is fairly common knowledge for specialists like us, I guess. But the main thing here is that AI is becoming very important, obviously. And some of us, some groups are interested in seeing how AI can be used for safety, for functional safety particularly. And so there are also many standards, especially ISO and IEC, they're collaborating and they're generating a bunch of standards. Some of them are fairly straightforward and guidelines, more so than standards, but there are more standards coming up in the future. I think the speakers after me will be talking about 8800, I believe, and some of the standards are coming up. So I will not focus too much on the standards portion. Uh, so basically, we have what is called current and clear challenges of using AI. Now, what does that mean? What I mean by that is that you have to be extremely careful the way you use AI. Um, it's challenging. Just don't believe that some people are using for some applications, you could use it for safety and you'll be all right. And I disagree with that. So you have to be extremely careful about that. In fact, some of these standards I'm talking about, they actually warn you about that. They warn you about the potential dangers of using AI in automotive safety. And these are some of them. In fact, the one that I noted in green here are, in my opinion, the more detailed ones, like 5469, 42001, and some of them are forthcoming, like 8800, people talked about already. It's not available yet. I think it will be published in the next few months. All right, so this one in particular is about managing aspects, because the management of anything is very important. And as you know, ISO standards are based on this particular standard, which is 3100 from ISO, which is the mother of all standards in terms of risk assessment. It's a very good standard. Yes, it's a good standards for people in working in functional safety to take a look at, only from the management aspects. As you could see, it's a risk assessment model, basically. All right, here, this is important. So these are some of this is not an exhaustive list. This is mostly what I see the most demanding, the most crucial issues if you want to use AI for automotive safety. Number one, the AI is non-deterministic. That's a big problem. Okay. Another one is inscrutable, means that you cannot open the box and take a look what's inside. It's like a black box. You have an input and output, and that's basically it. People are working on trying to open the box and see what's inside, but in my opinion, we have not, as an industry, made much progress about that. Still a black box. And also it's unexplainable. I mean, it works, but figuring out exactly how it works is problematic. And if you're a systems engineer person, you need to get inside and figure out how it works. Also, it has a data problem in the sense that the data has to be just right. You have bias aspects in data and other aspects. So if the data is not right, the system will not work correctly. Also, you have a modeling problem. The previous speaker talked about one specific neural network, but there are many architectures. And that's the advances lately in this area, that they're just working on various types of architectures. So that's a modeling problem. Okay. Another thing is that it is extremely difficult to work with requirements. Okay. In fact, this standard I talked about before, 5469, it talks about that. Especially if you work in systems engineering, you start off with requirements. You do testing, verification, validation based on requirements. And it's very difficult to come up with requirements with AI systems. So that's a big problem. And then a lot of people talked about edge cases already. On the right side, you have just some examples of what they're talking about. I'm really talking about all of AI, okay? Starting with ANNs, artificial neural networking, machine learning, all the way down to LLMs and transformer architectures and generative AI. So I'm talking about the whole thing, because some of these are being used for other areas, and some people, especially young people without much experience, they're trying to use transformers a lot, attention networks, for instance, for automotive, okay? And in my opinion, some of the things that they're trying to do, it's working all right, but you have to be careful with other things. It just doesn't work, okay? All right, so these are some challenges to overcome. One of them is composability. This is a term that was coined by Herman Kopetz. Herman Kopetz is the founder of a company in Austria called TT Tech. They're very good in embedded systems, real-time systems, and dependability, safety, and stuff like that. But he's the one that wrote a book, and from his book, this concept of composability is very important. That, in my opinion, I wish some people would take a look at it. Take a look at the definition, okay? It's an architecture. It's said to be composable with respect to a specific property in the system. Will not invalidate this property once the property has been established at the system level. So it has to do with systems engineering. It means that when you break up the whole system into subsystems, if you are able to prove a property at the subsystem level, that should not invalidate a property at the higher level, which is beautiful. It's extremely important. This is very difficult to prove with AI, with neural networks, extremely difficult. Basically, I haven't seen any proof, okay? Either theoretically or practically. Another challenge is modularity. And I take, for instance, there are basically two ways to do AI in automotive, major ways, I would say. One is championed by Tesla, you probably know that, which is end-to-end. What they're trying to do is to build a huge AI system from beginning to end. The input is the sensory data from all the sensors, and the output are basically the controls for the car, longitudinal and lateral controls. And then it's just magic from the input to the output. It's a black box, and they're trying to solve the problem that way, okay? And their only argument is that, yeah, we have thousands of cars and millions of cars, actually, zillions and zillions of data. You just put a huge, spend a huge amount of money and time training this huge neural network, and hopefully the problem will be solved. And he's been promising this for at least 8 years. So in my opinion, actually my opinion about that is that I don't believe it will work. I like the approach taken by Wayman and other ones that uses a systems engineering point of view. They break down the whole system, the car, into many subsystems, and they apply AI into the subsystems and also non-AI subsystems, and then they combine them. I believe that's the way to go. And in fact, my talk is structured like that. So this is why I talk about modularity. So modularity means that you're able actually to break that down, the subsystem into smaller systems. You do that into a modular fashion, okay? And then people, especially computer science people, they do not pay attention too much to real time. Real time is extremely important. It is not enough to do the job, okay, functionally. You have to do it with timing constraints. Otherwise, it does not work. Timing is so critical. And in fact, Herman Kopetz, in his book, he also mentioned that real time is crucial. That's one of the cornerstones for functional safety, is to pay attention to the real time requirements. Okay. And then the topic about no requirements, I mentioned that earlier in the sense that AI, it's very difficult to include requirements with AI. And then, of course, you have the issue of testing, validation, and verification. That's also challenging to do with AI systems, which is related to the last one, which is how do you apply systems engineering methodologies to AI-based systems, which is extremely difficult to do. In terms of the V model, I put this diagram only because the V model is a good model that it's being used in functional safety standards, but not just standards, but even practitioners. But what we're talking about here is what are the challenges with respect to this particular V model? And basically, whenever you introduce AI, this is what happens. You break traceability. You break a lot of interfaces, either from bottom up or left to right, which is very important. You break that down, okay? You're not able to, only because it's a black box. That's the main problem that I see. So this is the problem with Tesla. And in my opinion, this is why they're not making too much progress, because it's like you go one step forward, two steps backwards, or vice versa, going back and forth. So you solve some problems and then you end up with other problems. And that's the issue right here. In my opinion, the solution to this problem, but in the context of this big model, is to do it like this. This is what Waymo is doing. So whenever you divide the whole system into subsystems and then apply validation, verification, modularity, testability that I was talking about earlier, this way, then you have better control because the system still, I mean, these stars that I introduced here is the fact that we are using AI subsystems. And AI subsystems, as I pointed out earlier, it produces a problem in that you cannot work with requirements. It's a disruption, okay? It does work sometimes, so you have to be careful the way it works. You have to modulate their outputs, if you will. But if you do it like this, I think we have a good way to still using AI in the context of the V model. And still you can use systems engineering, okay? So this is my proposal to use AI in the context of the V model for the entire life cycle of the vehicle. Well, the V model doesn't cover, the production, but only the design and testing and stuff like that. But in this context, I think it will work. Next, I'll be talking about some measures that can be used to overcome the issues that I'm talking about. This one comes from this standard 5469, which is not really standard, it's a technical specification, by the way. But here, this diagram, it's very compressed. There are three ideas here that you can use, three architectures, if you will. In fact, it's right there, it says architecture C, B, and A. But one of the main ideas is to do, for instance, a supervisory component that supervises the operation of other components, okay? And the reason that you do supervision is that you do not trust the neural network, okay? You cannot trust the neural network, so you have to monitor the way it works, that's one of the ideas. Another idea here is the backup decision, which comes from the fault-tolerant systems, which is a replicated components. In other words, you have one component, you implement it one way, and you have a different component, totally independent. Independence was talked about yesterday. It's very important to have independence. So you have an independent component that works in parallel, if you will, and that's called the backup in this case. And then you have a switching function on the right. So this diagram is very loaded in this diagram, in this document. I wish they had broken it down and explained more. I've done this a little bit here. This is one idea about the border, okay? And in the border, what you do is that you have these components that pretty much do the same thing, and then you do a boarding. This border was designed by the aerospace people and works very well with the space shuttle and aircraft. If you fly a Boeing or other planes, that's what they do, okay? They have this solution, okay? And then the idea of monitoring that I talked about before, okay? And also the last one is the backup, So these are, in fact, these techniques are very old. I come from even going back to the old way I mentioned aerospace. The aerospace people design and the people that did the space shuttle, they thought about these solutions a long time ago. This is nothing new, okay? The reason that has not been used in automotive, by the way, sorry, is that it's costly, okay? Because it's a cost decision. So, but now because hardware and software is going down in price, they're looking at these solutions, okay? So these solutions are very old, but costly. All right, systems engineering. It's old stuff, and this is why I'm breaking up a diagram that I did in a paper that was published in 1994, actually, okay? So this is the work I did in Spain. And here what you have is one of the latest works we did, where we collected a mobile robot, by the way. Is very similar to a car. It's extremely similar, okay? So you have the neural network in here. We do the fusion of several neural networks. We combine all of that. We tried a lot of techniques, including reinforcement learning to learn primitive behaviors and how to have this mobile robot to work in an environment. So we did a lot of stuff in terms of combining several modules. Some modules were strictly AI, neural network based. Some modules were not strictly AI. We use even techniques like fuzzy systems and other techniques. So the point is that the lesson learned here is it does work, because we proved that it does work a long time ago. And I believe, in my opinion, this is something that needs to be done today with the current technology. That's the paper. It was published in a chapter in a book. So we did a supervision. We did a combination of several modules, as I mentioned before, using systems engineering techniques. Because I'm a systems engineer by training, by the way, and it worked very well. This is another example that we did. Combining. Okay. In terms of the current developments, this is what's happening today. And I like the work that Waymo is doing. Waymo is doing similar things, except that they're using, of course, the latest techniques like attention networks. You know, that's one of the latest things, transformer architectures, LLMs for all of that. This is one of the latest papers, and in fact, I think it's 2024, 2023 that they're doing. This is another one. But I'm looking at what Waymo is doing in terms of the process is the same process that I used a long time ago, basically. What they're doing is the new methods, new techniques, and obviously for their cars, and I believe it's working. So I believe this is the way to do it. Okay, this is still another paper from them. Again, similar ideas as the one that I'm proposing, that I'm that myself I have a lot of experience with that. Moving forward, there are some things here that, in my opinion, needs to be done, particularly addressing this challenge that I talked about, composability, modularity in real time. That's big, in my opinion, okay? And that's very difficult to solve in the AI area. Yeah, with that, I guess there is a lot of interest in AI. We just need to be very careful in applying it. Even the latest stuff, you're talking about large language models, attention networks, transformer architectures, generative AI. Some of that is actually amazing. It works. We don't know how it works sometimes, you know, but it works for some things. But my point is that you have to be extremely careful if you want to apply any of this for automotive, particularly functional safety. You know, that's the main point. Another main point that to finish up is that systems engineering is a good way to do it, modular fashion. And some ideas are quite old. I proved some of that. I showed some of that Waymo is still using it because systems engineering is systems engineering. Yeah. With that, I close my presentation and I'll be happy to answer some questions. Thank you.
Thank you, Juan. Okay, already starting questions here.
Yeah, thank you very much for the presentation, Alexander Matrosch from Electrobit. What we see are basically, well, I personally see two different applications for AI at the moment. So one is in vehicle. I think that's what you focused mostly, if I got it right, but also during development, like using large language models for safety analysis support and things like that. So what is your view on that? How much can we also trust AI during the development phase? And what are the best techniques, models to use for which use case?
Yeah, that's a great question. Myself, I have worked in both areas. By the way, I have a lot of experience. In terms of applying AI, I concentrated on the design that I mentioned here, not on the development portion. But having said that, I mean, I'm playing around with AI with lots of applications, and it's still being used like for FMEAs. And myself, I'm interested in using AI, for instance, for requirements and deriving requirements. It can be used for a lot of stuff. By the way you use AI for development, the way you use AI for design, totally different. Okay. Everything I've talked about here, by the way, is development. It's not I mean, design, not development. Okay, development's a different story. In fact, I like to give another similar presentation or paper about this on what you're talking about, but I haven't done it yet. I'm playing with it, and it's amazing what you can do. It's totally amazing. You know, these things do work. LLM, I'm talking about attention networks, transformer architectures. They do work. We just don't understand how it works sometimes, but they do a lot of stuff. Very good, very good. Not perfectly, by the way, not perfectly. Okay.
Yeah, that's also what we said yesterday. I think it's okay to use AI to give you some hints to help you, but what is not okay is to trust completely AI. That it still may work, may not work. It may even give you some answers that you believe it are actually correct because they make sense, but actually they're not. So we have to always be careful.
Yeah, I had also very interesting results with.
Well, just to add one thing, I mean,
Yeah.
yesterday we heard Phil Koopman. I know Phil Koopman very well. You know, we worked for a long time. He's a great guy. But one of the things that I have not mentioned explicitly here about AI, it has hallucinations, right? You know that. But he prefers to call it bullshit, okay, which is a very stronger term. You know, and really, it's bullshit sometimes. So you have to be extremely careful, you know.
Yeah. Okay, one question here.
Yeah, Oscar Sotos, great talk, very good. From Validas. So what is an attention network? First time I hear this term. So I know LLMs, transformer, whatever, but what is an attention network? Can you say some sentences?
It's if you're a mathematician, attention is nothing more than cross correlation. Are you familiar with that term? Yeah, you cross correlate one sample with prior samples. So the same thing, you try to correlate. It's like you try to correlate what you're saying today, what you said 2 minutes before. It came from the language people, large language model. Okay, they're probably not very mathematical. They try to correlate, for instance, what you're saying right now with the words that you used to say before, especially for translation, as you know, especially in the German language. You cannot translate word by word. You have to get few words and then correlate to what you said earlier. That's what they're talking about attention. It's really cross correlation. Okay.
Mateusz Czerwienko. So I've got a question from the perspective of the perception software of one of the sensors. So if we are doing the decomposition, we have a few ASIL-B, let's say, sensors. And how far should we go with this supervisory component for those perception softwares, let's say? So, and how far should we go with the ASIL-B safety case and in terms of AI, right?
Are you talking about this idea that I mentioned, composability?
More or
Or-
less. I mean, there was a slide from 4569 regarding this different architectures.
Yeah, yeah.
And do you mean this on the level of the whole system, or
Oh,
do you
oh,
mean
oh, I
this
see, I see.
like, you know,
Yeah.
because if we are doing the perception software, like, should we really go with the safety concept, or should we focus on the testing? And
No,
Yeah.
it's that diagram is very broad. The best answer I can give you is in the context of ISO 26262. You could apply it at the item level, like at the item definition, at the subsystem level. It's at the subsystem level. But that diagram is it's really great because we apply at a small subsystem or a larger subsystem or even larger. As long as you have composability, this is why this concept of composability, in my opinion, people don't know about it. So I recommend they read the book from Kopets. It's a great book, okay? And that's what you need to do to make it composable. Because what that means is that you could apply at any level, and as long as it's composable, it works.
Okay, but let's say I've got a requirement from the customer, which is OEM, recognize an object or pedestrian ASIL-B with certain KPIs. So, like, should I go in detail in this, let's say, different architectures, looking from the perspective of this one of the sensors, software architecture, or should it come from the customer because he knows what is done on the, let's say, fusion level? And
It's both. I mean, the customer usually is high level, and then you have to go lower level at the system level. Yeah.
Yeah, I think also here we're a bit mixing ISO 26262 with SOTIF, so there are many different.
Yeah. I mean, yeah. So
Yes.
it's a struggle. Yeah, thank you.
Yes. Okay, the last question.
Roberto Paccabelli from Red Data. Thanks a lot for the great presentation. My question is more related to the standards. So my curiosity is if you have analyzed the ISOPAS 8800 and basically if you have any comments, because there are some proposals, if I remember correctly, about a possible V model plus the influence of the AI life cycle. I don't know if you have already checked this standard, and then if you have any comment about it.
Anakin, could you repeat his question? Do you understand him?
Was the question about the standard ISO 8800?
Yeah.
If you are aware of this, if you try to apply or not?
Yeah. Yes, I'm familiar with that standard. I haven't looked at it in great detail because it's not publicly available yet. But 8800 will be a follow-up to this one that I mentioned, 5469. It will be more towards automotive. That's the main difference. This one, 5469, it's more functional safety. And as I mentioned, I think we had a talk last night, functional safety is very broad. So it covers process control applications, chemical industries and stuff like that. But 8800 will be strictly automotive. So that's a major difference between that and this one.
Yeah, actually, I mean, it's not only a porting, but it's now including much more information as well. That's why also now in the ICT are now preparing the next standard to some mirroring.
And also to complement what I just said, it's a management standard. So think of it as, in my opinion, will be a very good standard. Think of it as 26262, but for AI for automotive. It's something like that. Okay.
Okay, maybe the last comment that we have to move on.
Well, I could add something to this. We had extensive discussions about this with Simon Burton, who is also working on this PAS 8800. And basically, it's an extension of the SOTIF standard, 21448, and uses these SOTIF mechanisms that are defined in 21448 and applies it to AI and what you need to do to create the right models, the right training data, and the right verification on the system. So that's
yes, I agree. I agree. Yeah.
Yeah, but again, the standard is a kind of chicken egg. The standard will not really tell you what you have to do. It will try to capture the current understanding of the working group. And yeah, it's one step. Okay, many thanks to Juan.
Thank you very much.
Okay, we are now moving to the next presentation, and it's about AI and how to handle it safely, so similar topic. And is presented by Avinash Visagan Varadarajan, hopefully I pronounced correctly, functional safety specialist at Brace Automotive. Thank you.
Maybe have to use this one. Okay, perfect. Yes. Now, good morning, everyone. Somebody had in the presentation yesterday standing on the shoulder of giants. I don't know who it was, but it's a really nice statement. And I would really like to stand on the shoulders of two giants that came before me because they had pretty much all my presentation presented them. But my topic will be AI and how to handle it safely. Luckily, I have some content which is not overlapping with the both of them, so I can present something new to you guys. The first one was going to be the term AI. Juan already mentioned the different kinds of AI that you can already implement in automotive systems. But the most important used are machine learning, which you can already see in the market. Yeah? But we will see some examples on what are the current applications of this. So I would like to begin with a very short story, which is, I have a small statement at the end to signify it. So let's say AI in automotive is not only about design. There was already a nice question saying, what about, let's say, the other aspects of AI? You can use this in R&D, you can use this in testing, you can use this in manufacturing, predictive maintenance. But we all know that it can be a key, let's say, a performance indicator for ADAS, electrification, smart assistance. But it's an expanding market space. To really begin with, let's say you have person X that wakes up at 8:30 a.m. I'm going to present an utopia situation. The car already knows what his next meeting is, so it already plans a really good pathway for him, avoiding all the traffic and maybe, let's say, so you have the use of AI in there. So it knows a lot about traffic networks. And then maybe there is an accident on the way. So infrastructure systems already provide the right information to the AI somewhere in the metaverse, and the car already plans another route. It also does V2V. So some car is going maybe 30 kilometers in a 60-kilometer zone. Why is it doing that? V2V communication. And then it warns the other cars saying that, okay, this path is slow, please go in another path, which is also AI. And then we move on to more the design inside the vehicle. We have several items. For example, driver monitoring systems, which are really looking at the user and seeing is he attentive. One of the use cases I will present in a while. And these are a little bit more yet to be explored on how AI can be really used in lateral control, or let's say longitudinal control, or maybe even vertical control of the vehicle. So those applications, maybe we have some solutions in the future, but for now, the most requests that we see are outside of the vehicle, more or less, and a little bit inside the vehicle. One of the questions that you had in R&D, how can AI be used? We have short marketing. We are now trying to develop some technologies based on large language models. Ricardo mentioned yesterday that the whole standards is kind of a jungle, and we are trying to create a solution where a system can look at all the different standards for your particular product and synthesize a list of requirements that you have to follow. Because imagine an engineer reading tens of different standards. It's a big job. Yeah. So it can even be used in test specifications. For example, based on your requirements or based on your design, what are the different test specifications, which you can quite easily automate and send to your testing systems. But it's an expanding market space. We are still discovering what can be done, what cannot be done, what is quite good, what improves efficiency, and so on. Towards the next slide, I would like to take a really short example to explain a little bit the 5469. We tried our hands with the technical report, I should say. It's not really a standard, but a technical report. So we did take an example to see how the 5469 can be used in commercial applications. Now, legacy driver monitoring systems, these are based on the behavior of the driver. So for example, is he really using the steering according to the control? Is he following the lane approximately or more or less correct? And what we can really see in the systems are it provides a lot of unintended warnings. I have personal experience from this. I don't wish to name the OEMs which I've driven before, but it always gives me a warning saying, okay, please hold the steering wheel while I'm perfectly all right holding the steering wheel. And it says, please take a break while it's only been 5 minutes since I started driving the car. So there are a lot of false positives which lead to reduced trust in these systems. And we found out driver monitoring systems, AI technology can be really used to look at the driver and then give more accurate warnings. So we are going to use in-cabin sensors, for example, DMS cameras. We have a lot of solutions integrating cameras in the rear view mirrors or maybe other parts of the cabin. And then that really looks at the driver and say, okay, maybe now you are attentive, not attentive, and so on. What it does, it only provides warnings, or let's say it avoids false positives or sometimes also false negatives, which increases driver alertness. Maybe there was one statistic in a paper which I fully do not remember, that incorrect warnings actually make the driver more inattentive because they keep warning him, and in the end, the driver really starts to ignore these warnings. Yeah? So AI can be used to really improve the efficiency of these systems. So this is an application where we try to use a driver monitoring system to really look at the gaze of the user. So in some cases where the eyes are maybe fully open, where sometimes the eyes are partially open, and try to define the driver warning based on this gaze detection. As Juan maybe presented before, we have a lot of different architectures which can solve this problem, but more on that a bit later. But what we really tried to do was to really look at the risks of the machine learning algorithm failure. I think we all know about spaghetti code. If you really look at this machine learning things, it's a whole spaghetti factory. So nobody really knows what's going on inside these models. If you try to open them up, it's near impossible to make sense of what's going on inside just because they are so complex. But what we can still do is try to monitor the output of these systems and then at least try to define what's going on. This is very different from the V model that we are so used to, because the first step is to really define what the system will do. While as here, we have to start using the system, define a big set of outputs, and then define what the system should do. Yeah. So in a sense, you are working with a system that you really don't know what it's going to do. So we try to understand the risks of AI usage and try to define a good system based on the data that we have. Now, a lot of different people, I'm really happy that a lot of people are aware of the state-of-the-art standard. The ISO 4804, which is going to be phased out in a few months, hopefully, and then is going to be replaced by the 5083. Unfortunately, or fortunately, the 5083 is only focusing on automated driving and not really on the safety of AI. So it's not really possible for us to use the 5083 to understand the risks of the machine learning algorithm itself. Can be used, may be used, but it doesn't really cover that in the scope of the standard. So instead, we chose to use the 5469, which is the current state of art in functional, or let's say functional safety for AI systems. But there are a few caveats in this. It's very sector independent, meaning you can use this more for aviation to even coffee machines maybe, and even complex things like cars. So it's not very dependent on the automotive, and unfortunately it's also a technical report, which means that it's based on best practices and knowledges from expert, but not really, it doesn't give you any normative requirements for this. So if you really look at the 5469, it defines a lot of things which we can use, and we try to take 3 best practices which people can already start using. And maybe this is from the report that FEV already produced. I have not yet looked at this, but maybe you guys already covered this in your report. One of the nice things is the usage level. What do you use the AI for? Is your AI system used to make critical decisions which affect the safety? Or you have another usage level where you use AI to make systems, for example, compilers, or can be anything. And if it makes a really critical mistake there, in the end, the safety of the vehicle is also compromised. Usage level C may impact the safety of the system, and usage level D is, AI does not really impact the safety of the system, or it's not part of the safety function. So this, we believe, has very good potential to be included in the hazard and risk assessment. Although we have some concerns on integrating the 5483 or maybe the upcoming 8800 with the HARA process, because it really does not cover the risks of AI so well. It's more focused on making an item level discussion, but the AI, as we saw a few slides before, is more than that. Yeah. But I think somebody already gave the answer for this. I think it's Professor Burton that's looking at this, and it's more regarding the SOTIF part of the safety, which will integrate very well with the AI systems. That is our conclusion so far. Unfortunately, I have to excuse myself for blocking all the solutions because this is a commercial product and we don't yet want to release this information quite publicly. And we tried to take the architecture which was proposed in the 5469, what Juan basically showed, to really start using these architectures to define a solution which can be quite good. Unfortunately, we found out the biggest problem was basically the switch, where probably AI is not going to be used, but it's going to be really dependent on legacy systems, which kind of defeats the purpose, because in the end, you always have a fallback that says whatever work the AI does, the switch is going to be a very old legacy system or an old architecture, which will in the end say, okay, let's go back to the backup or maybe the limits proposed by the supervisory system. So in the 8800, maybe if some of you are involved with the research or making of the standard, we would really request you guys to look at the switch or maybe the biggest decision maker and try to include this to see how we can use AI in the switches. This is, quite essentially a lot of work being done. I would not like to go a lot on this because Juan already told a lot about this, but one of the things that we understood was the more complex your safety mechanisms or that you try to make your AI system safer, you start losing utility. And then in the end, you really see that you are going to fall back on the switch, which is going to be the backup or the supervisory limit, which in the end defeats the whole purpose of having AI because you want systems to be more smarter, but doesn't make sense to fall back every time to a solution that you already know, which is going to lead to false positives, maybe performance issues, can be anything. I cannot provide some numbers yet, but the more complex the solution goes, the more processing time it takes, and maybe there are even impact on the FTTI of the system. Yeah. So another best practice that we could use is the 3-stage acceptance criteria. So for every step of the V model, which is basically the modularity, focus on data acquisition, knowledge induction, and then try to see if you can make a decision based on AI. A lot of people start already focusing on the decision, but we have not quite good covered already data acquisition and knowledge induction. And one of the things is being an edge case. Once you find an edge case, it fails to be edge anymore. Then you will only start finding more edge cases. And it's only a matter of time until most of the edge cases are found, which is kind of the opposite of a V model because you are trying to look for failures or let's say the most edge scenarios in your system. It's very important to define acceptance criteria for these systems, so you already have at least a benchmark to see what your models can be. This is the same old with the V model, but I would really like to focus on the yellow part here, which is going to be the data consideration. So a lot of people already try to define specifications for the AI model, which is kind of constricting, in our opinion, to start with developing this, but start fast. And then the most important, we think, is the output data that you get from your models that you can already use to validate your specifications or maybe even create new specifications. So maybe also another recommendation for if somebody is present here from the committee, maybe Ricardo, is to really give adequate importance on how we can formalize the gathering of data and using it to revise the specification. In the end, also one of the conclusions is we found out that AI is more closely related to the SOTIF standard compared to the 26262, where we focus more on random hardware faults, systematic development failures, which does not really help the AI systems a lot. So some of the key learnings we know from the 5469, data and its quality is key. Data will be your new specification. So you cannot write specification for AI systems out of the box, but depending on the data that you have, your specifications will greatly improve and what you measure will also be improved. Reliably explaining model behavior is challenging because, as I said, it's a big spaghetti factory. And then if you really try to understand what's going on, it's near impossible to understand what is going on. And the biggest challenge is I had one developer which was developing these models for the gaze detection system. And by the time I tested it, he came up with a new solution. So which actually meant that my solution, which I tested, became invalid. And this is only going to become a big problem because somebody mentioned Tesla gets zillion bytes of data every now and then, but by the time you define a solution, test it, and deploy it, the problem is already outdated. Yeah. So we have to give adequate focus to the models and let's say the data that we use to improve our models. One of the most important things is the development bias. Just for the sake of, let's say, experimenting, we gave the same problem to 2 different developers, and the approach that both of them took were wildly different in order to solve this problem, especially with the architecture that they took, which we saw before. Development bias is going to play an important factor, and this is something that we have to be very careful about. Yeah? So, this is already kind of not a secret anymore. I think we have a lot of people looking forward to the ISO PAS 8800, which is going to be safety of the AI technology itself, which hopefully covers or which is a little bit more than technical regulation and gives us a little bit more norms so that more and more companies are very confident in deploying these kind of technologies in their systems. So I would like to conclude by telling you guys about the challenges ahead. What we faced during the 5469 is still very generic and not specific to any industry, so that makes it a little bit more difficult to define a framework, which we also much like and love. Hopefully this is answered by the PAS 8800, which is going to be hopefully released this year. Ethics and behavior, validation and acceptance, still these are challenges. We have to really focus on quantitative evidence, which is basically test data or maybe digital twin, which somebody is going to talk about, virtual testing before we are going to deploy these systems in the field. Sufficient robustness of AI assurance case. This is one of the most pressing questions we have during audits and assessments. How do you guarantee the behavior of something which you cannot even write specifications for reliably? Yeah. What are you going to compare it against? So who is going to say that the AI system is safe? Is it going to be another AI, or is it going to be another human which we are trying to replace with AI? Who is going to say AI is safe enough? Yeah. Hopefully the lessons learned from L2++ or maybe L3, L4 systems are going to help us a little bit in the near future to define what is safe enough in the market. Yeah. And for sure, we cannot compare it with the average driver, because who is the average driver? So balancing public expectations on AI is, for example, if a customer that buys a car that really wants to say, okay, my car can do anything and everything, is it really the right expectation to have? Because that's what Tesla is right now doing, finding the pulse of the customer so that maybe they can sell more cars with what customers want, but is it really the most safest solution? Or is the approach that's taken by other self-driving cars, modularizing everything, is it the safe approach? Nobody knows. Or do we have a third approach, fourth, fifth? Nobody knows yet. So at least we are in Europe looking towards the regulatory bodies to find good solutions where people can at least use as a guideline to start developing and releasing these systems in the market. But at least what I know from the government bodies, that developing these systems, maybe it has its own challenges, but ensuring that these are, let's say, regulatory approved and releasing them in the market is already quite a big challenge. Yeah. We only see very few instances of geo-fenced applications, or maybe very few closed cycle applications in use, but more widespread applications needs more regulatory approach. So with this, that's a little bit of my questions, but I would also, since I have a few more minutes, I would like to show you some more standards that you can use. One of the other, I would say, challenges is that there are a lot of different organizations developing these standards. You have the ISO, SAE, you have the BSI, you have the IEEE. So a lot of different people are trying to define already quite good solutions, but which one to follow or which one is the right fit for me, maybe the AI that we develop will tell us. And also we have some other standards with AI and machine learning. This is the previous slide was especially with ADS, automated drive systems. And for AI, you still have a lot of new standards where IEEE and ISO, IEC are leading the efforts to maybe understand what's going on in the market. With this, I would like to close my presentation, and maybe are there any questions from the audience? Thank you.
Thank you. I mean, there are experts here on the AI panel boards are there. 8800 in the direction is going much ahead of what you expect. Maybe have a look. It is pretty much try to align with the 26262 and 21448, and it is strongly in connection with 5469. I have a question here.
Sure.
In part of your presentation, when you are discussing about the users level, are you, I'm a bit confused with the, are you classification level or users level? Are you?
The class 1, 2, and 3, these are different, but I'm more focusing on the usage level.
Yeah, then in this case, users level A1, B1, and C will be relevant for the safety, whereas the B2, C2, A2, B2, and D, and C also partly not relevant for the safety or not applicable for the.
There are many different classifications for this, but how does it really relate to ISO? We did not go so much into detail.
Not the ISO, but the topic was for a safety related applications. The 5469 will be
5469 yes.
Will be that what they're doing, like
for sure. Yeah,
and there are the independent assessment groups are already certifying the product against the 5469 automotive application, along with the 8800 already started, like TÜV already started doing that.
Yeah.
So yeah, I mean, I'm a bit confused with the classifications and the users definition, what you portrayed maybe.
Yeah, but this is already quite some time ago. So this is something that this is, I have to give a disclaimer that this is not 1:1 with the 5469, but this is something we developed internally for ourselves based on the 5469.
Okay, then it's fine. Yeah? So
just to keep it really simple. Yeah.
Okay, sorry, we have now one online.
Yes. So, thank you for the presentation. Do you believe that traditional functional safety approaches, for example, following ISO 26262, are no longer necessary and replaced by the methods you have described? That's the first question. And the second, or are you saying traditional methods are not enough in case of AI?
I would say more the second, because this is the evidence why systems like ISO, I would not say you should just completely scrap them, because a lot of people will be angry with me. But ideally, we just say ISO 26262 focuses on random hardware faults and systematic development, while AI, maybe it can make a lot of mistakes, but is it really safety critical, yes or no? We don't know yet. Yeah, so that's why you need a lot of different data, and you need an approach that complements 26262 rather than completely taking this away and doing something out of the box.
Yeah, but the point as well that the ISO 26262 mandates somehow a B-cycle approach where the requirement definitions are very important. Then you go to the architecture definition and so on. Well, with the AI, you are skipping completely this portion and you have no requirements. You are basically explaining, teaching by examples, by data. And then you are moving a bit the problem. And now the ISO 26262, you can still apply to the hardware, to the software for systematic failures, for random failures, and you have to apply. But then when you go to the actual model of the AI and the can't this really provide the right functionality, the right nominal performance, that's you go more to SOTIF and to the new standards.
Exactly. Yeah.
Thank you very much for the presentation, Alex Maras from Electrobit. You have this usage classification, and these classifications remind me very much to what currently the European Union is doing in the AI Act. Are you looking at this, and
Yes.
do you see in which criticality level these systems will end up in the end?
I would rather say regulations are quite vague at this point, and then the regulations, as usual, they will not say, please follow this standard, but they will only give you a very vague statement of it should be something similar to this. Like we said yesterday, the standards are not the holy books, but what you define to make sure that your system is safe is the most important. Yeah. So I believe from the AI Act, we still believe the usage clauses, that's always a 50-50 that it will be included, yes or no. I don't know yet, because I have not read the act yet. But as we already know from experience, regulations will be far behind than what the actual technology is. Yeah, and one of the problems is from the approval bodies, there is yet nobody that is an expert that can certify these systems.
Yeah, what is clear that the AI opens up new challenges and new topics that I think that the new regulations will not tell you what to do, but will put some guardrails of what you should not do. Yeah, use AI for safety or some kind of bias that maybe you have some, yeah, some depends on the origin of the people and so on. They may have some bias that are not detecting, yeah, some race and so on. So yes, now we have the AI Act in Europe. In China was 2 weeks ago, also was announced something similar. So many guardrails.
Yeah. Yeah, Juan Pimentel again. Just to clarify this classification of subsystems from 5469, similar to what I was talking about earlier, this is a bit convoluted way of classifying it. It's actually 2 levels of AI. They have A1, A2, B1, B2, C, and D. So there are 6 altogether. And the criteria is that some of them could be automated, not automated. Some of them could be for online versus offline, something that you're talking about. Those are the criteria that are used to classify these subsystems, okay? I'm not sure if this will be well accepted in automotive, because remember that 5469 is not automotive, it's very generic functional safety. So that's something that will come up in the future. This will be related pretty much to, perhaps if you correlate this to 26262, to the AC levels. I would love to see that work extended later on, but still too early, you know, it could go in many directions. I hope this more analysis of these classifications. I feel neutral. I mean, I like few aspects of this classification. I don't like few other aspects and stuff like that. And so that's my own opinion. Thank you.
Okay, maybe okay, before to close, I just wanted to make a comment and a question as well.
Sure.
So we are always talking about the standards for automotive, not automotive, but attend safety. Is it safety or so why we have so much difference for automotive and non-automotive? Do we notice? Do we understand this?
I think so. Especially from a very practical experience with this standard, it should be written for a coffee machine, maybe AI or a toothbrush, whatever. And also it has to be applicable for something that moves at a speed and has to make decisions that can define or not define injuries to the user. Yeah, with a toothbrush, what's the worst that can happen?
Yeah, of course. Well, attend if it's ASIL-D or is it SIL3 or MSIL, whatever. Attend safety is safety. So why do we have so many different standards? I mean, behind the jungle that we have already in automotive, we have now the jungle in automotive, jungle in industrial, medical. So why we do have so much domain-specific standards? And I think attend what is changing is not the safety. What is changing is the way you are developing and the constraints you have in your product. For example, in avionics, potentially you can put one computer on the right wings, one computer on the left wings. In automotive, you have different constraints in terms of space and so on. And also the development life cycle, the way you are developing is more distributed. So there are many changes like that, but then the safety is safety. And as I agree with the Kwan, but then system engineering is system engineers. So we could remove all standards and say, make it safe. But finally, we need some guidance. Okay.
That's true. Yes. Just to finally close it, also we should look at the legality, liability perspectives that we have something to fall back on. Simple as that.
Exactly. So standards are always legal framework.
Yes.
Okay, many thanks.
Thank you. Thanks a lot.
Okay, I would like to call now here Juan and Oscar. And the next, as you asked, you really enjoyed, we have now a panel. And okay, the panel we're talking about, okay, the header is overcoming compliance challenges in automotive functional safety. And what we are gonna talk now is about compiler for AI and differences with regards to standard software compilers. So you know already Juan presented before, Oscar Lotos did not present before, but I think you know already him. He's a CEO and founder of Validas. Okay, so we've been talking a lot about AI and so on. What maybe we have not really talked so much is about tools and like AI compilers and so on. So maybe can we talk briefly what such tools are and what are they doing as opposed to a normal C compilers? Can you give us some comments about this? Just to set the scenes.
Yeah, well, of course, when we're talking about tools and compliance, we should start with the SOTIF standard, which is saying, hey, there is a tool chain how to typically AI is done. So you have your training data and your verification data and saying this, and then it states, yes, and you should use ISO 262, 811 tool confidence to your tools at least to make the tool chain safe. So that's definitely something. But when you look closer to these AI tool chains, and we work with a great American AI company, they have a lot of optimization. So you can optimize the network. You can first train it and then optimize it and then verify it. So, and these optimizations are, for example, reducing the size of the floating points from 32-bit to 16-bit. because then it's the network gets smaller and you can work with bigger networks. So those are some optimizers, and yeah, of course, is also a tool is to distribute this the reasoning and to, let's say, balance all the different parallel GPUs, general processing units, and they are yeah, they are doing the work. And of course, when you have these convolutions, we saw it previously in a talk where you have these different things, and every node has its own task, and that's why it's so fast. And yeah, those kind of tools there are. And then there are, of course, the other tools for verification. And for example, you can, some of you might be able, there's a framework to qualify and verify artificial applications. I found it's a German startup from KIT. It's called Validator, but with AI, Validator. So it's validator.com. If you type it, you will see it. They have two different kind of verifications for AI applications, and one is yeah, you can upload an AI and then they are examining it and entering questions and checking the answers, or they try to compute adversarial. So there are different kind of verification methods, but also this compliance method. And I liked very much, for example, for the EU Act, AI Act, there is a checklist, and then you can go through it and say, yes, we have done this, or even upload fill some templates and make it compliant. So these kind of tools are the specific ones for AI applications. So, well, of course, every company has its own solutions to automatize and process and so on, but these are, I would say, the common ones.
Yeah, in terms of compilers for AI, you have to take a look at also the goal, the end result. So we're talking about automotive here, which is very different than other applications of AI. I talked about that AI could be used with so many things. And some of these compilers are getting so specialized that they do the translation, for instance, for a TPU, tensor processing unit, or a GPU, or a CPU in general, or more specifically for ASIC, more specialized hardware, if you will. So you have to take a look at the type of hardware that would be in a car, which is totally different than consumer electronics, for instance. So one of the compilers that I like a lot, at least the idea, is TVM from Google, the Tensor Vector Machine. Because at the end of the day, when you translate these AI algorithms, okay, traditionally compilers compile scalar quantities, basically. But in AI, you do not work with scalars anymore. You work with vectors and even matrices, and they call it tensors. So they optimize the tensor processing unit. In fact, the TVM stands for that, it's a tensor virtual machine that you translate the intermediate representation of the AI algorithms in terms of graph models, basically. So there are several stages. The top level will be the graph model, and then from that, they translate into intermediate representation model, and from that to the actual hardware. And the actual hardware could vary. You could be talking about a huge machine, computer, let's say, or similar to what NVIDIA or Tesla or whatever they're doing. Or it could be your iPhone, for instance. There are many algorithms that could run in the iPhone or your cellular phone. So the system is very complex. And like Oscar was mentioning, you're talking about optimization. It's a very big issue, to optimize the code, optimize the time that it takes, or even to execute. So there's a lot of issues. So the translation process is not very straightforward. It's really becoming very, very complex. At the end of the day, in AI, it's based so much on the nature of AI, because like convolutional neural networks, you talked about that, is really a lot of matrices and vectors, and they call it tensors. So they optimize those operations. However, it's not always ideal all of the time, because sometimes that optimization works for some parts of the algorithm, if you will, some portions, but it doesn't work very well for the other portions. So this is why you have to optimize it. So the solution does not always work for all types of operations. So it's an issue where you have to take a look at, first of all, what is the hardware for your AI that you're interested in? what type of algorithms. I think based on that will guide you to the type of compilers that you need to use.
Okay, so before we mention that for AI, we cannot really follow ISO 26262, but we need to rely on different standards, different solutions. Going to tools, do you think two questions basically. The first question is, do you think the tool evaluation offered by ISO 26262 is still relevant for also AI tools? And the qualification methods that are proposed, do you think are also still relevant, or we also need to go now to different level of standards and different solutions?
Yeah, well, I think the first is the tool classification. So if we see, and this is still relevant, so you can classify these optimizers and say, okay, let's just test the optimized thing and then measure the accuracy. And well, this would reduce the tool confidence level or the qualification need to TCL1, meaning this optimizer is uncritical. If you have then still good results, and you compare the results before optimization and after optimization, but at the end, what counts is after optimization. So this is an easier step where I would say we can get away without qualification. But when it comes to measuring accuracy, then the tool, well, should be qualified, because then you trust this accuracy when you are making your safety argument. So this is rather more critical. But a very important aspect is the data inside. And when you look to ISO 262, there and on any other safety standard, I don't know any safety standard about the data. I know a data safety working group in UK. They meet every month or 3 months and discussing data safety issues, like having the wrong coordinate when sending a missile or other things are really data relevant things where we do not address at ISO 262 at all. We have configuration data at a small thing, but this is not the data which we are currently seeing.
8800 will cover a bit more this.
Yeah, and I think that's also coming into the question when validation thing. So when we really want to validate an AI tool is doing, let's say, the right optimization, and then we need to have more data and different testing strategies. I still think what ISO 262 proposes is validation is good, but the challenge is not the method. The challenge is really the test cases. So we call it a test strategy. And the test strategy is, I always explain our customers, it's a number, how many test cases you have or you need, and an argumentation why this is sufficient. And then we are in the data problem and cannot really say, hey, we need here 1,000 test cases, then we are safe. How do you know it? Maybe statistical can help.
Yeah, absolutely. I believe that these compilers for AI, they need to be qualified. There's no question about it. However, we're still early in the stages as an industry because this stuff is fairly new. And in my opinion, one of the best things that could happen in this area, I mean, this is an area where standards are good. So 26262 has a nice set of guidelines for tool qualification. I like that. It's great. It would be awesome or great that we have something similar to that for compilers for AI, but we're still a long ways from that, so you could have guidelines for people to actually use these guidelines and qualify these tools, that would be probably a few years down the road, but that's
but the
something
question
that would be
again,
great.
sorry to interrupt you, but the question again is why the current guideline is not sufficient? What are the gaps?
Oh, that's a great question. Because it doesn't take into account the nature of these compilers. We're just talking about the nature is quite different. Conceptually, they're okay at a very high level. Whenever you go to answer more detailed questions, that's where you cannot answer those questions, basically. So yes, I mean, they're very good at a high level, but you get a problem. Like I've done tool qualifications myself. And if I were to apply 26262 right now for a project using AI compiler, I would do it well half of the way, and then I would get stuck in answering some of the questions. That's my opinion. And I need some more guidelines to do it completely, in my opinion. It's
maybe we should be a bit more precise what a AI compiler is. So the definition, you can have, let's say, some inference engines that are written in C, and then use a C compiler to bring this to your target GPU. So this is then a standard C compiler used within AI applications. But you can also have something like the CUDA language, which allows you to formulate and distribute your AI application to several nodes and all those things. So this is also where you have a CUDA language specification and you can qualify against it. So, but maybe you know better than I, these training tools, when you have your AI architecture with these different tensors and those things, and then bring them down to the different nodes and hardware. Is this AI tool what you
It's
mean?
pretty much related to the first talk that we had today was great in that they use a specific algorithm, if you will, and try to correlate to the level of safety. You know, we need something like that because you need to take a look at the level of safety that you need in order to qualify that tool for that particular application. It has to be tied in, you know, and that's what is missing, in my opinion. It's very difficult to answer those questions right now. One way is to just take a look at the risk assessment from 26262, or just forget about that and talk about, in general, just probabilities. You know, what at the end of the day, it's all about, you know, probabilities of you know, things that would cause an unsafe usage of your product. You know, unreasonable. You need to prove that it's not. It does not introduce unreasonable safety of the system at the end of the day. You know, what's unreasonable? You know, that's you get into the probabilistic modeling of that. You know, that's one way to do it without using the standard.
So if I would suggest to extend ISO 262, I would say add a chapter about data. Give different data attributes like accuracy, like precision, up-to-dateness, whatever we have as an in case data is relevant, let's say training data or other things, then you need to have some aspects of it and then also some methods how to handle it. And yeah, there are methods how to classify the risk of data. So this data working group, they have a data assurance level defined, and they say what, how critical is the data, what can happen if the data is wrong, and then you can also reason about these data aspects.
Yeah, just to follow up on that, that's exactly what I meant earlier when I talked about these performance indicators for AI. That's something that's missing. In my opinion, that's the guidelines I was talking about. If they could introduce these performance indicators for AI, like precision, recall, and area under the curve, and there are a few other ones, and use that into this qualification of the tools, that would be awesome. That's the thing that I'm talking about that's missing.
Yeah. Then you have an argument because sometimes I get asked, when have I done enough for tool qualification? Because ISO 262 just say you should show that the tool complies with requirement. And of course I can say, yes, in ISO 262, there's a chapter about compliance, and it says if you have 100% code coverage, you're compliant. But that's not what is intended to have code coverage in the tool. So, but if there's another chapter about data, then we can use this in case we don't find any argument. So we sometimes qualify compiler using code coverage argument because we have no other argument to ensure the data the test cases are sufficient. So we measure, for example, in the optimization field of a compiler, we measure whether all optimization rules have been triggered several times. And then if they have been triggered and we're correct, then we know this. So we just reuse the argument of code coverage to qualify compiler when we need it, if we don't have anything else. And if there is no argument for data safety, we cannot reuse it in tool qualification. And that's what I would have here. But
yeah, absolutely. Thank you. This is what I was talking about. That if I were to do that job right now, I would get stuck because we need those kind of things from the AI community, you know, to correlate to tool qualification.
Yeah, but I have been yesterday evening in the dinner. I have been acquired to join ISO 262 and contribute more actively, at least on the tooling side. And yeah, maybe we meet each other more frequently and can contribute there.
Yeah. Any comments or questions from the audience here and also online? Okay, one here.
So we specifically, Avinash from Place Automotive, so we specifically speak about compilers and differences with regard to standard compilers that we already have in the market. But one thing that's yeah, in the back of my mind is what are the key differences that you see with AI-specific compilers compared to normal yeah, safety compilers?
Yeah, well, the key difference is normal compilers have a well-defined specification. So you have the C++ or C standard. There are ISO documents specifying exactly what should be done. And there are on the market, there are available qualification suites you can just buy for the standard, because there's a standard and they can make a qualification suite that covers the standards. You can just buy and run it. So, and in AI, I don't see those kind of standards.
But
so that's the challenge there. So you can, of course, qualify any compiler compiling language X to language Y. So, and Rust is a bit a corner case here. They don't have an ISO standardization, but they're trying to specify a language, but they have also these kind of patches and change requests and whatever. So it's from C to Rust, it's a small step, but from Rust to AI, or from C to AI is a bigger step, because we still lack the specifications.
Yeah, let me give you a different answer to that question. It's a great question, obviously. The traditional compilers, they compile language statements like C++, Pascal, or whatever, Java, into what is called the machine language that has to do with the actual architecture of the CPU itself. So they go from very high level all the way down to the registers and the central processing units, you know. That's a well-known operation that has been done for many, many, many years. Now, AI compilers work at a much higher level, and they're not based on translating statements. They're based on translating operations, vector operations, matrix operations. Because at the end of the day, like a convolutional neural network, it's all vector processing, matrix processing, that they call it tensors. So they go to that level in order to save that. So the translation is a massive translation. It's not a single opcode, but it's called a single statement, if you will. It's massive, you know, and that's where the main difference is. The other major difference is that the initial level is very high up. So you start with a graph. You don't start with a statement like in traditional compiler. You start with a graph, and from the graph you go into the actual operations, which is all math, you know. And then from that, they move into the hardware, which is another challenge because there are all kinds of hardware. You know? So it's not just one type of hardware, going all the way from massive, even on the cloud, processors to your cell phone or intelligent phone, whatever. So there are all kinds of hardware, and trying to do that job for all kinds of hardware is also very difficult. So this is why there are several stages, you know, all the way from the translation at the very beginning, all the way to the optimization at the very end. And this optimizer it's a big problem because they cannot optimize everything. So the optimizing is kind of a miss and hit. You know, like I said, myself, I like what Google is doing in terms of that, because they translate into all kinds of hardware. You know, it's awesome. The TV, and you know, you take a look at that. You know, the tensor vector machine. That's what they call it.
Another
virtual machine, sorry, not vector machine, virtual. You know.
Another big difference is the input. So when you're compiling the software for an ECU, you have millions of lines of code which are programmed and maybe some data. And the input for AI is the opposite. So you have some small flows that you translate. The architecture reflects somehow, but then the most part is the data. So that's what yeah, different ways of programming.
Yeah, but okay, let's go maybe back to the basics. So I mean, as we mentioned, the ISO standard has the two classification. This is the tool impact, tool detection. I would say from this point of view, no big implication. So I think we can still apply this classification also for AI tools and end up with TCL 1, 2, or 3. But then the ISO standard is proposing 4 methods for qualification. One is proven in use. I will say, let's put on the side. The second is development based on safety standards. Again, let's keep it. So we only have 2 methods. One is development, and that may be also something that we should clarify. The ISO standard doesn't say select one method, the one you like, say select a combination of methods. If it's only one, justify one, why only one is sufficient. That's maybe sometimes is not done. And I see companies jump into, okay, let's use this. So at least let's try to select 2 methods. The first method is development based on some quality standards. One of the issues I see with the AI compilers, like you were mentioning TVM and so on, we have open source. So we go back to the issue that we will discuss also later today. Can you really develop these based on quality standards, not even safety, quality standards, considering we have open source? That's, I think, is one of the big challenges. The second method is validation. Validation, again, is not I'm testing my tool, because that is already covered in the first option, the development. Validation is I'm checking what my tool is doing, what is expected to be doing. And yeah, I cannot apply the same data that I have into training, because my hardware for training and my hardware really on the target is different, and I cannot spend 10 years testing, so I have a different performance. And now, can I really reduce my data set to a minimum amount to have this validation? But that's, I think, is one of the big challenges as well.
I completely agree. So there are many good points. And why it's called validation, not verification? Why don't we validate a tool and not verify it? Verify would be going through all the specifications, and validation means finding out the critical ones and then doing what is intended. So that is the validation. But you had a question, Alexander?
Now it's working. It's more about the OSS usage actually, and this is also what we've seen in the presentation from Red Hat yesterday, and this is how it works. You need to do a step back and look at the objectives that the safety standards define. So not going into the details, what they say, how you could actually achieve the objectives, but do a step back and look at the objectives and find an argumentation why the objective is met even with different methods. This is what all the safety standards support, so they don't force you to use this, and this is what we have to do.
Yeah, also to add to what you are saying is very valid. And again, I don't know if you all are aware, but in the second edition, we try to change, moving from really requirement-based to object-based. Of course, we have requirements because it's what you have to do to claim compliance. But what the standard says, okay, it is a requirement to meet the objective. Finally, what is important is the objectives, because potentially you have topology and you have a technology that the requirements are not all applicable or also not relevant. Then I fully agree. Go back to the objectives. What do you want to achieve? And then justify that you are able to achieve this objective. More questions online as well? No one online? Okay, one question.
Just wanted to shout out the topic and wanted to know what you think about the synthetic data and its usage in AI training.
You understand? So the use of synthetic data in AI training. So instead of using real data, you can use synthetic data to have more miles or whatever, and
use AI to create AI models, AI data.
Well, not necessarily AI. So I think you can do a lot with simulation and virtual twins, and this is definitely useful and more. I think even virtual data can be more useful than real data, because if you collect real data, just miles, so it won't help. So it's like, hey, we have been driven 1 million miles, and now it's okay. But if you have never driven through a city, then you don't know. So. But with the synthetic data, there are catalogs available, like switching the line, surpassing another car, having crossing. So there are a lot of scenarios available, and that's virtual data. And another very important point on virtual data is you can better inject faults. So you can train, oh, there's a child coming, or there's a bird coming, or there's a, well, whatever can happen, you can better train it or test it using virtual data. Of course, at the end, question is, it's also a tooling question. How good is your simulator? How good is your virtualization thing? And do you at the end count the real miles on the street, or do you need the virtual data for the argumentation? And if you need the virtual data for the argumentation, then there is an impact, and then you need to classify the tool or qualify the tool, show that it's really good data. So that's definitely going to happen.
Yeah, let me add something to that. I totally agree with that. I guess my answer is it depends. It could be very dangerous. I like to offer one way to actually guide the usage of that. It has to be between the distinction between an open loop system and a closed loop system with feedback, okay? As long as you use it in an open loop, it's fairly safe, okay? And this is probably what you were mostly talking about. It is helpful to have synthetic data to generate, but whenever you have feedback, it means that you use the AI system to give you data, and then based on that data, you feed back to the system, and then you keep doing that, and that could become unstable, okay? Because one of the problems with feedback, just in anything, even in dynamic systems, is that it could become unstable, you know? So stability is a big issue in feedback systems. So you could end up in a situation where the AI system is just going one way, and it's just the feedback keeps growing and stuff like that, and becomes totally unusable and dangerous. And this is what some people are talking about, the sayers of AI, is that AI will take over or something. That's what they're talking about.
Skynet. One question at the end.
Just a simple, Carmine from Art Germany. Yes, just a simple question about this synthetic data can contain, for example, not experienced situation event. So the synthetic data, I think, are classified for the experienced situation or I don't know about the experience of who classified the data or something like that. But I think that the real data can contain also if they could be continually the same, because it's very difficult to find an outline. No? But you think that the synthetic data sometimes could be not very real. No.
Yeah, that's an interesting aspect we didn't mention so far. There is a law and UN regulation. It's from 2020, from 22, so 2 years ago. And this states whenever you're using simulator to qualify your ADAS application, of course, you have to qualify the simulator, but then you have to qualify also the models you're using, meaning the data where you are driving. And this is really huge. And I was on a testing conference, and they were all talking about this, because that is, honestly, it is the only thing that makes sense. So if you have Python, and some people ask us, can you qualify Python? You have so many Python programs, but this doesn't make sense because Python is like a programming language. And in the same way, it's with a simulator. A simulator, qualifying a simulator, yeah, it can add and multiply correctly, but is your model correct is a more important question. And of course, strictly speaking, you should have requirements, or they have requirements now, they have legal requirements to write down the requirements for the model. And if it's an abstract model, then you can be very abstract. So for example, I learned at a university, and this is a nice example, what is a model? A model is an abstraction for a certain purpose. So we can always use the real world, and we do not need to model and abstract that is very complex. And the example the professor made was, there is at University U, there's a chair looking to the energy houses and low energy houses without heating and reducing energy. And they had a house with grass on the roof and were measuring things. And then they asked themselves, but there are humans living in these houses. How can we model a human in the house from the energy perspective? And the answer was, yes, a human is emitting 40 watt. So let's put a clump into it or two clumps into it, and then we model humans in these houses. So a clump can be a very good abstraction for a human for a given purpose. And that's exactly what you need to have. You need to know the purpose of your model. If it's to measure the distance, then you need to be very accurate there. If it's to measure the drift, then you need to be very accurate there. And if it's measuring time, you need to be accurate there. So there are different purposes, and then you can qualify your model is really doing what it should do.
Yeah, absolutely. Model validation and data validation are probably two of the most important aspects in AI. Okay, a lot of people are talking about it, and the data has to be statistically validated. Because if you just focus on one type of statistics, then obviously that's not very good. There was a story, I don't know if you read about that few months ago, that going back to Tesla and Elon Musk, they were saying that the data was biased because the data that were fed into their neural networks was based around the area where Elon Musk lived and went to work, because they wanted to make it sound like, it works better. They probably did not want to get embarrassed or something didn't work. So they used a lot of data based on where Elon Musk lived, and that is not right. That's totally not right, going back to your topic. So how do you qualify your data? It's a very important component. It has to be statistically independent and cover all of the scenarios, basically, that you want to cover, So yeah, it's a big problem.
Yeah, it's a big problem. And again, also, if you want to be too strict, like follow the traffic laws, all the rules, what the ideal human will be doing, probably your model will be wrong. And you need to also consider the edge case that will happen in the field. And maybe sometimes you need to break some traffic law to avoid accidents. And that is also one of the issues. How do you train a model for this? Like sometimes you need to cross a line on the street, go to the other lane of the motorway, or not motorway, no, of the road, because there is an obstacle. And yeah, how do you train all of this? That's a big, big challenge.
A nice closing word.
Yeah.
Nice. We can use the remaining 2 minutes
Well,
for
actually,
the next speaker.
Yeah, here it says 2 minutes, but we are actually already 5 minutes somehow behind the original schedule. So I will say if we have no more questions, we could stop here. Yeah, and yeah, again, thanks to the panelists. But Oscar, you need to say.
Thank you.
Okay, thanks again, Juan. And yes, the last presentation before the coffee break is a qualification of tools and libraries for safety and security. So somehow continuation of what we started. And
fits very well. Thank you.
Yeah. So we can jump to the questions.
Okay. Well, this time I'd like to continue what has been discussed yesterday, the difference between safety and security, cybersecurity. And we have already talked enough about the ISO 262 things, but let's have a look to the cybersecurity and see whether and how we can benefit there. So, well, I think that's is clear to all of you. Well, we want to build a safe and secure system. We need to have safe and secure hardware, software, and tools. So, and all is based on the standard compliance, meaning having something like a driver's license to be able to, drive safely. And that's the structure of thing. And by the way, who knows what the I in ASIL or ASIL means? Integrity, yes. And what does it stand? Is it just trust in someone? integrity means compliance to the requirements. So this is, and that's why this I is here. It's compliance with the requirements. So you have process requirements, and when you're compliant with it, then you are per definition integer. So that's a definition of integrity, meaning compliance with requirements. So doesn't really, there is no strict dependency between safety and integrity. You can have a driver's license and be a bad driver, and you can be a good driver without a driver's license. But at the end, I learned driving in the driver's school, so I try. I'm not sure if I'm a safe driver, but I try to be. Yeah, well, the definition, what is a tool? The tool is used to develop the software. It is not part of the product. So if in case you want to integrate the tool into the product, let's say if you put here the complete Linux, not only the small parts of it, and including a compiler because it's part of it, yeah, then the compiler is not a tool anymore, then it's a software. So, and that's the definition. And for the libraries, the safety standards, you know, most of you know that software can always be compiled to an archive, which is called library. So you can make your autonomous driving software, compile it to an archive and say, now I have a library and I want to qualify it as a library. That's not okay because the safety characteristic is that the risk is shared. So it's like open source library, which is used in many different cars. So if you compile this to a library and then bring it to the car, the safety experts will laugh at you and say, no, that's not a library. And even if you then claim it's unchanged. So this is really unchanged means from the upstream downloaded it and use it without changing. So this is the definition of a library here. Yeah, that's and when it comes to software, software is using library and is built using tools, and that's the field of Validas. And I won't do any other things of Validas. That's just where we are specialized here. So we won't help our customers in safety of the software, but here in tools and libraries is enough for us to do. Yeah, let's look at the risk handling in tools and libraries. And there are two strategies. You have a risk, something may happen, and you can handle it and say, okay, if something happened, then I'll send you an ambulance and this will help you. But that's good because can help it and can reduce the risk. But it's the other way to build an airbag that you don't get hurt. So the risk is you get hurt in this car. But you can have it and say, okay, once you're hurt, I help you, but it's of course better to reduce it. So if you don't get hurt, if I have airbags for you, then it's better for you. And this is the strategy. And usually we say we need to reduce the risk to an acceptable level, and then the remaining things can be handled. So you have your instruction manual, pilots have their specific training about how to manage an airplane because they need to learn the known bugs of it and others. So they need to know what they can do with it and what not. So this is then the risk handling can be done to the given to the system. Yeah, so that's of course, and that's also ISO 262 tries to give you guidance how to reduce the risks and then handle the remaining ones. And this is also, of course, this is true for the normal supply chain where you say, okay, I'm my OEM, my first tier, my second tier, hardware deliverers. So this is the normal supply chain. But we also have a tool supply chain going from the tool user to the tool provider to open source community, providing all the tools. But let's have a look to some tool problems, not all of them. Maybe the XZ attack is one of the biggest ones, or the SolarWinds attack is something. So SolarWinds is a security company which has been attacked, and then has been hacked, and then the hackers did not encode the whole computers and say, give us $1 million. So the hacker did worse. The hacker modified the tool that SolarWinds, this security tool, is distributing to the Dow Jones companies, Ministerium of Defense, White House, all they are using this the tools from SolarWinds. And then SolarWinds said, hey, dear customers, we have a new version of our tool. And here is it. We have a new version of our tool and this was hacked. And then all these companies had open doors. And the day when this went public, the stock course crashed by 80% of this company, and today they don't exist anymore. So just to have an example what can be there. And I think the XZ attack was even worse. So we were just lucky that nothing happened, but this was even like a nuclear bomb was this attack. So they are really dramatic attacks from security. But also the safety is dangerous. So I have seen or I've heard from testing drivers who are driving their cars on the day and in the evening programming it. So extreme scenarios, extreme maneuvers, sliding with the car, things like that. And one evening, the testing driver was programming the car, and the software get too big, so he could not bring it in the car anymore, and he couldn't drive. So then he had an idea. Hey, I can do something cool. I can tell the compiler to make the program smaller and optimize for space. And then he optimized for space, and it fit into the car. Next day he could drive. But guess what happened? There was a compiler bug. And when he did the next extreme maneuver, there was a self-steering on his back axis. The wheels were self-steering. He couldn't control the car. He lost the car. He went into the hospital. So nothing worse happened. But this is an example of a safety risk that can come from those tools. So not only in security we have risk, but also in safety. Yeah. How can we do tool qualification and safety? I think you all know this. I can be a bit briefer. So there is this tool confidence level that is determined. These are the methods we have explained previously. So you're saving me some time, Ricardo, here with this. Important is the combination that Ricardo mentioned. So validation means just testing the tool, running Hello World. You can argue I've tested it, but you cannot argue that this was in compliance with a safety standard because Hello World is not enough. And that's where the combination matters. You should have a good test strategy, and then this is a good combination of between the safety aspects of testing, good traceability, good requirements, and then you have the main aspects covered here, and the rest is testing. So that is a sufficiently good argumentation. Yeah, the documents, of course, there's a classification report with a tool confidence level in it. And the safety manual is the most important thing because it tells the user how to use a tool safely and and handle the remaining risks. And depends, of course, on the classification. If you say this feature is not used, may not be used, then you need to write in the safety manual, don't use this feature. If you say, hey, I can detect the error of this is an uncritical feature, then let's say I can detect the error by testing the code as it was manual written. If there's a code generator, you can test code as if it was manual written. Yeah, then you need to write to the safety manual, test the code as if it was manual written. And the problem are the undetectable errors, these remaining ones where you don't have a high detection probability. And that's exactly for those, you can create a qualification plan to reduce the risk. You can say, okay, that this compiler optimizes correctly. I want to reduce the risk. I cannot do this by testing. I want to test the optimization part. So you don't test the whole tool, you just test the part which you think is critical. And that's why it's not called verification. Verification would go to the whole tool. Validation just goes to the critical, to the important aspects. So this is the reason. Okay, those are potential tool errors that you want to test with the test strategy, and you have test cases in it. And then you run the test cases and you see, oh, not everything that can go wrong went wrong. Maybe everything is green, or maybe you have some remaining bugs where you can easily find workarounds and put them to the safety manual. You should also have the known bugs, but then the safety manual is perfect. Yeah, how is the process? I mentioned this tool supply chain. So of course, the OEM has some risks, something, and they can reduce the risk and they can handle the risks. And of course, they want the risks from the tool, which I mentioned earlier, they want to be reduced. And they will say, dear tool provider, can you reduce the risk? And then they have they want to detect the risk or avoid the risk, and they classify the risk and say to the tool provider, please reduce your risks and give us the ones you can't reduce. And that's what the tool provider is working. The tool providers, they are constantly making new features, which may introduce new known bugs, unknown bugs. but they also get bug fixes and they bug reports and they fix it and they get new bug reports. So that's their way of thinking. It's completely different from this here, where you say, okay, I have a security, safety and security planning. I have my start of development, start of production, end of maintenance. So this is how the OEM thinks, but this is how the tool provider thinks. And of course, if the OEM says, yeah, you can reduce this, you have to have a tool confidence level, then you will get a qualification kit and you can run test cases and you get your tool qualification report, your safety manual, reduce the remaining risk. So this is risk reduction in the tool, and this is risk handling of the remaining risks in the safety manual. So, and of course, if there is an updated version, then you need to give them new known bugs and handle them in a proper way. So this is the flow in the tool supply chain, how you work with tools on the risk side. Yeah, let's now look to the security. So this is quite well defined. We have a tool confidence level. We know what to do. We know what to expect. And now let's look to the tool security aspects. What is tool security? Well, we can look into ISO 21434 or other standards, and you almost found nothing. So you will find, tool management. So this is good. Tool have to be managed, and tool that can influence the cybersecurity of an item or component shall be managed. Yeah, what does it mean? Yeah, of course, there are tool risks, and how can we handle them? How can we reduce them? And how can we protect us against these tools being hacked? And there are a lot of examples I mentioned already. And well, we propose, and that's they don't say nothing. And when you talk to a tool provider, they say there are no requirements. We just give our tool users, in case something happened, there's a vulnerability that comes to known, and we will just give them an update and say we are not impacted. So they just do the risk handling, but they don't reduce the risk. So because the standard does not say you should reduce your risks, at least this could be said, but they just say you should manage, and therefore everything is free. So these are proposals, how would we approach it? And we have learned it from the safety side. So in the safety side, you do a tool chain analysis to determine your tool confidence level. Hey, and we can do the same thing. We can do the security analysis and come up with some tool risk levels. So this is very similar to what the TARA, the threat and risk analysis, is doing. And we can see which tool is dangerous and what would happen, and if it's an impact to safety, to finance, to operation. So these kind of risks we can classify and come up with some risk levels. In security, you always are allowed to retain the risks. You say, okay, I don't care, I share it or whatever. So just in ISO 262 in safety, you have your tool confidence level, and then you have to. But here in security, there is another step. Okay, we can decide on the tool security level, and we can argue. If it's a very dangerous tool and we argue, well, we don't do anything, this is compliant with the standard. However, if something happens, then you are reliable because you did something, and you at least you have to document it. And that's what we propose, or what needs to be done then. Okay, if we come to the decision the tool has no risk level, then yeah, we don't do nothing. If we can say, okay, let's at least handle the risks, which is the second level, we should handle the risks, then yeah, we created a security manual for the tool and show the tool user how to handle it. But we can also reduce the risk and say, okay, let's do a qualification plan, a qualification report, and really reduce the risks. And of course, also having a security manual, what we have done and what has been the findings there and things like that. So this is and very similar things to the documents we have seen in the safety. We will have also a classification report, which comes out here. This is security tool classification report. And yeah, the other reports I mentioned already there. Yeah, the flow will be almost the same. So the risks are still on the side of the OEM. The OEM will say, okay, I do a risk classification, and doesn't say how, but we have proposed it here with the tool risk level. And then we're doing a threat analysis and look to the common vulnerabilities and exploits there and exposures there that they are known. And we will go to the tool provider and ask them, please reduce your risk. and then they have the similar things. They extend the tool. Then they might add new components. They might fix some components, update components. They come up with a security qualification kit, and then you can have the security documents that I showed previously. And of course, this needs to be done also iteratively. When no new things come, it has to be updated. And well, there's a difference between safety and security. Typically, safety protects us against human errors. And this is something that every now and then happens. And usually every every year, there should be an update of the known bugs, and you should look into it, or whenever you do a critical thing. But in security, it's completely different. So they're speaking of days. There's a 0-day exploits. They are really on the same day where this happens, then they try to hack you. So if you take a week and do this in a weekly basis, then hey, yeah, this is what is practically doable, but it's not on a year, it's a week. So these iterations are much more and much closer and need to be better automated here. Yeah, let's come to a summary. Summary is when we compare safety and security, of course, the safety protects us against the human errors. The security has to protect us against the attackers. And interestingly, here's only the product which needs to be safe. But as we have seen in the SolarWinds attack here, we also need to protect the environment. So the hackers, well, didn't go into the car, but did go into or try to come into the development process of the car. And this is a different aim. And the risks, okay, they are similar. In ISO 262, we say we have the tool detection level that the potential errors can be introduced or can be not detected. So introduce or fail to detect. And the same thing happens here with, we can introduce vulnerabilities or we can fail to detect vulnerabilities. So I didn't speak about detecting vulnerabilities. So there are features in some tools like encryption or stack protection, stack hardening, and there are features of tools that can help you. Maybe the battery is over. Okay, they can help you to increase the safety, the security of your system. If you're using encryption, if you're using stack hardening, your system will be more secure. And these are the features, but what if they fail to operate? For example, a programmer wanted to clean up the memory. He was using some encryption with password, and then he cleaned the memory using memset and then 0. Then the stack did not contain the password. It's a very wise programmer that did this. But the programmer did not encounter the compiler to be very clever and saying, hey, you set a memory here, and then you return from your program. You don't use the memory anymore, so why do you set it? We can optimize this away. And then the password was on the stack, and everyone could see the password. And these are the features where we want to protect, we increase the security, but we also need to ensure that this is really done. So we need something like a tool qualification, like a tool qualification of those security features. And this can be done in the same way as a tool qualification of safety features. Okay, I think I'm done. So this is just the summary here. We have looked to the safety and security things, and we think the handling of the risk is more important than the reduction of the risk is more important, and the handling is what remains to be done. And security standards still, hesitant to ask for proper risk reduction. And we made some proposals that can be seen in the slides here. And yeah, that's it. So don't worry about tools and libraries. You look a bit worried, but be happy with what it does. Thank you.
So I think the English were ahead of time because in many languages we have one word, security and safety. Mm-hmm. English at least have 2 different words.
In Germany we have Sicherheit.
Yeah, exactly. Yeah. Sicherheit, security, sicurezza. So yeah. Okay, questions about this presentation? Online again or here?
No, before the break. Okay, one. You can have also ask me anytime, any question, you know.
Otherwise, I will ask.
Yeah.
Roberto Baccavelli from Red Hat. So basically, in your proposal, I see a different talk, basically the proposal to have a unified hazard risk analysis. Then for Validas, you wanted to follow something like that, then to have a unique hazard risk analysis for safety and security.
Yeah, this is a very good question. So we do the tool chain analysis for the safety departments of the companies, and we already made proposals. Hey, we can also, with the same tool chain analysis, we can analyze the security risks for you. But they said, well, this is a colleague, so you have to ask him. And we are asking him, but this is one thing, that the organization is a bit different, but the principles are very similar. So based on these kind of tool chain models, we can do this very similar. Another challenge is the tools are different. So when you ask, or when you see the tools that we are using to program things, these are different tools that our, let's say, IT department is using. They're using VPN, they're using firewalls, they're using, and those are the tools they mention when it comes to security. They don't mention the compiler and the code generator and the testing tool, which they should be more, but convincing the security people that the security problem is the safety side is a hard thing, and there needs to be more talks like this. Thank you.
So potentially one question from my side, so I'll stop the coffee break. You can wait a bit. How far do we have to go? So I saw projects with qualifying few tools, projects qualify any single tool you're using, even Windows. So where do we stop? How do you understand which tool can influence your project and they should really be analyzed and qualified and which not?
Yeah, one thing is, of course, when you look to a tool as standalone, it's always very critical because you don't know about the environment. And but if you look to the tool chain, then the tools can detect the errors vice versa, and then they will be lower tool confidence level. That's one thing. But the second part of the question is, do we need to consider Windows or other things? And I would say typically when we qualify the tool in the environment that you're using, then this is also covering the environment. So when we run the qualification under Windows, and we know it's working under Windows, then you can use it under Windows. So we do not need to consider Windows as standalone. But if someone comes up and say, hey, we are using here very frequently the copy command, and I'm concerned this could go wrong, yeah, well, then we need to address the concern and make a classification and say, hey, look here, if you copy your things and it doesn't think, then in worst case, please compare the size and the dates. And if this is okay, then copy worked properly. So those are things we can do if someone wants us to do it. Typically, we wouldn't ask people and say, what about your copy command? But if the problem is, if you, for example, have a debugger tool, and most people are using debugger tools, and some assessors don't know that debugging is not an activity required from ISO 262. So assessors might ask, oh, I see your Lauterbach debugger here. How is it classified? Then they open the classification report and they search for Lauterbach and they don't find it. Oh, you have forgotten about it. That's very bad. But therefore, if you have tools that are obvious, just name them in your report that you can find them. You can then say Lauterbach debugger has no impact because it does not support any activities required from ISO 262, and therefore, and we don't use it for testing, which is required, and therefore we think it's uncritical. So this is a very fast thing and very good that you don't get in problems with assessments.
Yeah, actually, in the IC standard is a bit different, no? Because we have these offline tools as well. So there we may have, I think it's a bit wide scope in the IC.
Yeah, offline is just not going to the product. So and this is yeah.
One question here.
Last question, otherwise people get hungry. And thirsty.
Thank you, Hans Böhme from FEV. What about tools like Word, Excel, PowerPoint, Outlook? What is your opinion on that?
Don't consider them. So that's, of course, you can say we have good argument. What we call what you see is what you get. And for example, if you create your architecture using PowerPoint and Word, that's okay. and this is a requirement for ISO 262 activity, but then please create a PDF file and have a look to it. And you are forced to do the review, and then please use the PDF file. Then you review what you see is what you get, and can forget about those tools.
I think the most complex could be Excel, because you can use some macros, and then this may be critical.
I have seen OEMs, I've seen an OEM paying several two-digit million amount of euro due to a wrong Excel program.
Yeah.
Just a recall action, diagnostic didn't work anymore, some plausibility checks in the diagnostic. Just a guy has combined two cells in Excel, and then everything didn't work anymore. Of course, wasn't qualified because diagnostic is an uncritical activity, has no ASIL. Then you do not need to classify and qualify the tools. Yeah, well. Meanwhile, this OEM has an ASIL for diagnostic.
Yeah, exactly. Okay, so many thanks, Oscar.
You're welcome.
Okay, we can now have a coffee break in I think half an hour, and then we're back. Correct? Yeah. Okay. Okay, take your seat. Oh, it's really. I call back into room. Everyone is coming very quick, so it's really perfect audience. Who knows online? Okay. Yeah, very nice talks this morning again, and now we go to also very interesting discussions. So we have Roberto Peccapelli, Functional Safety Manager at Red Hat. And this talk is about towards ISO PIS 8926, we touched already before, 2024, and future software challenges for functional safety.
Thanks, Ricardo. I hope that you have chosen a very strong coffee because now we are going to speak about standards then. Okay, before starting, let me introduce a bit. So I'm Roberto Baccapelli, Functional Safety Manager Community Leader for Red Hat. And actually, I'm covering the role as a project leader for the ISO standard regarding to the Part 8. And in the past, I covered the role as a project leader for the ISO PAS 926. And I have driven basically an initiative regarding to, the naming is Topic Group 6, then a topic group specialized on software in order to collect basically some ideas for the future third edition of the ISO 26262 standard. So here the intention, what I would like to touch basically is an overview about the ISO PAS 926, basically the main content. And later at the end, I would like to introduce some initiative regarding to the third edition. Unfortunately, I cannot speak more because it's forbidden by the ISO standard until we arrive with a unit decision, as Ricardo knows perfectly. But I would like anyway to share at least an overview about what we are doing. And obviously, this is my intent, to invite you to join us if you have time in order to make some proposal, comments about the third edition. So, before starting to go into details about the ISO PAS 926, a very short background. I'm sure that 99% of you will know about the ISO 262 standard. But basically, let me mention that basically the mother of the functional safety standard is represented by the IC 61508 for electronic device for in general for industrial domains for functional safety application. And in fact, we call it usually this type of standard as a meta standard. And from the IC 61508, basically we derived different standards specialized, for example, in our case, in automotive sector. And in that context, we have created basically this ISO PAS regarding the use of a pre-existing software architecture element for functional safety. Basically, one of the very first question that I already received in the past is, okay, but let's suppose that, for example, I would like to make a stamp, then a sort of certificate about my product versus the ISO standard. Now, how I should consider basically the ISO PAS 926 in that context? Is part of the ISO 26262 series of standard, or is a different standard? So how we can manage basically such information? Basically, you need to consider that this is a golden rule that you can apply for all standards. Basically, you need to consider a standard as a sort of book from which you can derive a major version, minor version. Then it's up to you, basically, when you create a major version, you establish the cadence for publishing basically this book. But for the minor version, basically what you can do is to create, not to republish again the same book, but you can publish papers or errata corrige notes that can support basically the content that you have previously published. Then the answer in that case will be, obviously, when you want to perform an assessment, the book is represented by the ISO 26262 standard, obviously. In that standard, you have the collection of the normative requirements that you need to apply.
The ISO pass 926 provide a guidance, like the other ISO pass that you can see connected with this document. The purpose of the ISO pass 926. Basically, our intention is to propose a framework for the reader in order to justify, basically to evaluate the suitability of an existing software not originally developed according to a functional safety standard, then in case the ISO 26262, but intention is to evaluate its suitability to be integrated in an overall embedded software developed in compliance with such standard. This document has been published this year, in the 1st January, and basically, as you can see, we have defined 3 main phases. The first one is represented by the impact analysis, and then we have basically other 2 main chapters, the suitability evaluation for class 2 PSA and the verification of the same class 2 PSA, and then the type of test that you can perform. Now, if you are familiar with the ISO standard, and maybe in that way I can cover another question, that I receive, basically, okay, but this ISO pass is going to propose something different with respect to the 2nd edition? The answer is basically no. In fact, our starting point is in common. We have the impact analysis. The impact analysis described in part 2. More precisely, the reuse of an existing element is described in clause 6.4.6. Very generic, we have the reuse of an existing element, then this clause is applicable for any kind of element, it could be software, hardware, and basically we have typically 3 steps for performing such evaluation, such impact analysis. The first step is to analyze basically the target environment, and then to compare the previous one that we use for conceiving the existing element with the new one, okay, then the new context. This is the first step. The second step is to identify basically the functionalities and properties offered by the existing element in order to derive basically specs, requirements, and to make a connection between the available identified features, properties offered by the existing element with your context. The third step is represented by the analysis of the existing documentation, then what is available, in order to understand if there are already suitable arguments that you can use for populating your safety case. At the end of these 3 steps, basically you can select according to the ISO standard, for example, part 8.12, if you are speaking about an existing software element, part 8.13 regarding to an existing hardware element, or if you are going to apply proving use argument, there's part 8 clause 14 that can use for such purpose. Okay, say that our starting point was in common. Later we speak more in detail about class 2. But what we included in the ISO pass, and there's in Annex A, a list of examples, list of possible existing software element for which basically the ISO pass can be applied. And as you can see, we have legacy code, open source operating system, software libraries, and so on. Now, the problem is, okay, but if I'm checking such list of possible software solution, I have different type of beast to evaluate. In that case, which is the proposal coming from the ISO pass 926? To perform, during the impact analysis, a sort of risk assessment, in which basically you can combine 2 different ingredients. One is represented by the evaluation of provenance-related uncertainties. In few words, you need to evaluate basically the software development process previously applied for conceiving such existing software element, and then you can compare such process against one reference, an international standard, like could be, for example, ISO 12207, specialized for the development of a software, or you can consider, for example, a functional safety standard, obviously, like IC 61508 or RTCA DO 178C for avionics. And then it's up to you to select basically one standard as a reference and then to compare the previous process adopted for conceiving such existing element against basically this standard. And then in that way, according to the results, you can identify, okay, perfect, the process is fully in compliance with such standard, then P1. P2 could mean that I identify some gaps, but I have some remedial action that I could apply in order to fix some gaps. Or P3 could be the case in which I don't want to select any kind of standard because for me it doesn't make sense. Or, for example, the list of gaps that I identified are so huge that I have no idea how I can touch, basically, how I can force, by using a process perspective, how I can force basically I can list basically the list of activities for supporting and then mitigate these gaps. Second ingredient is represented by the complexity-related uncertainties. Now, unfortunately, here there's a typo, but okay, sorry. Here we have a set of complexity measures established in order to determine the likelihood of PSAE systematic faults due to its complexity. This sentence is magic. Now, the first point from a software expert should be, okay, fantastic. Then you said me that I need to derive a set of complexity measure. But the first problem should be, okay, but which is your definition of software complexity? Because if you type on Google, you can identify thousand papers trying to defining, providing their own definition of software complexity. And you could imagine in the community of the functional safety how many weeks we spent on analyzing such definition. At the end of the story, we said, but in reality, we have already such definition in the ISO standard. In fact, if you check in part 6, 7.4.3, there's a fantastic table in which the description about what you need in terms of principle for defining a good software architectural design. In fact, there's a request to have a hierarchical structure, high cohesion, low coupling, the management of shared resources, and so on. You need to check, need to have an appropriate scheduling, and then a management of timing, and so on. Then there's a list of principles, and what we said is, okay, perfect, we don't need to reinvent the wheel. We can consider this clause as our definition of software complexity, and not only in part 6 and the same clause, we have an additional note that includes a list of examples about indicators of high complexity, excessive number of requirements, excessive number of parameters and variables, and so on. A difficulty on understanding the software code. Then, by using basically such list of indicators, we have derived in the Annex B, basically, some example of instrument that you can use in order to have such indication. And then you can find an Annex B, a table one by one with the list of indicators proposed in part 6 and some example about good indication, bad indication. And not only, we have included other complexity measures used, published in industry. Then, once identified basically these ingredients, obviously, according to the selection of the complexity measure, you could have the complexity C1 means the complexity is low. C2 means that you have identified some bad, so basically you have obtained some bad indication from such complexity measure. C3, basically, you have identified a very negative situation in which you cannot touch, basically you cannot reduce the complexity. According to these results, basically you can combine the results from the provenance, the results from the complexity, And there's one table in the ISO pass 926 in which basically you can merge both results and you can obtain the class of your existing element. Then, unfortunately here, for copyright reason, I cannot publish directly the content of this table, but it's very simple, it's trivial to say that the corner cases are represented by P1, C1 that produce a class 1, and P3, C3 produce an R. Meaning, class 1 means basically that you can apply, in terms of planning, a tailoring represented by part 8, clause 12. Class 2 means basically to apply the list of normative requirements listed in the ISO pass 926 and derived from part 6. And NR basically means not recommended for functional safety. Okay. Now, another point here, basically, implicitly, here that's the main reason of why we have proposed the ISO pass in 926. Because after the second edition, a wrong interpretation of the standard could be, unfortunately, there's a unique clause, part 8.12, fully dedicated for the evaluation, or if you want, the qualification of a used software component. But if you check the part 8, clause 12, in reality, there's a huge amount of quality requirements. Please show me if you have documentation about the accuracy. Show me if you have the requirements. Show me if you have the diagram about the states of your software and so on. But in reality, for functional safety, the requirements specialized for functional safety are the only one. Show me if the software is capable to satisfy the allocated safety requirements. Stop. The second request is, please apply a structural coverage for an ASIL-D. Then in reality, in part 8.12, we have only 2 requirements really for functional safety. And then what I'm describing represents a sort of black box approach. Because obviously that if you need only to perform a requirement-based test for justifying the use of a software element, the outcome means that I don't need to go deeply inside the existing software element. And this is a problem. Why? Because if the interpretation is, okay, but the ISO standards suggest me only this method for qualifying any kind of existing element, really is a problem. I can justify, for example, Linux by using part 8.12. It's impossible. This is basically the reason why we introduce class 2. And we introduced not only class 2, we have introduced the not recommended situation in which the provenance is very bad, the complexity is too bad, and then, frankly speaking, dear friend, this existing element cannot be used for functional safety. Please develop a new one. Then, according to this classification, as I described before, the classification represents a sort of method for planning your activities. Then, here we have obviously is a schematic representation in which basically we started from a big pre-existing software architectural element and I classify it as a class 2. Then inside I have identified one block as not safety recommended and the other 2 blocks. I started to check if it's possible to satisfy the list of requirements listed in the ISO pass 926. No, it's not possible. Then I could rerun basically the classification in order to refine my safety plan fully dedicated for each sub-element. In that case, we have 2 sub-elements classified as class 1 and 1 in the middle classified as class 2. In that case, in this example, we said, okay, now I'm able to satisfy all normative requirements listed in the ISO pass in 926. Now let me jump to the initiative regarding to the 3rd edition. So where we are today, exactly last week we had basically the working group 8 plenary, and then we started to collect all comments connected to all parts of the ISO standard. Then our expectation is to have basically 2 working draft phases. If you're not familiar with this term, a working draft means basically that we can have an internal we have the creation of the new parts of the ISO standard as a working draft, and the conclusion of this phase is represented by a commenting phase limited to the members of the groups. But basically, we could have a CD phase, committee draft phase. In fact, this is a question that you posed to the SC32. If it's possible, basically, to skip the CD phase. Why? Because basically, during the CD phase, is requested to provide a preference, there's a ballot phase, and then in which there's a request for each national delegation to provide if each part satisfy really the expectation of the national delegation or not. At the moment, it is written in red because we have no an official position. We have not received yet an official position from CT32. Then, before this plenary, we have created different topic groups. Why? In order to, basically, we have asked to the different national delegation, okay, which is your wish list? What you want to see for the future in the third edition? And basically, we have other technologies, topic group 1. Basically, I see, especially yesterday, discussion about how functional safety, security, other technology can be combined in a unique approach. TG2 is related to predictive maintenance. TG3 is related to automotive driving. TG4, end-to-end safety. And TG5 is related to the SOTIF. TG6 was related basically to the software that I led, basically. TG7 is regarding to the process safety, basically what we discussed yesterday. I don't remember the name. The colleague from French, Delphine, okay, Delphine, that explained, basically described basically the functional safety management system. And TG8 regarding safety concept, and TG9 it was related to the AI technology. Then, in conclusion, regarding to software, there are, and this is what I can share with you, some interesting information about, obviously, our intent will be to integrate the ISO Pass 926 in the third edition. Then we have proposed basically to include a technical evaluation as a prerequisite during the selection of a software candidate. There's an ongoing discussion about how we can adopt a DevOps process inside the ISO standard, because today, as you know, that's the terrible V model, and in some cases it seems not applicable CI/CD. Then our intent is to solve such issue. And there's another point regarding to the functional safety data. We have discussed exactly a few minutes before about the criticality regarding to have data able to support functional safety arguments. And last but not least, there's in parallel the discussion and updates coming from the IC 61508 community for the third edition. And our intention is to try to identify some points of improvement for us. And obviously, if you want, join us.
Many thanks. Okay, we already have there's 2 questions here.
It's me. Okay. Okay. Well, first one remark on part 812 from ISO 262. So TÜV Süd, who is the strongest one in Germany, refused to qualify libraries according to part 812 because they, compared with IEC 61508, think this is a whole. So you don't need to have code coverage except for ASLD. You don't need to have programming guidelines. You don't need to. So there's a lot of simplification that automotive industry introduced this, and there's always a debate with them. So well, tell it in the back.
But agree.
And the other thing is, it refers to part 6.9 and to part 8.9. So it's not only the 2 requirements you mentioned, it's also part 6.9, which is software unit verification. So you have to do a proper software unit verification, and then you can, in order to be compliant with 812, so you have to consider the references and not only what is written in it.
Okay, basically what we said is we try to identify a class one as a design that you can imagine similar like in terms of complexity, like a sort of software unit or basically something very limited. And then in that case, in fact, how we did it by introducing the concept of complexity related uncertainties and the provenance related uncertainties. If it's very simple, then in that case it makes sense to apply a requirement-based test to justify the usability. In other case, no, obviously. Yeah, no, it's a good point, yeah.
Yeah, I'd like to second that actually, also from the software creator side, part 8, clause 12 doesn't help at all. So it's really not helpful. When you do something, go to IEC 6.508, this is much more helpful, but also much more complex to understand. But I would like to go back to a slide that you had about the integration here. So you basically said you, closer? Okay. You, one slide before, we have to basically this decomposition of the subsystems and how now we have a set of various different subsystems that interact with each other in a software architecture. How do you address the integration aspects of these now many subsystems that you have that you are now classified on level 1, but they are still put together and form an entire system? How is this addressed?
Basically, you have, according to the granularity and then the level of detail that you are going to analyze, basically, if you're lucky to satisfy directly the first iteration, it means that you have derived the requirements from your environment.
Yes.
Then you have automatically the connection with the property offered by the PSAE. And then you are able to justify, okay, there are some elements that produce at the end some identified function. The bad case could be, no, unfortunately, I have no sufficient information. In that case, I need to jump in the detail to the different sub-elements involved.
Yes.
And then again, to repeat this game. At the end, according to this type of classification, what you need is to perform a verification at integration level for the sub-elements. And then later, to have the final integration, the overall PSA against your environment. There are 2 steps for the verification.
Okay. So if I get it right, you're basically including the integration parts of part 6 and the ISO 26.26.2, which you then have to do on this.
Yes, exactly.
Okay.
Part
part
6,
part
close.
6. I don't know. Would have to look.
10, I remember. Yeah,
the integration requirements.
Exactly.
Yeah.
Okay.
I want to Gabriele Paoloni from Red Hat. I want to expand a bit on this point. So basically, the sub-elements about your question. So the sub-elements in the class 2, basically these are needed to perform on the class 2 a safety analysis, but not with the goal of allocating sub-requirements to the single sub-elements, because these are not single software unit anymore, but more, let's say, with the goal to derive a more meaningful test campaign at the, for the class 2 elements, to also with respect to the failure modes that you would see. So this is the idea, to have a view, at least a view of the internal sub-elements, to make a call first on the complexity indicator, and also to support a safety analysis between these sub-elements, and accordingly to derive a meaningful test campaign for the class 12 and other verification measures eventually.
Yeah, also potentially something I would like to add, that usually the qualification for software and also the evaluation for the hardware in the ISO are done in a way that the user is doing this. So a kind of not black box, because at the end the software is not anymore a black box, but somehow that I don't have much know-how. Okay, now I have to qualify or evaluate. I don't know why we are using different terms, but okay. But of course, if you are at the originator of the software, yeah, I think you can have a better chance.
Yeah, but let me add one point about it. The big difference in terms of classification from part 8 clause 13 is while for the hardware side, they decide basically to associate as intrinsic properties of the product the concept of class. Then class 1 means basically that you have a few list of failure modes, few final states of the hardware elements. And then according to this definition, association of existing hardware element, you have automatically, by definition, a class, could be class 1, class 2, or class 3. And then according to such classification, you have automatically a list of activities. For the software side, we use a different point of view, more similar to the tool classification. Our intention is we have in front of us, that's important the type of beast. But what you need is to know provenance and complexity. And according to the combination of provenance and complexity, you can associate if it's class 1, if it's class 2, or is not recommended. If it's not sufficient, you can go deeply, more in detail to the sub-element level. And this is the different approach that we use for the classification in part 8, basically in the future part 8.12.
Yeah, and okay, we don't have any more time, but one question also could be, once you have done everything, you find that actually your software cannot be used like that. You have to do modifications. Which clause of the ISO needs to be followed for modifications?
Because at the moment, there's the terrible sentence coming from part 6, 7.4.7, that basically an existing software element can be qualified without modification. And this is what we are trying to modify. And it's in contrast with what is described in part 2, clause 6.4.6, because in general, it's described in this clause that for any kind of existing element, it's possible to evaluate and qualify this element with or without modification. But unfortunately, in part 6, probably because the intention of the authors was, since part 8.12 is really a black box approach, I can apply it only if I cannot approve any kind of modification of the element. It should be as it is. It should be simple.
Exactly. Okay, I mean, very short. We are out of time.
Very short. So modification is forbidden because you have also other requirements. When you look to IEC 61508, there's I think a dozen of requirements how to modify pre-existing software. So and that's, if you say don't modify, then you don't have the requirements. If you say we are allowed to modify, then you should have those requirements.
Later we have the panel for continuing the discussion.
Let's discuss more in the panel, yes. So very interesting. Okay, many thanks.
Thanks a lot.
Okay, so we go to the next presentation. This time is Professor Mohammed Al-Sayed, functional safety engineer. No professor, okay, sorry. Okay, now you're professor. Functional safety engineer, CEO for the TwoGo Solutions, yes. And the topic is building a safety case for automotive vehicles.
Thank you. Thank you, everyone. Just a bit of warning. There would be a little bit of telling about myself a little bit in this presentation. What's very interesting is that yesterday we had a similar presentation from Dr. Phil, and he really went into detail into explaining everything about the safety case and what we like to see from the UL 4600. What I'd like to do today is talk a little bit of a different approach with regards to safety case and how do we do it, not exactly the same as the one we have from UL 4600. This is the agenda that we have for today. It's pretty short, but I hope will intrigue you nonetheless. Just a little bit of an introduction. I said pre-warning, I have some introduction and marketing information. I actually started with functional safety back in Scotland, following a master's in safety engineering. And then I moved to, started my own consultancy back in Canada, which was focused on the oil and gas business, and moved that over to Denmark. And then in Denmark in 2008, I was supporting the offshore business doing oil and gas, and there we have quite an intense safety case. And then I moved to Berlin 2012, where I started looking at the automotive industry and really did a bit of research around autonomous technology. And there where I wrote a paper summarizing a lot of that research and called the safety case for autonomous vehicles. And then I set up the to-go solutions with the purpose of design and deliver safe, secure mobility for the automotive industry. The to-go solutions, again, just that was a bit about me, about to-go solutions. Basically, the goal is to, for an OEM who wants solutions for their level 5 autonomous vehicle challenges, our monitoring and control system provides a triple S answer: safe, secure, and simple. It increases safety via redundancy. It reduces technological challenges via simplicity, and it provides reduces cybersecurity risk via almost elimination of V2X. So we basically we patent the technology system that provides this level 5 technology. It's a high-level system. It's not going into so much detail with AI and so on, but it nonetheless able to provide the answer to a lot of the questions we have and a lot of the challenges we have. What I want to say here is we've come a long way, but we cannot continue this way without a partnership. So this is something I say all the time when I present this presentation. One hand cannot clap, so we need to cooperate. And that's all I'm going to say about myself and the company. But now going forward into the safety case. So what is a safety case? Well, it's not this. It's a document in which the OEM communicates to the representative of the public or the regulator that their vehicles are safe enough for public use. This automatically implies public roads at all times. Any risks identified have been reduced to levels that are as low as reasonably practicable. If it's not the case, this can be limited. It could be safe enough for public use on private roads, or not only during daytime, or in clear weather conditions. So let's see how to build one of those. Think about the argument safe enough for public use. For autonomous vehicles, the main argument for a safety case is that this autonomous vehicle will be safe enough to not cause additional harm to the public. This needs to be supported by claims. An example of a claim could be the claim that technical risks are reduced to alarm levels. Evidence needs to be provided to show that. So the safety case is a collection of justified reasons or proven claims supported by evidence to convince the reader that the validity of the argument that the vehicle is safe enough. This needs to be progressive in nature, following the question and answer protocol. The claim is trying to answer the question, why is this safe enough? Sorry, I shouted on the screen. Because the risks are identified and managed to alarm levels. Now, how can we prove that all the risks are identified? Say, for example, we did a hazard, we identified the risks, and we used the industry standard to manage them. But that's not the end of that. There are multiple layers to the claims, but let's see how that will be built with using arguments. How to develop the arguments that the claim, for example, are all the risks are identified using hazard, for example, will widen the scope of the safety case. There will not only be technical risks that we have always discussed here. We talked about technical safety, we talked about cybersecurity. There will be business risks, organizational risks, procedural risk. There will be operational risks that we talked about yesterday, human resource risks, supplier risks, production, environment risk, service risk, and decommissioning risks. So we need to define the scope. What is it that we're looking at? And then afterwards, we need to delegate which department in the company is looking at what level of risk and what risk. We cannot, in functional safety or technical level people, manage business risks. For example, here, tight timelines to achieve certain release dates will jeopardize the entire development process, and thus by the safety. How is this managed? This is not going to be managed on a technical level from people. So that's the first step, identify what scope we are going to cover. In the next step, we look at, okay, how do we build the content? Let's say we're going to talk about technical risks. What are the technical risks? So we need a brainstorming exercise to identify what technical risk and hazards could lead to the vehicle to become unsafe for use or not safe enough. For example, functional safety, like brake failure, SOTIF failure, like brake activation, AI failure, like the vehicle behave not in a normal, predictable manner. Failure to follow traffic rules and regulations in absence of signs. If we don't have the 30 kilometer per hour, the vehicle is supposed to know that this is a 30 kilometer per hour road based on the type of road. Failure to avoid accidents like humans do. We have an instinct to be able to avoid accidents, and by nature, how is AI going to do that? Failure to provide cybersecurity, to prevent cybersecurity attacks, electric faults, high voltage, fire risks, mechanical risks. We have cooling systems, we have hydraulics. We need to ensure absence of any risk. So claims are needed to support this scope that we discussed now. So that was the arguments. Let's talk about claims. How to develop the claims? We need to break down the argument. So we need to ask questions. For example, building the safety case, the question, why is autonomous vehicles safe enough for public use? That's a very loaded statement. To answer this question, we need multiple layers of questions, of claims that will be supported by evidence at various levels. To start with the question, because we say, because all risks are identified and managed to acceptable levels. This is a claim. In order to prove this claim, we need to still ask some questions. How do you know that all the risks have been identified? This has resulted in defining the scope previous. What risks have you identified? Well, we did a hazard and we identified the content. So we looked at technical risk, we looked at cybersecurity risk, we looked at SOTIF risks. Okay, how are they managed? And what is the level of risk reduction achieved? Dr. Phil started with this statement yesterday. I'm not going so much into this statement at the moment. How can this hazard process, let's say we noticed that the hazard process was done, and this hazard process identified scope, and the next level hazard, we identified the content. So how can we validate this hazard process? That we say a claim, the hazard process has been validated as per standard. Okay, prove that. Prove that you have followed the standard. How can the results be assured? Well, the list has been reviewed by competent third-party people. That's another claim. We provide evidence to that. Is the list, another question, is the list with industry best practices? Yes, it is within industry best practices. Is the list in line with some of the standards we have? Yes, the list is in line. Every time you make a claim, we need to provide that with an evidence. So we broke down one sentence, vehicle available or safe enough for public use, to starting with one level and breaking it down all the way. So the statement that validate the presented argument need to be broken down, like we said, and we need to ask questions. So just so that you don't fall asleep, ISO 262 has been used to address and manage functional safety risks. This is a claim. To which question would this claim be provided? No? It would be provided to how are technical risks, example, functional safety risks, managed? The answer would be using technical standards, using risk management systems we have in the company, and using industry best practices. So the claim ISO 26262 has been used to address and manage functional safety risks is the answer to a question, how are technical risks being managed? So we are following from the main argument, question by question, going down to an answer. Okay. Now, every claim needs to be supported by evidence. We've seen how arguments are built, how we've broken down the argument with questions, and how we build claims. The evidence is where the work really is. In collecting the evidence, we also identify assumptions that we've made. So we might have made some statements that are not, don't have any backup, don't have any evidence. We might have identified some areas where we are not able or violate our claim or our argument without being able to provide any evidence and without able to have support. So those are defeaters yesterday Dr. Phil talked about. So just an example for evidence, let's talk about safe enough. What is the level of risk reduction that's needed? The claim needs to be provided for the different levels, for the different scopes and content. For example, we have functional safety, we have business, we have HR. We talked about these different types of business risks. The safety management system, which was discussed yesterday, talks about how to address the different levels of risks. For example, the claim that this is safe enough for public use. The acceptance level for functional safety is prescribed. For technical risks, ISO 26262, when you do Tahara, you have certain levels that are allocated based on your probability, your exposure, and your controllability. You are supposed to reduce the risk by a certain amount, as LB, as LC, as LD. However, for autonomous vehicle, we have to take controllability out of the equation because there's no driver. So when we look at our legacy items that we have produced before and used before for cars that with people inside, we need to do a reassessment without controllability. And if we do that, we'll find that most of the functions we have are one level of risk, one level of safety higher. This is one aspect. The other aspect is for autonomous vehicle technologies, we need availability. Availability so that the system needs to work. Normally, when we look at safety, we say that it should not fail. Now we're saying the system needs to work, needs to be available all the time because we don't have anyone to react. And in that sense, you need redundancy. Okay, what type of redundancy? I need redundancy that is independent and at the same level of integrity because it needs to be available when the system doesn't work. So now we're still talking about technical risk. We have looked at legacy items need to be improved. We have looked at redundancy. Now we have a redundant system. But then one might say, well, how about current levels of risk? We have accidents, people are driving. Is that something that we can use? And we've heard this arguments before. And I mentioned this yesterday, there's a risk of outrage. What is the risk of outrage? In the autonomous vehicle technologies, we don't have a driver. So we cannot have accountability for an accident if an accident could happen. The people will react. Outrage will increase, risk will increase. So, okay, what about, how do we know if the public is okay? And this is a very key point. How do we know if the public is okay with the risk level that we have achieved? Well, it's not that easy. But we could get an indication using surveys or on what is called the VOL. I don't know if anyone of you is familiar with this concept, value of life, in which which will be different, the VOL, for different locations, different geographical locations, and sometimes within the same country, you may have different locations. As an OEM, you have to go with market-specific products. So something like the willingness to pay concept, in fact, studies have been done, and the data is available to show what kind of value of life is available in the different geographical locations. So we can orient ourselves with there. One might ask a question, what about SOTIF risks? Because we have been looking at technical safety, functional safety. What about SOTIF? What about cybersecurity? What about a combination of SOTIF and cybersecurity risks? Such scenarios are foreseeable, not unlikely given the current state of affairs. The owner needs to design these risks out. And we should look at managing societal risks via the FN curve. And I don't know if anyone is familiar with the FN curve, because when you have societal risk, you're looking at one accident causing multiple fatalities. We don't have in the ISO 26262, and the question to the committee, any level risk that addresses multiple fatality risks. We have individual risks. We look at S3. In IEC 61508, we have S4, which could look at multiple fatalities. When we start looking at S4, you require a SIL4 level, and that cannot be in the vehicle at all. So when we start looking at evaluating what is the acceptable level of risk, we're looking at various issues, and we're looking at various levels of risks that need to be addressed. So it is a very, very difficult question, and we need to provide evidence, surveys, arguments in technical safety standards, arguments from the industry. This is why it's paramount for autonomous vehicle technologies to, especially when we start talking about SIL4, to utilize every possibility they have to optimize the system design such that risks are eliminated. And this can obviously include infrastructure. I know that somebody put on the picture yesterday with Elon Musk saying this shall work at all times without any use of networks. This is not taking into consideration anything of what I said here today. For example, geopolitical risks in cyber attacks on private companies could impact governments, not just companies. Autonomous vehicles come with risk and opportunity, and the community itself needs to decide if this is something they want to have, and what do they want to work with, and work with the owner to define the level that needs to be achieved. Oh, time's up. So, as a summary, we have discussed the safety case, the scope, the content, and the main elements. We've also provided some examples from the safety case for autonomous vehicles, and I hope this makes a path for setting up a safety case for autonomous vehicles. I'm not talking about safety case for autonomous vehicles, I'm talking about how to set the path for a safety case for autonomous vehicles. And now, floor is open for questions.
Okay. Okay, question time, online or in the room?
Yes.
Mateusz Czerwienko, RSB. So you addressed the very interesting topic of availability.
Yeah.
Which is also appearing, and I may or may not encountered this top-level safety requirement with ASIL-B or other to one of the subsystems of this, let's say, autonomous driving, and which per se is contradictory to like more conventional safety goals, right? Where you have to enter the safe state. So the safe state is violation of the availability top level safety requirement. And then what should be the scope of such, like in terms of what we are claiming in the safety, how would you phrase the safety case or let's say top level safety goal, like with having in mind that there is this availability problem, right? So yeah, so that's the, or should it be kind of addressed on the vehicle level, or should it be also addressed at the subsystem level?
We've heard today several times, to address big problems, you have to break them down. So we have a system, we have subsystems, and those subsystems need to be available. Availability is a requirement on your subsystem or on the vehicle. So take the brake, take the critical safety systems, take brake, steering, and brake and steering, for example, braking and steering and propulsion. You cannot have failure of the brake system. The brake system needs to work. So what is the common approach now for OEMs is redundant systems for the safety critical elements. And the requirement formulation is the system shall work as a next to it. And normally we don't have that. Normally we have the system shall not fail as a. But good question.
Yeah, I mean, in general, availability is also an attribute of the safety goal, so it's not a new safety goal. There is, I think in the part 10, this is also described how to handle this availability. But I agree with you, is tough and is mainly a system, the redundancy at system level at 10.
Just the point is that it may be a problem coming from this, like the system requirement that is kind of decomposed to the subsystem level. Maybe there shouldn't be a subsystem level requirement then. Yeah, so I'm just wondering whether there should be some, right? If it's contradicting to the, like, transitioning to or moving to the safe state.
At the system, take the vehicle. Starting from a vehicle must be available. The drive system must be available. You have another branch of requirements that goes all the way down to the subsystems. So you have the requirement not to fail, and then your requirement to be available. And then from that requirement to be available, typically your branch of redundancy comes out.
Yeah, I mean, attend, if you're talking also about ISO 26262, availability means the fail operation. And then you need to identify which failures you want to be operational. That is the first target. You cannot be fail operational for any kind of failures. You need to start somehow with some definitions. Which failures can be accepted because the risk is sufficiently low, which one maybe could be critical and could happen, and then you want to have some redundancy, so yeah.
Exactly. The HARA will tell you which systems are critical. You have a question there. Some OEMs are going with very critical, drive critical systems, propulsion, braking, as a minimum, propulsion, braking, and steering.
I mean, it's a nice presentation. I mean,
thank you. Like yourself yesterday.
Again, see you again. I mean, at least your fundamental is proper from oil and natural gas background, so you understand. Just to add the comment from Ricardo, when you say that fail operational, you put it right down to like thinking the cost factors. But it is good that all failure operational systems should work like as in avionics sector. So they have a complete redundancies, they have cost involved, very simple software, no complex silicons they use like ASICs most of the times. No tool complexities. Yeah, I mean, so you can develop. These systems are existing in the Airbus and Boeing, the commercial DOs 178 sectors. It is there. Only in sector like automotive, it is too complex to make the fail operational systems. So then the definition of fail over mission systems has come discussion, like where it is a healable, where it's not healable. Then you go to limp home or limp aside strategy for that matter. Yeah.
The question is, where do you stop? And Do you stop also to have one battery, or you need to want two batteries? From your
Oh,
end,
that's a big discussion. You know that.
I know. Yes.
It is holding for a long time for this drive-by-wire and steer-by-wire
Yes,
systems,
I
so
know.
where to
I
store
know.
the energy, and
So, I mean,
it is
finally,
never passing through the regulations for really long time, R79 or R13 regulations. So that's right.
finally moving to level 4, you need also redundancy in power. But
It will.
if you're looking today to human driving, we are fail silent or fail crashing. So we have one driver today.
Yeah, I mean, that's what.
But that's the point. We cannot go with the same that we have today going forward, because we cannot blame this on a driver.
Exactly.
And this will cause out, I mean, we're seeing it right now. The outrage is increasing, the number of requirements, the regulations is increasing. So I don't think we can continue, because we will regulate ourselves out of ever getting there.
No, correct. Okay, I think we need to move to the next. So many thanks.
You're welcome.
Okay, we have now the next presentation. It is again virtual, and we have Massimo Carignano and Claudio De Ramo. Are you online? Massimo, Claudio? Okay. Are they connected? Anyway, Massimo Carignano and Claudio De Ramo are from, I mean, Massimo is Functional Safety Governance Manager from Iveco, and Claudio is Functional Safety Engineer. And the talk will be optimized efficient model for ISO 26262 and a risk model for monitoring FUSA faults and failures, so really about field monitoring. Are you online? They are here. Yeah, I think they tried to call me.
Just a small technical remark. They need to accept the offer to present.
Mary? They said they don't have the connection, the link for the panelists, only the one for the conference.
We are sending them the request. They need to accept it. Put accept.
Okay. Sorry, guys, for this technical connection, technical issues. Maybe you can still talk a bit briefly about his presentation, Mohammed, and we have to sort this out. Okay.
And just hello, hello. Yes, yeah, we are sending you the request to present, and we need to we're going to the lunch break.
Lunch break now? Okay. Okay, so we change the plan, so we will have it till lunch break now. I see already your face, yeah. And yeah, we move the presentation to later, hopefully. Oh, they're here. Oh, sorry, guys.
Can you hear me? Okay. Sorry.
Oh. Can you try again, Massimo? Massimo? working?
Hello?
Yeah, yeah, there's some
Okay,
bit of echo.
so I think you can hear me, right?
Yeah, now it's better. Yes, okay, now it's better. Okay, so can you try to share also your presentation?
Hello?
Yeah, can you hear me?
Yes, okay. Then
Perfect.
I should be able to start presenting.
Yes, can you try?
Yes. Do you see my screen?
No, I only see my face. Not a nice image.
Now?
Yes, I can see. Can you put in presentation mode and we should be
Yes.
okay to go.
Okay.
Okay,
Sorry.
excellent. Please start. Thank you.
Sorry for the delay. So my name is Claudio Dermo, and today I'm jointly presenting with Massimo Carignano an optimized efficient model to detect functional safety related faults and failures. So I will give the word to Massimo so he can give a little introduction of this topic.
Okay, thank you, Claudio. Thank you, Chairman. I would like to underline in this presentation a sort of optimized and efficient models for ISO 26262. Optimized in the sense that we have to prevent all the action during the functioning and the working of the operation fleet of our vehicle. And from the operating fleet has to be monitored in order to timely handling the anomalies, thus minimizing the impact and the cost that arise from a product and/or process solution. The proposed method has also been developed to confirm the quality on product development and to support the proven in use argument related to specific elements. Such elements have been integrating with their item, but may have not been developed according to ISO 26262. If correctly applied and thanks to the huge data collection in case of our company, we have the possibility to use a control room able through the telematic tools control unit included in the new vehicle, in the new truck and bus since 2022, it is possible to collect a huge quantity of data and build up step by step during the years of operation of the vehicles on the real world, on the real roads, okay, build up step by step a proven in use in relation to all the components that had design in respect to the ISO 26262, but some components may be also in deviation. So we have the possibility collecting a huge number of data on the road vehicles, okay, collecting a sort of concepts related to the proven in use. From the monitoring process point of view, we have what I have already described. We have the fleet monitoring of all our, let me say, market, in case of having the possibility of the usage of telematic systems able to transmit to Earth in the server adopted by the company each hours or another frequency of acquisition based on the gravity of the parameter to be monitored. And after, we can have the possibility of a huge data collection followed by filtering data, clustering them, and eventually reconstruct the wrong failures, wrong functioning failures, faults, and others bad aspects related to the electronic and electric components of our interconnected architecture, networks included. The data analysis that follows our process is represented in relation to the functional safety, the construct, the build up, the design of the diagnostic trouble code or the logical combination among these diagnostic trouble codes that has been sent from all the control units of the vehicle, observed and transmitted thanks to the telematic control units. The diagnostic trouble code properly collect, properly monitor it, properly combine, you can set up a sort of situation of the functional safety working of your system. The functional safety working of your system has to be considered in terms, in our opinion, has to be considered in terms of functional safety faults occurring during operation, or bad behavior, or some, let me say, false positive sended, wrong functioning of diagnosis, wrong triggering of safety mechanism, and so on. So you have the possibility to check from a provenance news point of view the capability of your components in deviation respect to the ISO 26262, but you have also the possibility to check all your safety mechanisms designed in the development phase of your electric and electronic architecture of your vehicle. Okay. The failure rate estimation is the second, and the risk parameter, as Claudio will see you, will underline you after, okay, are the possibility to maintain, build up, and quantify the overall risk with the corrective action. So, just to have a look at some three assumptions. We have considered the constant failure rate for simplicity. The failure rate of the system is assumed to be constant, and this point is also made by ISO 26262 in part 8. The diagnostic coverage. In relation to the diagnostic coverage, we have the actual system diagnostic performance assumed to be equal once established during the development. And the availability of data, as I mentioned before, are the number of user-relevant failures diagnosed by the onboard diagnostic system assumed to be known at any time of the operation. I would like to give the floor to Claudio just to put in details our process.
Okay, thanks, Massimo. So the first building block of our method is to estimate the failure rate from the field. And in order to do so, we basically suppose with assumption number 3 that we have the number of functional safety related faults which can be detected. So ideally, these would be multi-point detectable faults. And based on this number, it is possible to estimate the number of undetectable functional safety faults. So this ideally would be the number of residual faults, single point fault, and to perform this estimate, it would require another session. So at this point, we can estimate the failure rate from the field using the chi-square distribution as suggested by the standard. Of course, we can take into account the efficiency of the monitoring process. For example, if just 50% of the vehicle are being monitored, then this efficiency would be 0.5. And of course, we need also to take into account the hours that our vehicle have been operating. So this T, this capital T, is the cumulative fleet operational hours. So at this point, what we do have? We have two failure rates, the one from project and the one from the field. So suppose that everything goes smoothly and enough time is passed, few faults have been raised from the field, then we can see that actually our system is behaving correctly, possibly even better. So we choose, we pick as failure rate the one from the field. Otherwise, there are two options. Not enough time has passed, right? Or maybe I'm having, yes, too many faults. So if not time has passed and I do not have faults, I stick with the project failure rate, at least for the moment. Otherwise, I need to ask myself, okay, after all, the failure rate is randomic, right? Sorry, it is constant, but the failures related are random, okay? Then the question is, if I detect early failures, is this true or I'm just unlucky? So if I'm just unlucky, I go into this branch and I stay with my project failure rate. Otherwise, what I'm seeing from the field is the actual system behavior, and hence I go with the failure rate from the field. So at this point, we have chosen our failure rate for the system in operation. And now we need to assess 3 risk parameters. And why we do this? Because usually ASIL level are not understood by people who do not know about functional safety. So they want a risk metric in terms of high risk, medium risk, low risk. So what this overall risk metric should take into account? Of course, it should take into account the severity of the potential hazard. So here we introduce this variable called residual severity. It is measured according the same scale using the hazard analysis and risk assessment. Can be the same level of the severity. There is an opportunity to consider a lower severity level because the system in operation has some safety mechanism. Maybe not all of them, but some, yes. Then another factor that we want to take into consideration is how my system is with respect to the state of the art. So we introduce this ratio between the failure rate of my system and the target of the functional safety standard. So this is basically a metric which tells me if I'm doing all I can do or not, right? Finally, the third metric gives an extensive measure for the number of hazardous events that can occur for the entire fleet. So with the failure rate, the volume intended for production, and the lifetime for each sample, I can calculate the number of expected failures, right? But not all of them will result into an accident because maybe they verify in an operational situation which is not dangerous. So at this point, we give an overall risk metric based on 3 tables. Each table has a severity level. Of course, the higher is the severity, the higher the serious risk zone will be. So, for example, here for severity, for residual severity equal to S3, the red portion is greater than the rest of the other 2 tables. How do we set this color threshold? For the fleet operational risk relative, this is quite easy because if you remember, it is simply the ratio, right? So so everything below 1 is fine. If we are again near 1, okay, it is fine. But if the order of magnitude increase, then this tells us that we have that we have an actual risk. Instead, for the extensive risk parameter, the absolute fleet operational risk, it is more complicated because, of course, the higher my fleet, the higher volumes predicted for my fleet, the higher number of faults I will have. So this can be tuned according to company policy and liability to risk. In the end, to summarize, the method here presented embraces the spirit of ISO 26262 because we use the chi-square distribution, right? And it is based on 3 risk parameters, which can be used, let's say, for example, compliance to the state of the art in a court of law. The residual severity, of course, it is impacted, it has an impact with the public, right? And also this method can be used even if the vehicles are not already in production, because at the end I can always use the project failure rate to predict an overall risk. So we have launched this method and we compared the results with Monte Carlo simulation, and the results are in line, which means that the failure rate is in the same order of magnitude, right? Okay. Then there is the big limitation of this method is assumption number 2, which is the most stringent. Basically, this assumption tells us that if during the development process we consider failure rates with I don't know, two order of magnitudes higher than what they need to be, then these need to be, let's say, done for every components. Finally, further improvement is to adapt this method with SOTIF. The problem with SOTIF is that the unknown triggering condition, they are hard to be estimated by the non-triggering condition because they are unknown by definition. Instead, for the residual and single point faults, there is a way to do such estimate. So the idea would be to use a digital twin or an event accident data recorder. Are there any questions?
Okay, first, thank you for the...
Yeah.
Excellent. Can you switch on the camera, possible?
Yes.
So we can also see
yes,
you guys.
Give me a second because it's on the other computer.
Okay, if it's not too difficult, it'd be nice to...
Yeah. Just give me a second.
Questions from the... Yeah, okay, I already see some questions here. And also again, online, please.
Thank you, Gabriele Paoloni, Red Hat. I have a question because actually I have a couple of questions, unfortunately. So
we have time. Lunch, we can wait.
Oh, okay. Very sure. Anyway, so the first one is, I mean, this method seems, I mean, if my understanding is correct, so this method is based on the, you know, on the observation of the failure rate and monitoring of the failure rate from the field. Now, the first question is, how can you, I mean, I guess that before you deploy a safe fleet, you need to have data from the field and you need to somehow be confident that the field that you gathered data from is very much close to the context of deployment later. So first question is this correct? And how can you guarantee this? The second question is, would you use this method also to qualify for functional safety use a complex system with, you know, with the hardware and software stack that is
maybe initially not qualified for functional safety.
Okay, so sorry, just give me a second. Can you hear me? Yes.
Yes, it's okay.
Okay, so great question. So what we can do, of course, is to monitor some elements, either electronic control units or an item like AB from previous projects, and then use this data as an argument to reuse this system into next projects. Also, this method will support compliance for new regulation regarding autonomous driving standards, because they will because by this regulation, functional safety management system which monitors the system in execution is mandatory, right? Regarding your second question, I would say yes, as long as you have, sufficient data, because the problem is that the amount of data is to acquire is a lot in terms of hours, because we know that 262 works with a very low number.
So when you say sufficient data, I mean, do you envision a possibility where a complex hardware and software stack with no previous data is, qualified by, deploying it in a sort of controlled scenario, and that you say, okay, this is good enough to move ahead and also deploy it on the road, or?
Yeah, I mean, it can be done. It can be done. Maybe you do not need also to develop to deploy this system on the road, because if you take into example camera system, right? You can put in parallel, I don't know, 10 cameras and run many hours of clips, but at the same time you need to provide evidence that the clips you are running, they provide an extensive description of what the reality is really is, right? You can also do this, of course, before release of production using a success run approach. The problem is that with actual vehicle testing, it is hard to acquire the number of hours, right? Instead, if you have, let's say, a chance to do it with a qualification test, then I would say to do so. But you need a statement saying that. In example, I provided that the clips simulate well enough the reality.
Yes, just to better focusing the concept of a fleet, we can consider two types of fleet. The fleet related to the reliability growth during the development phase, at the end of the development phase in the validation one. And the fleet, the real fleet of operational trucks, when the trucks has been sold. So we are considered the trucks that has been sold. Also the reliability growth trucks to the validation phase during the development and design phase. But it's very important, this method, because it's become a procedure internal of our company, is due to the fact that the telematics tool that is an optional for the model year 22 and model year 24, okay, adopted by our track, is an optional and give you an enormous possibility to collect the data. So the scenario is the real data one.
Okay, thanks. So, next question.
Hello, I'm Andrea Matteucci, Protentex. Actually, it's a follow-up question. So first of all, thank you for the presentation, really great work. I'm a fan of field monitoring. You will see later in my presentation, spoiler alert. But I want just to ask if you have somehow estimated during your simulation the amount of data that you will need, in the sense how many vehicles must be your fleet in the field, how many, or let's say, if you, of estimating, for example, 10 years of life for each vehicle, if you need couple of years or something like that, if you have somehow give a number of this data to have enough confidence later for your risk assessment. Thank you.
Yes, normally the numbers of data are related as the ISO 26262, okay, advise us to support the failure in time thresholds. So cost and the budgets in a real company are the driver, mostly to decide the quantity of the fleet. This is the important aspects of our methodology. That if the real fleet is growing as we hope, obviously, because the vehicle quantity that is sent, okay, is higher and higher. Okay, you have normal the reach of the quantity in a brief time, the reach of the quantity properly to make some hours. The hours are given by the failure in time threshold. For example, 100 feet, maybe 10 millions of hours if I not wrong. So 1 million of hours with let me joke, 1 million of vehicle. Okay, after 1 hour, you have the summary of your situation and robustness inside. Okay, so you have to consider that 10 vehicles could be represented, 10, 20, 50 vehicles could be represented the reliability growth fleet, while 1,000, 2,000 and 3,000 vehicles may be the first quarter, for example, of your production and operational fleet. So in the first months after your vehicle launch, you are able to begin to consider a quantity of data, okay, able to be near to the fit representation. Okay, because it's not so easy to reach 10 millions of hours, okay, but you can reach 1,000, 100 and so on. 1 million of hours you can have after 7-8 months, because every vehicle more or less are 2,000 each hour, each year, okay, mostly 8 hours a day for a door-to-door or someone. So hours are 2,000 each vehicle. 2,000 each vehicle, okay? 10 vehicle, 20,000, okay? And so on. So you can be near to the ISO 26262 quantity of data, able to check the respectation of your fit threshold.
Sorry, I just want to add some point. So of course the timing is as mentioned in the functional safety standard, defined with the target failure rate, right? And you can consider success run and have the time threshold. Another way to do this would be to not consider this criteria of choice, but start from the project failure rate, right? And as the vehicles are running, you want to change this project failure rate as evolves. So in the sense, the project failure rate is your initial data, and you correct it as the time goes by, instead of choosing between two. this is something that you can do also. And in this case, the number of hours is to be required is less because you start from the project value, right?
Okay, I'm afraid we have to stop here, otherwise the guys here are starving. And so let's take lunch and we come back in 1 hour. But Massimo, Claudio, many thanks for the presentation. Very nice.
Thanks to you. I beg your pardon because the camera didn't. I beg your pardon because the camera didn't switch on, but we are not are not virtual, but we are real. I send the photo to the phone on Riccardo Vincelli that no, is not intelligent, artificial intelligence, but is a real speech. Thank you. Enjoy your lunch.
Thank you. Bye. Bye-bye.
Thank you. Thank you. Bye-bye. Bye.
I'm not hearing anything.
I have same problem.
Yeah, I hear
Good
you,
morning,
but not
Bill.
them.
How are you?
I'm doing great. How are you doing?
Good, thank you.
So it's not us.
Yeah, I'm assuming so.
He will have his presentation before. So maybe good news for you, we will finish a bit earlier today. You need to catch your flight. But okay, panel we have now, and you can see already on the screen, we have Phil that you will know already from yesterday. We have Colaud Hatem, technical specialist, functional safety manager at Dana Incorporated. And here we also have Andrea Matteucci, senior product manager at Progentex. The topic is very interesting, is how to manage the hazard for safety critical systems during the product life cycle. Interesting topic. So maybe I can start already with one question from my side. Do we have any standards that are helping toward this direction of this hazard? And I mean, which standard do you think it could be the best to use? And what is the maturity of this standard or those standards? Who wants to start? No one.
Well, I'm not the, I would say, the expert of function of all the possible standards. We've seen in these days a gigantic list of standards. So I don't know all of them, but definitely the functional safety standard is 26262. Of course, consider also the entire life cycle. So also after production. It is somehow lean, in my opinion, for the let's say for the after production to do what is recommended to do. This is clearly called, so they talk about maintenance before for the entire life, before retirement, and definitely they are looking for the manage of the quality issues and safety issues across the entire life cycle. But I think that somehow is lean, or at least this is where also we have new interesting studies that are now coming. Actually, I'm anticipating something of the presentation later that I'm going to do regarding predictive maintenance. As today we have discussed also with the presentation of our colleagues from Iveco, the idea of monitoring after production, what is happening in the field through some let's say feedback loop of data collected from the field. This is definitely something very useful, and yet I don't see much norm, at least in the context of functional safety.
Yes,
Hello, good afternoon or good morning also. Thanks for inviting us for this panel discussion. I would like to add over here, like the standard is enhancing the standardization way to do things. But we still, for example, for ISO 26262 or even for like sort of or other standards for that prototype release, the safety standards for electrical standards, all these standards are on place, and we're still using the design principles also in order to conduct the hazards. So if we look like back before ISO 26262 or these like standards, we have a really good design for the systems and for the vehicle, and we're still using design FMEA and the methods. Over here, what we're using for the standards or when we do the hazard analysis is either like at the vehicle level or for any hazards. For the component, we're still using these like methods in order to conduct what type of hazards of failure can affect the safety. Over here, the key point to evaluate these hazards in terms of safety, what's the impact of safety and what is the severity for these hazards? Is it like still we can consider them as a safe hazards or not hazards at all? Or these failures can affect and at the end will be hazards at the vehicle level and could increase the risk for the occupants or for the people on the road. So these things like evaluation for the study, maturity level, I think the maturity level is very good, but the key point, another key point over here, now we have new demand for the industry for the self-driving car. Most of the companies or customers, they're requesting to have the A sample on that to be tested on the public road. This is the maturity level changed from the, for example, traditional development to the new development for self-driving vehicles. So we need to have really good mature level for A sample rather than like delayed to the B or C samples. And the verification, the whole, let's say the model for development change it a little bit from like to have the iteration approach and to have more, for example, external measures or constraints to be added to the components or even to the system in order to expose that to the public road. So maturity level also not just for the standards and also for our work should be like enough to be reduce the risk to acceptable level.
Okay, I guess I would jump in and say, historically, we had this useful fiction that when a car was shipped as series production, all the hazards had been mitigated satisfactorily. And for a while, recalls were that, well, you know, we knew all the hazards, but we messed up on some mitigation. And then as software became more a part of the vehicles, we started not having all the hazards even, and recalls started becoming just as much about missed hazards as poor mitigation. Then security became an issue, and we said, but that's security, it's not safety. So we've still got all the hazards identified and mitigated, even though it's not really true. And we're doing these patches because the security people are lame and they don't know what they're doing. I'm having fun here, okay, just to be sure. And then machine learning came along, and we can no longer pretend that our hazard list is complete and mitigated the day we ship, because machine learning, A, we don't know how to do that. And B, even if we knew how to do that, the world changes every day and we have to change our machine learning. So to the degree we were willfully ignorant of the need for continuous security patches, once you have machine learning, you can't even ignore that anymore. You're going to have to do these patches all the time. And so that's what's dragging the entire industry kicking and screaming into life cycle hazard analysis and mitigation. Now you asked the standards question. Well, of course, I have a favorite standard. I'm not going to make that a secret. My favorite standard is UL 4600. And one of the centerpieces of that standard is safety performance indicators, which I spoke about briefly yesterday. But the reason it's there is because when you ship an autonomous vehicle or highly automated vehicle, you're not going to know if you've gotten all the hazards. And even if you did, they're going to change tomorrow. And so SPIs are the backbone of hazard management for UL 4600, and it's all about life cycle identification of new hazards because your safety case was invalidated and feeding back and updating them. So it's a seismic shift that recalls. It isn't about recalls. It's about lifelong hazard analysis and mitigation, and take the stigma away from recalls because that, of course, that's going to happen. Why would you expect anything else with machine learning?
I fully agree, yes. And we'll be okay going to my next question then. How do we handle system modifications? Or let's say also consider about the traditional recalls where you have to bring your car to the dealer and pick something, or now that the recalls are just push a download, push some updates, software updates, and yeah, off you go. So how do you see now hazard analysis in terms of system modifications and with the different kind of also recalls? Yes?
Yeah. For system modification, always we have to understand the impact of this modification on functional safety or even on other domains. So whenever we start, like the key point over here to start the impact analysis, what the modification can impact like evaluation for it, for this like a change. And we have over here, it's not just to understand the interfaces, also the interaction between this like system, this modification, this small part, and how that's will impact the whole like vehicle through the connection. So it's good to start with the impact analysis to understand what is the impact of this change and follow also the process. Always following the process is a good thing because we have to understand also who's managing that from the end, from the beginning to the end, in order to have even the correct communication, correct documentation for it. So it's not, I don't see system modification as if we handle it correctly, it's not, let's say it as a challenge, as something very, very like part of the daily working for like changing something on the system or in our design.
If I can jump in, I agree with everything you said. Let me give you the hard parts. The first hard part is there's a moral hazard that if you know it's easy to change, you're going to be sloppy, right? And that's just human nature. The second one is just to make sure everyone in the room is on board here, because I know most of the people, maybe all the people, but let's make sure we get this straight. There's a recall and there's a remedy. And the recall is the administrative process. I'm talking US, of course. Recall is the administrative process to identify a safety defect is in there and it needs to be fixed. And whether it's an over-the-air update or a dealer visit does not change the fact it is a recall, no matter what all the Tesla fans want to tell you. It is a recall is a recall because it's by definition a safety defect. Some safety defects are mitigated, remedied with over-the-air update, and some aren't. And the more over-the-air update you are, probably the happier everyone is, and that's cool, but it doesn't make it not a recall. Everyone sort of needs to get that straight. That having been said, when you look at impact analysis, right, the problem with impact analysis is understanding the difference between a small change and a big change. Because the small change you can do sort of lightweight, and a big change you have to really do a lot of E&V. And it's really, really slippery where it is. And I will point out an observation that if you add one training example to machine learning, it's a big update because you have no idea what's going to happen. And every time even if you train machine learning multiple times on the same data set, you get different answers. So you have to treat every single time you touch machine learning as a big update. And there's going to be a lot of people unhappy to hear that.
I agree with you. So for this point, like regardless if it is a small update or big update, we have to understand like what's the impact, over here. This is the key point.
And how do you know which is which?
Also do not miss, I agree with you. Yeah.
People lie to themselves. Oh, I only touched one. Okay, anyone in the room who's written a lot of code, I didn't touch anything. Why did it break? Uh-huh. There you
I
go.
agree. Another point over here is safety is not checklist. We did this, and we are safe. No, we have to check the completeness of our work. Yeah.
I agree completely.
You can see there is a much concerns, right, about changes of system and software, as we have discussed also with our colleagues of Red Hat. I mean, it's going to change faster and faster. I've seen interesting approaches in the field from the industry, like doing diff analysis. So just looking for really the single line of code, not single line actually, the compiled. So the compiled code, downloadable, how it changes bit by bit, and then routing back what are the changes and the impact of these change sets, so that they could somehow claim what Phil was saying about big change or big or small change. So the smaller are these bit changes, and somehow they can claim that validation is not required because the change are not impactful. I don't know how to call it. Yeah, I think there are very interesting approaches, and interestingly, the industry is moving forward to provide solutions. Yet they must be proven. I don't see that there is a silver bullet for this.
No, I don't think we have that. And I think especially with the OTA, is not only the impact of what you're changing, but also the OTA itself can have really the update. It can have a big safety risk. I mean, we know drivers got stuck in the car for hours because the car was doing some kind of updates and you could not even open the doors. So all of this is bringing up a new reality that I feel often is neglected. Yeah, we have one question here.
Not questions like cannot.
Please always give a name and company, please.
Okay. This is Abbas here. I'm from ZF Mobility, and I'm not a question just to add here. I agree that there are something open the door things, so which I was trying to explain. These aspects of not just functional safety or overall safety, particularly in the direction of new technology for the EV vehicles or for the autonomous vehicle, highly automated vehicles. In fact, in TIC industries, there is an approach for hazard-based safety engineering, HBAC in short. They use it for various standards they follow. And like, if you think not just for the 26262, but little bit bigger scope, because when you do a highly automated vehicle, the scope is little outside the E&E architecture of the system. So it's go outside what is the impact to the environmental, how it will operate, how the user or the external user or vulnerable road user will be interact with the systems when there is no driver in the loop. In that case, the hazard analysis could be overruled by some other, like you do not go for HARA, you go for a PHA from the 12,100 ISO IC standards, which is also being there in the industry for some time and pretty extensively to start with that. I do not say a standard can help you, but at least a guiding force in the directions which you make in a way that I'm not missing anything. Then back that evaluation of everything after the release is a systematic approach, which is stated in 194 checkpoints in UL 4600 from independent assessors to actual within the project assessor, independent assessors. So it has to be systematically evolved for what kind of technology you are using. Like AI topic is always being a fuzzy topic to discuss, but there is also other topics like what kind of steering, actuator, brakings, which may not be an AI topic. So you have to approach each of the problem area and how the harmonization between all the systems going into one vehicles is being interacting to the environment has to be taken care. So those approach has to be analyzed from various aspects as well, I would say that.
So I like that point. If I can add something, safety culture comes into play here. Because when you're doing life cycle hazard analysis, the most dangerous thing you can do is say, oh, that only happened once, so we're not going to worry about it. And that's just the type of thing that leads to problems in these systems.
Okay, one more question.
Juan Pimentel from Omnex. I'm not sure if this is a question more so than a comment maybe or observation. In terms of what we're talking about here, I think Phil mentioned this, OTA is going to play a big factor and pretty much related to what he also mentioned about safety recalls. Some safety recalls are handled by OTA, some are not, I agree with that. I took a look at the standard 24089 in depth. And well, particularly myself, I'm disappointed from the viewpoint of autonomous vehicles because there's hardly anything from automated vehicles in that standard. It's a pretty good standard. It covers pretty much safety from a very high level point of view on cybersecurity and a few other things that you need to do to prepare a update process and actually carry out that process, you know. However, from the viewpoint of managing the safety critical systems or hazards in this, from a talk, if indeed the safety recall involves an analysis, for instance, that's missing. So I would love to see the process that is in 21448, okay, which is a closed loop. It's iterative process because at every stage in that loop, you ask yourself, you know, is this, how we address all of the safety issues, SOTIP safety issues at least, you know, and then it iterates until you're done and you exit that loop and then that's fine. Only when you exit that loop, then you go to the software preparation and software download. And that's the start that I would love to see in any standard for OTA, particularly 28 or 89, you know, it's too late now. And that part is missing from the viewpoint of automated driving. Now, I talked to some people who are very knowledgeable about AI, and especially the standard, they say, oh, that's out of context. Yeah, fine, you know, that's a cop-out, in my opinion. But at least there would be some standard or some guideline or something that would tie in the process from 21448 into 24089. Thank you.
More questions? So maybe my next question, do you feel there's something online? No, okay, no. Yeah, my next question would be, do you feel that the hazard analysis approach is application specific? So if you're taking traditional applications like braking, steering, or body, airbags, or a new application like ADAS AD, the approach you have to take will be different, or somehow the approach is application independent?
Well, the basic principles definitely are applicable. So early today, this morning, we have discussed about why there are so many different standards for the different domains. I think that ultimately the point is simply that we have different constraints. So we have business constraints that are considered in these specific standards. But I mean, then regarding the application itself, hopefully we can always apply the same systematic approaches, and this should kind of root back to our basis, right? So system engineering and so on. I hope so. Otherwise, I mean, we've discussed about the multiplication of standards, and if we are going to have a multiplication of standards also by application, I think this is going to be a very, very tight jungle.
If I can, oh, go ahead, Khalid.
Go ahead.
Okay. If I could add an additional point here, one of the things I've noticed is a large number of recent software recalls that are about configuration management rather than a mistake that the wrong version of software got uploaded, or the wrong patch version, or the factory loaded the wrong version. So a lot of configuration management issues. So I agree that, you know, you want to use the stuff you used to do it originally, you probably want to use to validate the changes, plus you need this additional impact analysis. But people are really falling down on the job of configuration management, and that's got to be a first-class citizen, because if you get the wrong versions, incompatible versions in a car, you're going to have a problem, and it's going to be something that is too easily missed by, well, we validated this new module, what's your problem?
I would like to add over here, like in terms of like safety analysis, we're still using the same methods and methodologies. But sometimes for each project specific or product specific, we have to choose what kind of analysis we have to do in order which should be suitable for the call from the analysis. For example, for the vehicle, we're still using the hazard analysis risk assessment but when we do it for the component, it's not like we do something like hazard analysis. So it's not application specific, the approach, like the approaches over here or methods are well defined, but we have to choose the best methods for us for each system or each subsystem in order to achieve the goals or what we want to do. Then for the vehicle integration or at the other level, we have to have the connection between these analysis. For example, if we did the analysis for the component, what's the how that can affect the vehicle integration or the system integrated. Yeah.
Okay. Still one question here.
Traditionally, the 2622 was designed for a human-based system, keeping a human as a main operator of the systems. That's why it falls for any actuators developed for the driving functions or the sensing functions. If it's fall into that a human is behind that force, then it's fine. So that's why the ACC factors, controllability factors come into picture, like how the person's involvement is there. The moment the scope has changed, like autopilot or the L4 highly automated vehicles, in that concept, the existing needs some adaptations. I don't say that it escalate completely, need some adaptations for the hazard analysis. that part need to be think. What best do we apply for a driverless system where the human is not the fallback or human is not directly involved, or be it for the steer-by-wire or brake-by-wire systems where the mechanical override will not be working in that conditions. The controllability will zero then. How it will work?
Yeah, but even for this, we have a controllability C3 that is uncontrollable, that maybe is also considered in that situation.
But then you categorize everything as a C3 and D. That's not giving you a meaningful outcome. You might go a little beyond that. That is it controllable maybe by the operators or think in different directions.
Yeah.
I'm just giving a hint in that.
This is kind of a gap, or I want to say that.
Yeah.
I want to comment. Yes, I agree. There are some gaps in the sense that there are points of view that are not keeping the pace of the, let's say, even the product needs right now. Yes.
Yeah, it's shifting the controllability from the driver to the system. So over here for the hazard analysis risk assessment, that's why now we need redundancy on system in order to have this controllability in place.
Yeah, that's why also we see now much more STPA, control-oriented safety analysis, and so on. Sorry, Phil, you mentioned something.
I'll go a step further because we heard a hint of this in a previous talk. I'm a fan of ASIL E for Echo, okay? And I'm remote, so no one can throw heavy objects at me and I can get away with saying this, even though I'm upsetting some people in the room, and that's okay. But the reasons are, I like the reason we heard earlier that what about 10 or 20 people at a time dying? And if you're automating heavy trucks, you can't ignore this, that this will happen. You also can't ignore there'll be common cause failures that cause a lot of vehicles to all crash at the same time for the same reason, because this is how computers fail. But there's also, there's a lot more ECUs or electronics to fail or whatever. There's a bunch more stuff to break. And so a per component failure rate, if there's 100 times more stuff to break, the same failure rate is going to break 100 times more often. You add all these things together and ASIL-G just doesn't feel like it's doing it for me, even if you want to say controllability 0.
Yeah, I have similar feelings.
Okay. But you're in the room and people can throw stuff at you, so be careful. So.
Yeah. No, I mean, the discussion was also done many times within the ISO working groups. So should we add the new level of not, but finally conclusion was not. And yeah, similar discussion for the ASIL for trucks, lorries, or motorcycles. Yeah. And okay, maybe link it is to my next question. I know maybe it's a bit controversial question, so feel free to answer or not to answer, but do you think hazard analysis approach is also culture specific? So we see also in some countries now the development cycles are reducing drastically respect to others. So are they better to do now better techniques so they can do something faster? Or is a different approach being used?
Oh, okay, I have a strong opinion on this one. It is that some types of companies are incentivized to accept more risk. It's not that they're saying we're going to be more permissive of hazards. It's that hazard analysis is not at the top of their list. Their list is time to market. Their list is getting the next round of venture capital, and they're incentivized to roll the dice. It's simple as that. It isn't that they're doing it differently. It's that they're mostly not doing it. They're just going out and saying, well, we drove around, everything looks good, time to scale up. And if you're a venture capitalist, you can look at it this way, and I'm not defending this. I'm just trying to, when you see something irrational that you think is irrational, the smart thing to do is to create a mindset that makes it rational to try and understand the other actor. So you're a venture capitalist. I'm gonna fund 10 companies because I want to win the robotaxi market. And if I fund 10 companies and 3 of them have the bad crash that kills the company, I still win 7 out of 10 bets. I'm gonna make this bet every time. And you have to look at it as a portfolio thing, which is way different than a safety engineer at each one of these companies who, believe me, I get the phone calls for people who want therapy to talk to me, that their company is just rolling the dice and they feel very uncomfortable with as a safety engineer. But you have to look at the incentives and the dynamics. So I don't think it's that they have a magic better way of doing hazard analysis. I think they're just not doing it, not in a traditional safety engineering way. And they're saying, well, if it hasn't happened, we're doing big data. If it's not in the data, it's not going to happen. And that doesn't work for safety.
Yeah, sorry, okay, we got one question here.
Yeah, hi, Pia Helmer from ZF. It's more also not a question. I have similar experience. I had several company discussions in past where they discussed the HARA for the controllability rating, and everything what's an SAE level 1 or 2 or even 0, 1 and 2 was always rated as no, it's controllable. So we don't care about, and it was pretty difficult in past to discuss this, and yeah, to have there the confidence that not so that the people can do this. So yeah, just wanted to add this.
On that regard, I want just to add a reflection. Yesterday we have discussed deeply the safety and cybersecurity, right? I remember that there were this question about how to put this the cybersecurity manager and the safety manager together in the same room. I mean, this is for me is a good example where simply because they are trained also to look for different things, they eventually not see, let's say, a common ground. I mean, just to make it explicit, functional safety ultimately is about to reduce the unreasonable, below the unreasonable risk. Doesn't mean it's a statistical approach, right? What is considered improbable is not considered at all. When indeed for cybersecurity, well, you are actually looking for a breach, right? There is the intention. Someone is looking for, even if improbable, is looking for that. So it's exactly the opposite, right? And they are very interested to the field, so to after production, because in the after production is where the security breach happens. When indeed, if you do the right job, the perfect design, it never fails, right? So
actually,
they have different approaches because they are trying for different problems, let's say, and therefore this may be the bias, the cultural bias behind that.
Yeah.
Beside some bad practices
sometimes I
that
find
we
that
discussed right now.
Security, the culture bias even more, because in safety, okay, something may break, okay, you cannot do anything about it. But in security, what is the motivation? Why someone should do this? In some countries, this is completely not considered. Well, in others, yes. Sorry, Claude.
Yeah, just I would like to add for the controllability evaluation. That's when we do the verification and validation for safety, we have to re-evaluate the values for controllabilities for the functions. So if the controllability, the evaluation is not correct, then we have to add more measures. That's why we have to do the safety validation at the vehicle level to ensure that we have assuming or put the correct controllability in place for the hazard. Otherwise, we have to redo and add more measures in order to enhance the controllability at the vehicle level.
To add to that, historically, I've seen controllability be bargained down as low as you can make it. And then there's an assumption, and later on when the assumption gets violated, they ignore that. A specific example, without naming a company, because I've seen multiple companies do this. Oh yeah, automatic, so unintended acceleration, that's very controllable because you can use the brake, and we have vacuum assist pump on the brake. And then they take away, so it's ASIL B. Then they take away the vacuum assist pump, but they don't change the ASIL. And then you see crashes because people lose vacuum on the brake and they can't override many companies do this. This is a classic thing from decades ago. And so I really worry that the industry as a whole systematically systematically overestimates controllability, because the culture is, let's blame the driver if we can find a way to blame the driver. And I'm the one who doesn't work for a car company, so I can be more blunt, and hopefully people feel seen when I say these things. But let me add another thing that's really interesting, because the regulators sort of went along for the ride. But the day after a company told the U.S. regulators, NHTSA, I think it was the week after, that they were going to deploy level 4, all of a sudden I started getting calls from them. And I said, that's really weird timing. Why is that? So I'm going to make a bedtime story. I don't know if it's true or not. And these people are all gone from the administration. The bedtime story was they knew this was going on, but as long as they could blame the driver, nothing was broken. And guess what? there's no driver to blame. What's your plan now? Oh, they better get a clue about software safety because their entire playbook just vanished in a puff of smoke. And so maybe the good news about automated driving, or especially autonomous driving, is that whole controllability theater goes away because who are you going to blame?
Excellent. So we only have 30 seconds left, so no time for a new question. Any final comments from the panelists? Or should we stop here otherwise?
So sorry I couldn't be there in person. I just got back from Australia. It was too much, but I appreciate everyone putting up with the remote and wish I could be there. Thanks.
I saw your picture. You were doing some very safety risky sport. Yes, hopefully next time we will be in person. Okay, so I would like to thanks a lot. Thanks really to the panelists. Was really great panel. And yes, we have to move on. Okay.
Thank you very much. Bye-bye.
Thanks. Bye.
Okay, next presentation again will be virtual, but no AI. So we should have, let me see here, yes, okay. We should have now Stefano Stabellini. Ciao, Stefano. Can you hear me?
Ciao, yes, I can hear you. Can you hear me?
Yes. Okay,
Very good.
that's is the next, so yeah, sorry, yeah, the presentation is about the safety certification, safety certifying on open source project, the example of Xen as hypervisor. So Stefano Stabellini is a fellow from AMD, and yeah, the stage is yours.
Thank you.
Can you
Let
try to
me
share the
share.
presentation?
Just now. Can you see it?
Not yet. Let's see. Okay, yes.
Perfect. Okay. So yeah, I've been a Xen maintainer for a very long time. Let me tell you about our road for Xen and safety. So Xen is, as a brief way of the introduction, is an open source project under the Linux Foundation. It is widely used in the industry across verticals from data center to embedded and automotive. One thing that is nice about Xen is that is a diverse multi-vendor community with maintainers coming and community members coming from all sorts of companies and backgrounds. And you can see the breakdown of the contribution by company on the pie chart on the right. And AMD is one of the top 3 contributors. Another thing that is interesting about Xen is that it can cover from the simplest embedded deployment and configurations to the more complicated. And so by a simple embedded deployment from a hypervisor perspective, I mean a static partitioning configuration where everything is statically assigned. There is no scheduling, there is real time. While on a more complex configuration like IVI, I mean something where there are many more domains, more complex domains such as Android, and devices are shared. Like you have a GPU shared among multiple domains, audio, input, all share among multiple domains using probably something like VertIO. So Xen can do both, and sometimes can do both on the same vehicle. Like for instance, in this example, we have Xen running on both the Vision Hub and also on the IVI system connected over PCI. So let me talk a bit about the simpler configuration before we go into the more complex. So first of all, Xen supports scheduling. Normal scheduling of multiple virtual CPU on a single physical CPU, as you can see on the bottom, like the credit scheduler. It also supports not doing any scheduling at all. And we call that null scheduler. What it really means is there is no scheduling. So everything is statically assigned one-to-one. There is no chance of moving those vCPU, no chance of context switching, nothing. Interestingly, Xen can even have both at the same time, because you can divide physical CPU into different groups and run and select different schedulers on different groups. So you can even have both on the same SoC. But really, for the simpler configuration, the one for real time and static partitioning, the null scheduler is the easiest and best option. The other interesting feature for the simpler configuration is DOM zeroless. So traditionally, you will have to boot Xen. Xen will have to boot a Linux environment privileged called DOM zero. By privilege, I mean it has the ability to make system-wide changes, such as system-wide shutdown, create other VMs, destroy other VMs. So you would first start DOM zero, and then DOM zero would start other VMs. Now, this is not ideal for a number of reasons, and one of them is safety. Because with DOM zero in the picture and required, you need a DOM zero safety certified at some level. So one of the changes that we made is DOM zero less, where Xen, everything is statically configured before boot. The information is passed to Xen at boot, and Xen start all of the VM in parallel without the need for DOM zero doing anything at all. So yellow and purple are booted in parallel with DOM zero, and DOM zero is doing nothing. So in fact, DOM zero becomes optional, and you can take it away, which is great for safety because then you don't have a dependency on DOM zero. So in summary, static partitioning configuration look like here in the picture. Everything is statically configured, like the number of VMs, the amount of memory, number of virtual CPUs. There is no scheduler, you just have the null scheduler. There is no DOM zero, there is no hypercalls, no services at runtime, just a very minimal footprint after boot. Even the IOMMU become optional because the memory can be one-to-one mapped on ARM. And if this didn't convince you that Xen is an embedded hypervisor, then the last bit will, because Xen now runs even on MMU-less systems, so systems without MMU, such as microcontrollers, like the Cortex R52 and the Cortex R82. And now I'm going to jump straight in the completely opposite end of the scale, where like IDI, where on this example on an AMD x86 system, where you have many more VMs, large VM like Android, lots of devices that are shared. Like we have VirtIO, NET, Block, GPU, T, GPIO, I2C, input, and PV audio all on the same system. So for sure, from a virtualization perspective, is a more complex system. Okay, that was just a brief intro, the 5 minutes intro, but and to get into the more interesting part of the presentation, to talk about safety. So Xen is the reference open source hypervisor for embedded and automotive at AMD, and we are working on making it safety certifiable. Both ARM and AMD x86, we are targeting IEC 61508, SIL 3, and ISO 26262 ASIL D. But what is interesting about this effort is we are doing it with the community. So this is an open source effort. The certification is based on the open source upstream code base and the open source and community processes. It's not a private fork, and we're definitely open to collaboration with others. Let me tell you what is the architecture for safety that we are using. So what you see on the picture. So Xen is running entirely in a higher privilege level on its own, which on ARM is called hypervisor mode or EL2, and that's control on very few components like the timer, intercontroller, MMU, IOMMU, the PCI root complex, and the CPU. Everything else is directly assigned to domains. There is no DOM zero anymore. DOM zero has been split into two, the control domain and the hardware domain. So the sum of these two will be old school DOM zero. But in reality, the control domain is only optional. In fact, we might not even have it at all. Control domain will be the only one that is privileged, the one that can, let's say, shut down the entire platform. But like I said, is optional. Because all of the domains are started with DOM zeroless, you don't need it. The other part that used to be DOM zero is the hardware domain and is the default recipient of all devices. So like the Ethernet device, SATA, you name it, they get assigned by default to the hardware domain, but it doesn't have to be privileged. It has just a small enough privilege level to be able to run VirtIO backends to share Ethernet or SATA or that device to other VMs. And this, just to make it more interesting, like it's all configurable. So like I said, the control domain is optional. You can run safe or non-safe application in regular DOMUs, and you don't even have to have a single hardware domain now, because the hardware domain is the default recipient of hardware. The other one, we call them driver domains, but you can have as many as you like and assign devices to them and then run Vertio backends there. So mixed criticality is completely supported, and it's also completely flexible. So you can have more than one safe VM. You can have only one or zero safe VM. You can have as many QM VMs as you like. There is no dependency on Linux or any other OSs. We don't depend on Zephyr or another RTOS. You can run it or you cannot run it depending on your configuration. Xen just is there to ensure isolation and freedom from interference between all of these domains. The configuration is fully static, so the domain creation is done via DOM zeroless, memory, vCPU, everything is configured before boot. It's configured before boot, and domain creation is done at boot only. When you want to reboot a domain, in fact, is only like a real, from a Xen point of view, is only a domain reset. The domain stays in place. The domain is not it's just reset from the initial state. And the operating system environment, such as Linux, thinks a reboot is happening. In reality, everything is still static, the same as at boot time. You can assign devices, both PCI and non-PCI, to any domain. Both the null and credit to scheduler are supported. We do support this fine level of configuration between and privilege split between control domain, hardware domain, and regular DOMUs. And finally, we support a number of VM-to-VM communication mechanisms, such as Vertio, static share memory, PV drivers, and more. So in terms of safety certification plan, our plan is divided in two phases: the safety concept review and the final assessment. And just this month, we completed the safety concept review, and it went very well. So we are on the right track. What are our engagement with the upstream community? Okay, so there are a number of things that we have already started last year, and we are in fact nearing completion this year. And there are a number of things that we have just started, and we are at the beginning of the journey. Things that we started last year and we are toward completion are any features that are relevant to our safety architecture. Like the DOM zeroless implementation for x86 is called a hyper launch, and this DOM zeroless implementation for x86 is missing. So that's still currently upstreaming, on its way upstream. Another feature that's missing is a PCI pass-through, like the device assignment of PCI device, a PCI pass-through implementation that's compatible with safety, meaning the PCI root complex has to be in Xen itself, and that is common across ARM and x86, and still is also on its way to being upstream. Another, but close to finishing, and another one is MISRA. MISRA was actually a very major endeavor, and the first big task that we did together with the community that definitely is relevant. I mean, it is safety, like clearly for safety. I'm going to tell you more about MISRA C, but we made tremendous progress, and we now have the MISRA C checker as part of the Xen CI loop. Other activities that we have just started are upstreaming of assumptions of use that are assumptions that Xen has on other components in the system, software safety requirements, and also the architecture specification. And I'll tell you more about that. Let me start from MISRA. So the first thing that we did is we sponsored MISRA C training from to all the key members of the community and the maintainers. It is important for MISRA that the community really understand the value of it for it to be successful in open source. And then we started, analyzing. We identified 143 rules that are relevant for Xen, and we started talking about them with the key maintainers one by one. Is it good for Xen? How can it be adopted? Do we add it to our coding style? We identified 120 rules that are really relevant for Xen, and we want them as part of our coding style. We added them to our coding style, and we started fixing violations. That resulted in 148 commits on Xen 4.18, and a 20-time improvement. Like we went from 2 million violations to 100,000. Now, I know the numbers in terms of absolute number are really high. Even 100,000 is high, is more than the number of lines of code in Zen, for ARM at least. But, you know, these numbers are counted by counting each macro as the invocation. So if there is a violation in test bit, it's not counted as one violation. It's counted for one violation for every time test bit is used. So it's more meaningful as a difference from 2 million to 100,000, so a 20x improvement. The other thing that's meaningful is I can tell you we have a MISRA C scanner as part of our CI loop, and we have 82 rules that are clean, 0 violations, 5 more that are clean on ARM64 only, so we are a total of 87, and 21 that are not 0, but there are low number of violations, and we are monitoring, meaning we are checking against regressions already. So some conclusion on our from our MISRA activities are, you know, MISRA needs to work for the community, and the community needs to work for MISRA. So in a way, is the community really need to learn the value of MISRA, and there is definitely a lot of value in there, such as you know, many rules on MISRA are there to address undefined or implementation specific behavior of the compiler that are really critical to address. But at the same time, for high quality code bases and existing code bases like Zen, and with an established culture for quality, it's often not possible to take the rule in as is, because there are many rules that are trying to reduce developer confusion, but developer confusion for a culture and a type of developer that's not the one of our community. So we had to make changes to the rules, still addressing the most important part, the undefined and implementation specific behavior, but deviating the one that is about developer confusion, which in reality will cause more confusion for us. Then jump into the other major category of things that we had been doing is requirements. So the first thing that we did is we split the requirement into 3 levels. High-level requirement we call market requirement, mid-level requirement we call product requirements, and software safety requirements, which are the in-detail description of all the expected behavior of Zen. After defining the 3 levels and you know, properly and documenting them, the next problem to tackle was traceability. So we need to trace, meaning link, each market requirement, the product requirement, and product requirement, software safety requirement, and eventually all the way to the test case, test code, and job. How do we handle that? So that's an interesting question, because typically requirements have often been dealt as with large, complex software like doors. And the problem is with using something like JAMA or doors in open source is, how do you get access to random contributors? How many licenses do you need? How can you edit in parallel and many people the same thing? How do you even teach the community to use doors? So this is a difficult problem. So, and this is the reason why at the beginning of the of this effort, we looked closely at it and we realized it was not possible to use something like that. Now, at the same time, there have been an effort in the open source community at large to use plain text document to write documentation. Now, when you go on GitHub, any project open with a README, and the README is rendered as a nice HTML, but the README itself is actually a text file that is written with a simple format called either Markdown or RST. So there is more and more documentation written in open source in either RST or Markdown. So the first decision we made is we are going to adopt RST. We could have adopted Markdown, but either way, we adopt one of these text formats to write requirements. Because this way we can use the same review process as for the code, the same way to the same maintainership process, the same change revision control process, the same Git repository, same everything as we do already for the code base. Then, and it still renders pretty well. Like on the left, you see an example of a requirement written in RST, and on the right, you see a rendered in HTML version of it. So what the problem is left? The problem is traceability. Like, I mean, the RST files by themselves are not going to link, you know, between each other. Now, fortunately, the open source community is really coming to the rescue here. There are a number of projects that I have started to address the traceability need, including OpenFastTrace, StrictDoc, and Bazel. And I know that some of the authors were at this conference. Now, we adopted OpenFastTrace. Why? Because it was the simplest for the way we set up the requirements. OpenFastTrace is based on tags. You add tags in these RST files, then you run OpenFastTrace. It's going to scan the entire repository, find the tags, generate the links, generate the traceability report, and the job is done. So this is an example of RST file with a specific tag, you know, this rec tilde, this, and so on, is a specific format with the class of the requirement. The last is the version of the requirement. So this is like an OpenFastTrace tag, and this is a dependency on other tags. So this is a practical example just to make it a bit more concrete for you. And that is the traceability report. So you can see that it's generated in HTML. And the other thing that is nice is it can tell you if any of the links are broken. The green mark means good. The red mark means something in the linking went wrong. Either something was outdated, the version was not upgraded, the link is missing, something is wrong. And that's it. So I'm here for the conclusion now and here to hear your questions. So in conclusion, the Xen community is working together on making Xen safety certifiable. The certification is based on the upstream community processes and code base. We do have bi-weekly meetings with other community members. There are a bunch of people from different companies joining, including Renesas, EPAM, ARM, AMD, and we had 2 new members this week alone. So let's work together and make one of the first open source projects to be actually safety certifiable. And I put some contacts on the top right on the slide. If you want to reach out to me, feel free. We do have an architecture for safety. We support mixed criticality. It's extremely configurable in terms of what OSs to use for safety, how many safe VM to have. Do you want a control domain or not? It's all very configurable. Misra, it was a major effort and a success among our maintainers. They understood the value of Misra and safety, and that actually was, I think, a very good way to start bringing the Xen community together and closer to safety. And finally, for requirements, we are using requirement as code. I think that was that's really a well-fitting for an open source project, and OpenFastTrace to handle traceability. We are in progress of upstreaming requirement and more. And I'm ready to take questions.
Okay, many thanks, Stefano.
You're welcome.
And by the way, thank you for waking up so early to join us as well. So
No
again,
problem.
we have already 2 questions. So let's start.
Yeah, Juan Pimentel from Omnex. My question is about the certification process. I have never heard of the one you're talking about. Is this supposed to be self-certifiable, community certifiable? Because you're going into a technique here that it's a deviation from the normal way it's doing this in functional safety, at least, which is third-party certification. So could you explain the pros and cons about this particular way of doing certification? And is it acceptable by the OEMs and the companies, you know, in the supply chain, basically?
Absolutely. This is a good question, and give me a chance to clarify. So we are proceeding on 2 parallel tracks. On one end, AMD as a company is working with assessor in a traditional way, so nothing different from the usual. But at the same time, we are upstreaming and you know, making public and working with the rest of the community on how many topics as possible, such as the requirements and such as Misra and more. The idea is the closer the community is aligned with safety, the easier it is for AMD or anyone else to safety certify Xen, and the easier it's going to be to upgrade. I mean, move the certification to a newer Xen version because everything is kept up to date and is maintained by the community. The other thing I would say is we are mapping upstream reviews, upstream maintainership, upstream skill sets to the ISO 26262 requirements. And I mean, so that is also something that we are doing, but that's not particularly different than detailing who are the gatekeepers for the certain project within a company.
Okay. Next question.
Oh, it's working? Okay, now it's working. Thank you very much. Thank you for the presentation, which was very interesting. And so my name is Alexander Matos from Electrobit, and I have a technical question. So you mentioned one of your focus is guaranteeing FFI between the virtual machines, but the hypervisor runs in a higher privilege level and can therefore also affect the virtual machines that it is starting. How do you ensure the freedom from interference between the hypervisor kernel and the virtual machines that it starts?
So the idea is that typically on these systems, the hypervisor will be at a higher level of safety, like we are aiming in this example as ASIL D as in Delta, and higher level of safety of the VMs. So the idea is that the hypervisor is more trusted. That said, the amount of time and services and provided by Xen after the initial boot phase, it's really minimal. So it will actually not be difficult to ensure freedom from interference also, I mean, not be difficult. I mean, definitely there are things that the hypervisor needs to do to that has an effect on the VMs. But I think it would be possible to prove a limited, at least, interference possible from the hypervisor because it runs for so little time. But yes, so the model is freedom from interference between the VMs, not the hypervisor versus the VM.
Okay, so you're basically taking a process argumentation for the implementation towards the VMs that it starts. Do I summarize it correctly?
Yeah, so the idea is that we can separate a safe VM from a non-safe VM. So you could run, let's say, Linux as non-safe, and you could run Zephyr as safe. Both of them alongside, and Xen will ensure that each of them cannot interfere with each other.
Thank you.
More questions? Okay, one question here, Oscar.
Just a quick one. What do you do with broken references you showed?
This is because we are still at the beginning, so we are still populating the requirement. This is actually from a month ago, so now we are we have many more requirements. But yeah, you need to address them. So broken references cannot be allowed to stay. That just means that either one of the requirements in the chain is missing or is outdated. So it's we're going to fix them all. That's in practice.
More questions? I mean, actually, we could also call already here, Gabriele Roberto, so we could already start and connect to the next panel because finally the topics are really linked. Potentially, one question from my side, Stefano. I think you already achieved quite a good progress here on Xen. What is the lesson that you will say you could give as a gift to other groups? I mean, now we're also talking about Linux and so on. Any indications, any tips you can give?
So I think it's quite important to align the culture. So I think that's my tip. So in reality, many open source projects, they do have a safety culture. It's that it doesn't align with the language, first of all, with the language, like just the word that they use when they talk about things. But it also doesn't necessarily align exactly with ISO. But it doesn't mean that people don't care about quality of the code. I mean, they very much do. So I think my first tip is, I think it's very important to align the community on the language why we're doing this, why this is good, why this increase the code quality. So one of the very first things that I did, that we did together, so I have to say Roberto from Bagsang really was very helpful also on this. So it's to explain that we're doing Misra to improve the code quality. We are not doing Misra to do Misra. The goal is to improve the code quality of Zen. And if something doesn't improve the code quality of Zen, we're going to do it different. It's not about a rubber stamping Misra on Zen, right? And that's what really brought the community into safety and Misra and the activity.
I mean, if you want to add, okay, but this question was more for anyway for Stefano. Okay, I mean, I would like to migrate now onto panel discussion, at least challenges and so on. But I think the first question for me is why are we talking so much now about the open software? And so up to recently, we did not have any of these. And now suddenly, Zen, Linux, all of these. Why? What's happening?
Well, I mean, from the visibility that I have is, I mean, what I can say is that I think, I mean, open source software provides a collaborative platform that to some extent have many advantages. One is like a faster time to market. Why? Because, you know, the code is open. And if we have projects that on top of the code also provide, you know, a reference collaborative platform, like, you know, we have, you know, the Eclipse, Elisa, there is the Zen special interest group and others. So the automotive grade Linux. So this really, you know, allow all the stakeholders, so the people that at the end would make money out of it, you know, to really, you know, speed up the development process, the verification process, all the activities that are needed at the end to deploy. So this is one of the reasons. And other reason is also that in terms of pool of talents that is available, you know, it is much easier, you know, to find engineers that are, you know, skilled, you know, to develop on that specific platform. And, you know, one other reason is that if you look at operating system like Linux or other, you know, open source project that have got really a huge, really wide adoption, the open sourceness of that code also provide trust and a high degree of reliability because of the exposure of the code, because of the indirect exposure of the deployments, right? So you have like, you know, very huge deployment that at the end result in, you know, in code stabilization. So, and I think, you know, from the visibility that I have, I think these are, you know, the factors like that are driving this transition.
Yeah, for me, the answer is basically so today we have a strong increasing about the trustability on Linux based on basically competence, rigorous process, and basically data available to justify, from which basically you can justify you have really concrete evidence that it works. For the competence, obviously, if we wanted to be a software maintainer, it's not easy. You need to provide a lot of evidence patches, basically. Such patches should be accepted by the community. And frankly speaking, it's not an easy job. And then it's even if we have not something like a concept like a safety culture, no? Which there's a sort of guideline for accepting formally one person to classify if such person is really expert, but there's an existing method for identifying competence in the community. Process, obviously, for accepting a patch, there are different peer review, and then you need to satisfy different questions. You need to provide evidence, justification about the reason why your patch that you're proposing is really okay, good, and meaningful to be integrated in the overall operating open source solution. And basically, last but not least, is the data. Yesterday, we discussed a lot of time about data, are critical for supporting, in our case, safety arguments, okay, to justify basically our safety case. Now, in the Linux world, basically, we have an incredible amount of data about historical, statistical background that justify that a patch works. The user coming from different end user, the different platform, hardware platform, the user, the same software. Then basically, this combination of ingredients make a lot of value exactly today. And then this is the reason why I guess Linux is so promoted to be used functional safety.
So I can add a small thing for that I think also applies to Xen, and is the fact that maintainers typically work for different companies. I mean, that depends on the software project, of course. There are open source projects where there is only one vendor, so and those are valuable too. But for projects like Xen and Linux that are multi-vendor and there are maintainers from every company, we should not underestimate how difficult it is to influence a maintainer into taking a bad patch, because it's close to impossible. You have no leverage whatsoever. So this is something different from proprietary environment where, yes, there is a gatekeeper, but you're close to a release and the release has to ship, and who is going to tell the SVP that the release is going to have to be delayed, right? So that kind of mentality doesn't work in multi-vendor open source projects.
Yeah, excellent, Matthäus. These are valid points, and I really subscribe to these points, but we should be honest to ourselves here. There's one further argument for customers. They simply think that it's cheaper. And we all know this is not necessarily the case, because maintenance efforts, upstreaming things, developing things, qualifying things, and ensuring maintenance over time are huge efforts. But this is for many customers who don't really understand what they will get here, a big motivation.
More questions from the audience, also again online? No, still too shy. I mean, for me, again, one of the question is responsibility. So if something finally goes wrong, yeah, of course, I can have some certificate, some assessment done by some third parties, but finally, who is taking responsibility for open software? That is also a question.
Us?
Yeah?
I mean, it's the software vendor, right? I mean, who is accountable? Like, for example, Red Hat. I mean, the question is tricky, really. I mean, and then there are different cases. Like, for example, if I look at the in-vehicle operating system, it will be ourselves taking accountability for the functional safety claim that we make, right? So, and, in this regard, we are responsible for that.
Yeah, but for example, the ISO standard is asking us to prepare a DIA done with your suppliers. In case of open software, I cannot have a DIA with open source community, I guess.
Yes, you can.
You can?
Yeah, of course. I mean, we draft DIA with the OEMs that we work with. So, because at the end, we are accountable for the claim, for the safety key, even if the ingredients come from the open source, right? Most of them, right? We at the end we are responsible for packaging this ingredient, for maintaining them over a pretty significant amount of time, right? You need to retain the safety case for quite a few years, and we also draft DIAs, yes.
Yeah, from my side, basically, I think in line with the ISO standard, basically, if let's forget for a moment an open source solution. If we receive from some of you an existing software element, which is the way for using it by applying a qualification on existing software,
Now, in that case, do you need a DAA? No. Obviously, the integrator will take the entire responsibility, accountability. Then, obviously, the integrator is accountable of what? About the risk, obviously, on adopting a certain solution. Then, what is important is, I think, here the message, what is important is not really a DAA, let me say, with an hypothetical open source community, but to have a strong, let me say, risk assessment, if you want, that justify technically the usability of what you want to reuse, in that case, an open source solution. This is my view.
Thank you. And okay, we discussed already before also your presentation about new standards for use software and now potential integration in third edition. How far away to really have a standards suitable for open source to make open source software safe or justify the safeness? Are we close now or still a long time to go?
I think in that case, the answer should be different because basically when we write a standard, in that case, like the ISO standard, ISO 26262, the target is not to satisfy one specific solution, obviously. In that case, we are not writing a standard in order to have open source solution. Then the approach should be identical for any kind of software. Then this is our point. What is missing and is in common with respect to an open source community and other closed community, like company, for example, is, unfortunately, we have discussed it several times today and yesterday about the interpretation of the V model that we have in part 6. Because basically the interpretation at first glance is we have some temporal conditions from the different phases. Then you need to start from scratch, you need to define the safety requirements, then after that you need to create a design, then you need to implement something, and then after that you can start to test your unit, so preferably the integration testing and so on. Then implicitly it seems that this V model is you cannot apply for an open source solution, but you can apply for any kind of software developed according to a continuous integration and continuous deployment. This is the reality, if your interpretation is like that. But if, I don't remember the talk from another colleague, if you think in terms of objectives of the standard, then in that case you can remove the concept of temporal condition. Basically, what you need is to ensure that you have an appropriate set of safety requirements. Then you need to verify that the design is correctly connected with the requirements, and that you have the right units, and so on. In that case, with a different interpretation, it's possible to qualify hypothetically a monster like Linux. Obviously, another gap is connected with the final part of the story of part 6, because it seems you start from scratch, and after the deployment, the story around software is completed, is done. It's not true, because after that, after the deployment, you collect the data about the use of your software in a context, and then you can update. You need to maintain the software. And this is a part that in reality is missing in the ISO standard. It is in common with an open source community, is in common for our companies. Then I think that if we split the single mountain monster private statement in a small private statement, probably we can obtain benefit for all of us.
I would like to add something. To be honest with you, I would even take a step back compared, to safety standard, because you said, how far we are, with respect, to the goal of a safety standard that is suitable for open source software. Now, if you remember the presentation that I did yesterday, what we did is, we built a safety case, and then, considering the objectives of the ISO. Okay, now, one of the key issues that we have today is that all the quality standards for software that we have are also based on a V model, on a requirement-driven development. And today, we do not really have quality standards that are really compatible with a code-driven development approach that is instead what is used for open source development. And in fact, I mean, probably I didn't mention it yesterday, but in my spare time, I'm also the chairman of the Linux Foundation ELISA project. And what we are trying to do now is we have started a discussion to define good quality practices for open source software, with the goal of defining really sort of key performance indicators that can be used to rate different open source projects, because all open source projects are different. Zen is different from Linux, that is different from the glibc, that is different from the standard C++ library, right, for example. So, and the key question is, how can we rate a good quality open source project versus a bad quality? If we first are able to answer that question, that will be much easier to define, you know, an acceptable tailoring, you know, for open source software in general, I think.
This is so important. I'm glad you mentioned this. This resonates with me extremely well. So the reality is open source projects are all different, and some of them might not necessarily have very good security or safety practices. I mean, if you go out to a random repository on GitHub, it does qualify as open source. It is open source as licensed. They maybe even take contributions once in a while, but doesn't mean that's necessary. But we do know that some open source projects, such as Zen, but it's not the only one, and you know, Zephyr and others. I mean, they have very strict review practices, and there must be a way to recognize. I think one of the difference between open source and other projects is some of these projects, well, obviously Zen is the one I'm most familiar with, but it's not the only one. They have extremely strict review processes, way stricter than any other. I mean, way stricter than some, at least, the other proprietary environment, meaning that, as an example, our patch series, before they get accepted, they are often going to 9 version revisions, 10, 11, 12. I've seen 14, 16 version of revision before they're accepted. So that's not, I mean, that's not common in proprietary environments or even in random GitHub repositories. So it's important to value this. And I don't think there is an ISO 26262 metrics that tells you what your average number of version of revisions before it gets accepted. But maybe there should be. Yeah.
Thank you. Okay, we got one question online, actually.
That is correct. And the question is, for AI, it seems every solution involves is open source. Any opinions on taking on both challenges, AI and open source, in a safety scenario?
Well, I mean, this is like, you know, trying to handle 2 independent degree of complexity at the same time. So I really think that in this regard, we should follow like the divide and conquer approach, as in, you know, first, you know, finding best practices to develop, you know, artificial intelligence with a safety claim, and then in parallel continuing to work, you know, on you know, best practices for open source development, and then probably we'll find a way, you know, to address both. Because to be honest with you, like, I think that when it comes to artificial intelligence, the main issue is really architectural. So it is, you know, by design, the way neural network works, you know, it is not possible to predetermine the expected result, right? Whereas the main challenge for open source software instead is mainly associated with the systematic capability of the development process. And there are 2, in my opinion, there are 2 independent domains. So if you solve, you know, them independently, then probably we'll find a way to, you know, to answer this question.
Next question.
So you mentioned the systematic capability of these components, and I would like to support that because this is not something you need only for safety. So even for a standard QM release of a Linux system, and there are many on the road by now, not with safety, but with QM criteria, the customers require an SBOM, so a software bill of materials. It needs to be rated. What is the quality of the components that you integrate there? And I also remember internally huge Excel tables with all packages and how we rated them. And to have here a common approach, that's what would be really a good thing.
But this is already being addressed there is a project, basically in the Linux Foundation, we have defined a common standard, to define this as BOM, so that we can have a bit of material shared between different projects. And I think it's used in Zen, Zephyr, in Linux. So
yeah, we had the problem before that. So
yeah, the problem before but now this is being addressed, and I think they're doing. Okay, so
yeah, we know it, but it's really you need this, and but still you have the format then, but you still need to fill it out. So you need to fill the criteria and come to a common set of criteria that you need here.
By reality, we have the same type of problem with the ISO standard in general, because if you check in part 2, basically the request for quality management is a ISO 9001 that you can use for certifying your bottle of water. And basically another request in part 6 basically is to have Automotive SPI, so CMMI, but basically this standard used for improving basically an existing process, not to verify if your process is in line with a software process standard. So it's not like 12207 standard. It's a different kind of standard. Then we have a gap, frankly speaking, in general.
So again, one question from my side. Can you elaborate a bit more on the relation between open software and ASIL? So do you think open software could be linked to maybe or maximum ASIL? So I can see you have different approaches here as well between Linux and Xen. Some comments about it.
We cannot generalize, I think, as Stefano said already. Different open source projects are very different between each other. For example, if you look at Zephyr, I think they're targeting SIL3, ASIL-D. Zen, what are you targeting, Stefano? Also, you also
SIL3, ASIL-D.
ASIL-D, right? With Linux, within Red Hat, we are targeting ASIL-B, but I think it's a common understanding. Also, Electrobit, right? You guys, I mean, is targeting ASIL-B because it is, the complexity of Linux is not comparable, to the code baseline of Zephyr or of Zen, and so really, or ThreadX is also open source now, I think. So really, yeah. So the answer is depends. So different open source projects are likely to be qualified, certified according to different SIL, ASIL, and yeah.
Yeah, so maybe to change the question, okay, I don't know if you can say if it's confidential or not, but is the level of ASIL that you are considering, it was driven by use cases or was driven by complexity?
It was driven mainly by complexity, and indeed, so yes, it was driven by complexity. We had partners that asked, like for an ASIL-D Linux, and we have to say, no, sorry. I mean, right now we are targeting B, and we don't feel like safe to go higher at the moment. So yeah.
Same for you, Stefano, if you can answer.
I think it's the combination. I mean, it's clear I think for a hypervisor is clearer than for an OS that, I mean, you really will want D ideally because, I mean, the purpose of a hypervisor is to run something like, let's say, ASIL-B Linux from our friends here alongside maybe QM Linux or Android. And for this use case, the recommendation is for the hypervisor to be D. So that's one reason. So for the use case is clear. And for the complexity, we looked at the code base, and like it was stated, the Xen code base is much smaller than Linux, and it was small enough that we thought we could go to D with a old school approach, and that's what we're doing.
Yeah, for me, basically, the question could be refined in a different sense. It could be in the future a Linux solution, a SIOC, basically. But I think, frankly speaking, not entirely, obviously, but by the nature of Linux, because obviously that the intent of this type of solution is to satisfy an incredible amount of hardware platform, and to be suitable for different end users. And then obviously that the different approach could try to limit basically the safety scope in order to get to reach basically a certain initial target. But at the end, in that case, the purpose could be at first glance to arrive at a sort of a SIOC, but at the end you need to validate your safety target against, again, your hardware, against the target environment.
By the way, I'm personally very much against if somebody tries to sell you like an OS certified in a hardware independent way, I would be very skeptical. Not even the glibc is hardware independent. Think about the kernel.
Well, it could be useful as a starting point, but at the end, you need to validate your story with the real hardware.
Yes, I guess so, yes. So we have the last few minutes, but still 6 minutes. And we have no coffee break, so. Yeah.
So what can I add regarding discussion about safety element out of context? So it's definitely possible to build an operating system as a safety element out of context. Of course, it's hardware dependent. So you can't get by without qualifying on the hardware and making it really guaranteeing this only on this exact device and nowhere else. But this is true, but for the application specific part, it's definitely doable to do this as safety element out of context, especially also for a hypervisor. So hypervisor is a natural component to be a SIOC, because it's really targeting the integrity level of the system, which can really nicely be encapsulated from the functional part, which actually also the IEC 61508 does a bit nicer than the ISO 26262. Really distinguishes between the two.
I think the problem is with the wording SIOC, as in out of context. That sounds like, that it works in every context. No, this is not true. I mean,
there are the assumptions. There are the assumptions which
I think
limit
it's
the
a big
context.
misunderstanding that out of context means no context. No,
Exactly.
context assumed.
Yeah, just to explain safety element out of context, you can qualify an operating system, but this does not mean it works in the context. So to show that it is working in the context is still something left to do. You can just simply select the requirements you want to show. And if you just want to show you have test requirements and source code and code coverage on an abstract thing, then that's everything you deliver. But of course, making it run on the hardware integration, you have to show afterwards. And that's the trick of the safety element out of context, is something like a pre-certified thing or pre-qualified thing that you can then afterwards reuse easier. And of course, claiming an operating system would be finally certified is a big difference than saying it's a safety element out of context.
Yeah, read it more, please.
And customers need to read the safety manual, something they unfortunately often tend to forget.
I always say in our company, not everyone can read and write.
Yeah, that's actually something that in the third edition, I think will be even much more discussed, the safety manual, safety application note, and so on. Yes, it's something very important. Really read the small print, especially SOC.
Yeah, in fact, this is one of the initiatives that for the third edition to revisit basically the definition of the safety concept because there's a sort of confusion about what is a functional safety concept, technical safety concept, if I need to write it for a software element or not. So, and basically there's a proposal to include a safety manual.
So, okay, I mean, last question to leave to stop the panel. If you can comment, otherwise I can understand maybe it's not possible, but can we expect some open software in mass production anytime soon?
Hopefully.
I'm looking at Stefano.
I can only say I'm very positive about it.
Good.
Likewise.
Yeah, of course it is. Yeah, we all hope so. We should work together in this, and I think the good point of the open source is to really work with teams, with really other experts, and to cooperate to the same target. That is okay. Many thanks to the panelists, especially to Stefano for a week really up very early in the morning.
You're welcome. My
Thank you.
pleasure.
So, okay, so we have now coffee break, half an hour, and then let's start to let's target to start on time, so we can also finish on time or before the scheduled time. Thank you.
Are we live already? All right, I just wanted, before we will go to the next presenter that our dear chairman will announce separately, I just wanted to make a little announcement since we're already getting closer to the end and remind you once again about the evaluation form. Please fill it in. And now it's the time when, if you missed someone, forgot about someone, to take a few minutes and add your opinion about that or another part. And also a little note for those who joined us, but as an audience and not as a speakers, do not hesitate to visit our website once again. And there you can find the form that you can fill in if you wish to join us as a speaker the next year. And with that, the floor is yours.
Okay, yes, the last part of the conference. All happy, all sad, no cry. So the next presenter will be again virtual. Yes, Andres, are you there? You're muted. Okay, can you say something? Andres? Okay, still we have to fix some issues here, but okay, we have Andres Barillado, is a functional safety assessor at NXP. And the presentation will be about digital twins for functional safety. That is something we have not really touched till now, so new topic. Andres?
Hi, Ricardo, can you hear me now?
Yeah, perfect.
Good. Can you see
I can
me?
hear, can you see you? I can see you, yes.
Perfect.
Can you try to share your presentation?
In a second. And here we go.
Excellent, yes.
Perfect.
Okay, the floor is yours. Thank you.
Thank you so much. Hi, everybody. So my name is Andres. I work in the functional safety office in the central functional safety office in NXP. As Ricardo said, I'm a functional safety assessor by day, and by night I scratch my head about what's coming next, so innovation and next chapters for the company in functional safety. And I'd like to spend the next few minutes sharing with you our short, but I hope that is interesting experience with digital twins, and of course how it intersects with functional safety. One of the nice things about being towards the end of the conference is that I get to see if my topic was completely crazy or not. So it turns out that a lot of the things that I'm going to talk about have already been mentioned, which I see as a positive thing. So think about this presentation more of as an application case, what has already been discussed, and anything else. So let me get started with the actual thing. So starting point is software-defined vehicles. This is the beginning of the conference. We are experiencing one of the largest shifts in the automotive industry. We're moving from the regular vehicles that we all know into SDVs. This is being driven, of course, by software. And even in the past decade or so, we've seen a huge proliferation of ECUs in our vehicles. We made a promise to the public. We said that we would be safer, zero accidents on the road, we would become electric, we would become energy efficient. And now it's time to deliver on those promises. How do we do that? SDVs. So I think that we can all agree that the picture on the left is ugly and the picture on the right is beautiful. So that's the promise, right? We want to move from what we have right now, hundreds of ECUs that are each representing a function that has static architectures, and they have increased complexity. Star complexity here means physical complexity. And we want to move to this nice picture on the right where everything is flat. There's only a few wires. The functions can be executed anywhere in the vehicle. We can do updates over the air. We have a nice connection to the cloud, and that's also relevant for the next slides. So having software in the center of the picture brings engineering efficiencies and new value creation. So this is the reason why we want to go there. For example, it could mean that we're simplifying electronics architecture and reducing system level BOM, centralizing software development and optimizing development methods to improve costs. We're managing vehicle energy to make cars more efficient, or increasing range in the case of electrical vehicles, or have easy methods to upgrade software. So no more do we need to worry about hundreds of different ECUs with different methods and so on. Finally, it can free R&D resources to focus on innovation. Yay! So at the same time, these are costs. These are sexy. Same time, automakers are trying to determine how to create additional value, more money. How is data generated from the vehicle? How is it going to be transformed into revenue streams? Can we sell new features to the cars that we have already sold? And perhaps more relevant for us, can we predict faults and fix them before our vehicles fail? So not a lot of functional safety, except maybe for the last point. What I gotta say though is that this is the right setup for digital twins. What is a digital twin anyway? So we have a strong definition. We have a digital twin being composed of three main elements. First, we have a physical entity, which lives in a physical space. And this, of course, is the vehicle or any item or subsystem in it. We have as a second element, the digital entity, which lives in a virtual space. It's also sometimes called a model simply, but the right technical term is a digital entity. And the third item there is a connection between them. Additionally, from this, in order to consider something a digital twin, we assume that the physical and digital entities are exchanging information in pseudo real time, meaning that there is a closed loop relationship between both. If this relationship doesn't exist, then we don't consider it as a digital twin. We consider a model of what's going on. So this means there's interaction between the physical entity and digital entity. So that's a definition. Some examples of how we use these might actually be helpful. On the top side of the slide, you'll see that we have what brings added value to the physical entity. So it could be as trivial as transferability. For example, being able to configure your seat according to your measurements without worrying about anything else, or improved performance. And performance here might be about the vehicle, but not necessarily. You can see the examples there. It could be something like an Ethernet controller deciding where to send traffic depending on the load, or even battery management state of charge with a predictive function. Perhaps more relevant for us is the second side of the slide, where we talk about things that are touching functional safety. So better reliability, silicon prognostics and predictive maintenance will be made possible because of digital twins. And real-time failure prediction may require perhaps better sensors. This might lead to, for example, creating virtual sensors with these digital twins and making ECUs more manageable. Okay, so this slide is here to show a bit of a roadmap on what the vehicle needs to look like in order to enable this technology. All the way on the left, we have what we've seen in the past, legacy domain-based architectures. All the way to the right, we have what we call SDV optimized, where we have a central compute with a high performance, and then we have the zonal controllers, really worrying about what is near it and not necessarily the function. You know this, it's a normal pathway. This is the obligatory slide on the standard landscape. You'll see on the right are functional safety standards and SOTIF. All the way to the left, we have not safety, but standards on digital twins. You can see that there's already a few of them. There's more coming up. So this is not something that I came up with out of the blue. It's something that is transforming industries all over the place. And we believe it will hit automotive as well. And in the center, you'll see that I've mentioned ISO PAS 8800 and ISO TR 5469. The reason for this is that digital twins, so the digital entity, could be likely implemented as an AI, as a machine learning model. Not necessarily, though. So, okay, so we have a landscape. By the way, the standards on the left have nothing to do with safety. These are just describing what a digital twin looks like and how it should behave. So we're missing this intersection between the left and the right. So now that I've introduced the concept, I want to share with you the three main challenges that we've been looking at for the past few months. This is something that we've been looking inside the company for a little bit. And yeah, this is our train of thought that I want to share. So first, on the life cycle. The slide here represents a colorful representation of ISO 30173. Excuse me. So ISO 30173, I'm sure everybody's familiar with it now, since we barely talked about standards in this conference. This is the one on digital twins as a baseline. So on the top, you'll see a flow for the digital entity, on the bottom for the physical entity. And it's not very hard to see. On the bottom, we see this linear flow. It can be easily folded into a V. V as in V cycle, we are very happy with that. The digital entity doesn't look like that. It looks more like DevOps. What do we do? So we took a first stab on trying to align these using ISO 262, which is this slide here. So we have them side to side. The picture on the left now is the one coming from the standard and no longer the colorful one, but it's still the same message. And so if I click through my slide, you'll see that we've been able to map more or less certain parts of ISO, focusing on the digital entity because the physical entity we know already. And it's all nice until we reach part 7, in which, yes, it's possible to do a mapping, but then we have this pesky iteration arrow on the left. So what do we do with this? So it seems like the first system release, when we do the first flow, it's just a simple development, a known development. However, after it release, the lifecycle circles back and we go back to this design and develop phase, which means we start with part 4, if not part 3. And then we must do the continuous integration tests. So the end result is that we have an evolving safety case over time, and we also might need independent assessments. What do we do? So this is challenge number 1. Maybe the 3rd edition might have some clues on how to handle this, but as of now, there's no, as per our understanding, there's no functional safety standard that takes care of this kind of problem. So that's challenge number 1. Challenge number 2. you saw that we had a nice connection to the cloud in the previous slide. So let's assume that our digital entity is indeed in the cloud. Now that means that that's the picture on the right, by the way. The blue has the edge device or the vehicle. Then on the green side, you see the digital twin running on the cloud. What we see now is that we need to add functional safety requirements to this digital twin that is running on the cloud. We can make it easy and say, okay, maybe we just need communication to make sure that the communication is okay. So data integrity and all that good stuff. But maybe we have a problem with security affecting the way that our device is actuated, our system is actuated. So security is a concern. We said, okay, let's make it easy. Let's move the digital twin to the edge. But now we have, on top of everything else, we have to make sure that our edge digital twin is resilient to hardware failures as a regular development, plus likely SOTIF. It was probably also relevant to the previous one, but let's make it simple. And what we discovered is that in order to run a valuable digital twin, we might still need a connection to the cloud. So security is still a concern. So that didn't go away. So we have a proposal which is not very revolutionary, but I still want to share. And that is a statement that we say we need a digital twin observer and safety management unit. That's the box in the center here in blue. In the top two boxes, what you see is the digital entity and physical entity. And what you'll see is that there's no direct actuation of the system without going by this middle box here, the observer and safety management unit. The proposal, the reason I'm saying this is not very revolutionary is that this is similar to what we find in ISO TR 5469 for machine learning, which was discussed previously today. But yeah, anyways, what we say is we need an independent element that is observing and looking at what the digital twin as a whole is doing. So challenge number 2 then on architecture and extending things to the cloud potentially. And then for our third challenge, you need to walk with me on this thought experiment, which is describing the slide. I'm going to walk through it. So we mentioned at the beginning that digital twins live in their own virtual space. Now we can imagine that we have a lot of digital twins or digital entities living in these virtual spaces, and they're exchanging information, which means that the virtual space is now extended to multiple digital twins, which is a good thing because that means we have exchange of information. So we have an enriched and virtual environment. We are living in meta, in the metaverse here. But then that means that if we have somebody failing there, we are corrupting data beyond just a vehicle. It's going into different vehicles. So earlier today, there was a mention of ASIL E. I think this is a situation, it's not necessarily the severity, but it's not the controllability, it's more the severity that is being extended. And then what about security? Same thing. Now that we have this virtual thing, attacks might have a severe safety impact. So conclusion is that we need a holistic safety and security architecture. That's definitely a requirement moving forward with digital twins. It's not all negative, so we have some hints on how to treat these shared virtual spaces. One is just assume that corrupt shared virtual spaces are okay and treat them as noise, expect them in the systems, and just live with it. Another thing that needs to be considered is how these virtual spaces are being created. So option 1 is there's a centralized shared virtual space, which is equivalent to have a server somewhere hosting this virtual space. And the second one is having ad hoc shared virtual spaces in which each digital entity is taking data in from everybody else and recreating its own virtual space and then sharing that with the others, and it's being voted. So these are options that need to be explored. We have not looked deep into these proposals, but I think that's something that the industry needs to go explore, see where we need to end. Okay, so I need to conclude. So as I said, I'm touching upon very quickly upon many of the topics that we mentioned today. SDV is a starting point, extending the life cycle for, in this case, digital twins beyond the release of the product. Extension of the item boundary so that it includes potentially other elements, and the shared virtual spaces beyond one item, and definitely safety and security as a solution to this. Thank you very much. I'm open for any questions that you guys might have.
Okay, many thanks. Any questions? Okay, Oscar.
So I still have energy for questions, but I need to leave after this talk. Yeah, my question is, do you know the, and I missed it in your list of the standards, it's EU law from 2022, and it has the number 1426. So
1420, no, I'm not aware of that, no.
1426, it's about ADAS type approvals. So if you want to do a ADAS type approval based on the digital twin, then you have to qualify the simulator and qualify all the simulated models, which is scaring to the community.
That you mentioned that earlier. Thank you.
Yeah, Halloween, so we can be scared. More questions?
Sorry, I forgot to say, of course, we can help with that at Validas. So my name is Oscar Sotos from Validas. Feel free to contact me.
Thank you, Oscar.
Okay.
Hello, Juan Pimentel from Omnex. Yeah, my question is about this digital twin observer and these shared virtual spaces.
Yeah.
In what form is NXP making this available to customers? Is it on the cloud? Is it software and hardware combined? Can you explain all of that?
Yeah, so we don't have a commercial product for this. We are at the early exploration phases of digital twins. One of the things that we do well is edge. We don't do cloud so far. So one of the reasons we wanted to go explore this was to understand how much of it can be implemented on the edge, so in the vehicle itself. So long story short, we don't offer anything right now. We're more sharing the concept to see what the community thinks. And from there, we can talk about where we want to go.
Okay, maybe Anders, can you elaborate a bit more about digital twins, machine learning, and open software?
Sure. So what we see is that when we start looking for examples for digital twins that exist today and that are safety related, what we end up with is mostly implementations in machine learning. We have, for example, looked at state of charge for battery management. And there are some traditional aspects on how to do this. So traditional meaning algorithmic. But it seems like machine learning is very precise for determining an accurate state of charge, which leads us to the problem of, okay, now we have to look at ISO 8800, and the only way that these things are trained are using open source. So what do we do? So earlier, that was actually my question. What do we do when we have both? Seems like it's separate problems. I agree with the response, by the way. But as of now, if we want to use a traditional safety case to prove that we're safe, so traditional meaning what we've done in the industry so far, it's not good enough. We cannot really say this is safe because we followed because we have open source and we've qualified. So yeah, we're in the investigation of trying to figure out how to do this as well.
Thank you. Yes. More questions? We are all tired already at this time. So coming to digital twins, I mean, how much really companies like NXP, Renesas can really provide value, and what can we really do when we go to digital twins?
What we see is that if we think of silicon by itself, the answer would be nothing. But what we see is that OEMs might need some help enabling these models through our silicon. So we want to provide the correct enablement for their functional safety use cases with digital twins. I'm sure it's the same with you, Ricardo and Renesas.
Sure.
Yeah.
Yeah, I think, of course, it's the trend, especially moving to shorter development cycles. What we discussed also before during yesterday and today, we need to develop software before the hardware is available as well. So
Correct.
these kind of digital twins are really important. The question is how much can you rely on the digital twins and so on, and then really how much you can really speed up. But that is our job.
Yeah, I can say I can extend by just mentioning I didn't go too much into it. Predictive maintenance as a major use case, and
will be the next presentation.
Yeah, so maybe I should stop talking then.
Yeah. Andrea is really under stress because it's the last presentation of the. I think we jumped straight to questions. Okay, any questions online or all quiet? So okay, so I will say let's close here your session, Andres. Thank you very much for joining and
thank you
contributing. Thank you. Okay, shall we do it the next? We go straight to questions now.
Yes, come on, guys. Questions. Wake up.
Now you are all expert. Okay, well, the next presenter is Andrea Mattiucci. I think you know him already since yesterday and today. Senior Product Manager, Protean Techs. And the topic I was also contribute to this is the predictive maintenance in the context of functional safety, the white paper that we created in IEEE. Please.
So, guys, come on, 20 minutes. So the presentation actually is not from Protean Techs. I'm not going to present the company. It's so I had the fortune to lead this small working group that worked on this topic. So predictive maintenance. So Functional Safety Standard Committee is the newborn committee under IEEE, the Computer Society, and so you have also met Joytika from the same society. Well, so. Okay. Actually, the presentation before introduced already the motivation about so why predictive maintenance is important. So our colleague of NXP presented actually that this connectivity introduced the opportunity also for new value streams, new business opportunities. So this is one of the many new business new opportunities. Well, on this regard, our goal was to investigate the prognosis. So if diagnosis is let's say the basis for functional safety, now what about the ability to predict if something is going to happen? So this is in a nutshell, let's say, what is predictive maintenance. So you have the ability to estimate what is the time to failure or remaining useful life. So how much time ahead you have before something occurs, something in this case, an error, a fault that will lead to a failure. Therefore, in the context of functional safety, you want to avoid the incoming, the occurrence of an hazard. Now, the presentation is just 4 points. So the scope of the white paper, the link, we will go through what today is described in the functional safety standards. We will refer to a very important technical report that has been prepared at the same time, been published at the same time by ISO. And last, the conclusion, okay, of our discussions. Oh, okay, good. So this is the this is the exact title, and there is also the hyperlink. It's free for download. Well, so please enjoy, use it. You got you got the motivation behind. So let's jump directly to one part of our analysis. So what we have today in the 26262, the second edition? Ooh, there is a typo. It's not 2028, but of course is 18. So if you look for predictive maintenance, actually there is no much mention of this concept, of these methodologies, but yet there are two important things: fault forecasting and how this fault forecasting is used, in which context. So there is a very nice definition. So we can see the ability to detect a fault or a degradation before it led to a failure. Exactly what predictive maintenance is. So it's mentioned as part of chapter 10, part 10, sorry, and here is, this is the second key word, safety-related availability requirement. Availability is something that we have discussed also today. Very importantly, now for especially for autonomous driving, for these systems, is not only about correctness. So 2 + 2 = 3. No, you do not only want to avoid such computational errors, but you want also to have the system available. This is more and more a concept that is pushed, especially by the OEMs. So you may be tolerant against errors if the system is still available. Just think about, for example, image processing. What if 1 bit of your 10 megapixel image is wrong? You are very, very robust against such kind of errors, actually. But the point is, if you miss some frames, so if the camera is not available, this is indeed very, very critical, because then in that missing frames, maybe there is an object that is crossing the road. So the availability of the system is much more important in some context, okay? Not a golden rule, of course. I'm just saying why availability is becoming very important. So, and at least today's standard give us a very nice, very important context where to place predictive maintenance. So the ability to forecast and these safety-related availability requirements, or RAS. The technical report 9839 from ISO is the same working group that that created the proposal for the third edition. So third edition will come. Now they are debating, they are discussing. What is expected is that this technical report is going to be one of the new part of the third edition. The report is long, but for me today it's very important to discuss the introduction of this new concept. The grading fault, okay? The grading fault. Okay, what does it mean a fault? Fault is the abnormal behavior of the system that will lead to a failure, and the failure leads to an hazard. Okay, so they are playing with the definition in this case, right? So what they are saying is that something is degrading abnormally, and it will cause an error. So there is the cause relationship, cause-effect relationship, but the point is in time, when is going to happen? So they are saying if the nominal behavior, the expected behavior, the normal degradation of the system is so that, you know, this is the reliability point, right? The performances of the system are going below what is the minimum acceptable level after the useful life. Okay, everything is fine. So we validate the reliability of a system, typically exactly keeping this in mind, right? So for a silicon device, HTOL, whatever, we do that so that, let's say, nominally, in average, all the devices are expected to live 30 years. the expected life of the car is 10, okay, there is enough guard band to say that the reliability is not going to cause, the degradation of the performance is not going to cause any fault. But the point is now here we are talking about the ability to monitor these performances. This Y can be anything. And if it's deviating from the expected behavior to intercept, or at least to predict by when the performances are not going to be enough. I mean, the example I think is quite simple, right? Think about anything that is a kind of a hardware, right? I don't know, anything that is subjected to friction. So sooner or later, it will, let's say, structurally not be strong enough. A rope, you're climbing a wall and the rope is getting consumed. Sooner or later, the rope is going to break. Now, the point here is that we are measuring how strong is your rope, your device, when you are using it. And the time to failure is nothing else than estimate this time distance from the measurable degradation till when the degradation is not enough. It seems trivial, but I assure you that actually this is highly debated still today, this concept. And this is one of the possible interpretation of this degrading fault, how is connected with the existing definition of intermittent fault and systematic faults. So this is, by the way, the working group preferred interpretation. Is not the only one, but is our preferred one. So here we have a KPI, whatever it is, we are measuring. So is deviating from the expected behavior. This is just a simplification of the picture before. And now here we are getting closer and closer to this critical threshold. We are saying that before this distance is getting smaller, now the probability that something random occurs, it's getting higher. Because again, random faults is so shit happens. And the permanent fault is when you do not want to be in the room. So, but before you may have some intermittent behavior. Think about too high temperature or an increase of the workload, if we're talking about typical MCU. And then you may have some intermittent faults, something that may become more and more frequent because degradation till it becomes permanent. Okay? So, 9 minutes, guys, 9 minutes. Now the proposals, the proposal of the working group. Four proposals. They start quite simple and then they become more complex, but each of them is, let's say, on top of the other, okay? So first one is specific metrics for remaining useful life predictive techniques. So we are saying, let's use some metrics, define some targets for this technique so that we can associate what is the required integrity level for each safety-related availability requirement. Very complex sentence, but the point is we are just saying for each integrity level, let's define a minimum target that you need to achieve, okay? And second message here is let's define some metrics, some KPIs. Second point is if we agree that is as a useful technique, a good methodology, this predictive maintenance, okay, let's acknowledge that it can be used for the degrading faults. So the consequences are not trivial. So if we can apply predictive maintenance as a safety mechanism, then when we, as a safety manager, we do the FMEDA, then we can use this technique, this methodology to reduce the base failure rate for the associated failure modes. So ultimately here we are suggesting if it's a safety mechanism, then it can be used as any other safety mechanism, simply. So now we are suggesting that it should be acknowledged that for the degrading faults, so for any failure mode associated with actual hardware degradation or aging, we can use, if it's possible to measure the degradation, we can use a safety mechanism like predictive maintenance. I will anticipate a question because you're tired. The point is that we are talking about a statistical methodology rather than a systematic safety mechanism. What I'm saying, a safety mechanism typically is you check something and beside false positives, false negatives, what do you say? You detect an error and typically is after the fault, right? So it's like you have certainty that you have detected an error. You may have a false positive, false negative, but the point is that there is determinism in the mechanism itself. Think about the ECC. If you do not have any error in your algorithm, you will detect error bits, right? In this case, we are instead saying we are going to predict something. There is a statistical error in this prediction, anyhow. And now we are saying we should consider metrics for this statistical approach. Any prediction is going to have an implicit statistical error. In concrete, we will see that later, but think about, if I'm going to tell you that your car is going to fail in 6 months, what are you going to do? Are you going to continue to drive? You run to the workshop? What do you do? Let's go through the proposal and keep in mind this thing. So third point is the recommended definition of the concept of failure mode coverage. Okay, for predictive maintenance. Again, what is the efficiency of this methodology? So failure mode coverage is nothing else than the ability, how you are confident that you have detected a fault, right? An injected fault, for example. Here in this case, we are suggesting to use, once again, one of these statistical parameters and specifically the confidence interval, okay? So I will go to the last point, that is what I was saying before, keep in mind the question. In the TR, there is a very important question that is, is remaining useful life sufficient? Resonates very well with the question that we have seen before, right? Is it safe? Is it safe enough? Right? This is exactly the same. Is the time to failure, is this prediction enough, sufficient? The TR doesn't provide an answer. It's just saying, as you can see here in this very schematic diagram, you start, something is observable, you continue to collect data, you make your first estimation, you assess the rule, is enough or not enough? If it's not enough, you go to safe state. But the question is, how is enough? Again, the question that I was saying before, 6 months are enough or not if you're driving a car? Or make it simple. You're driving a car and your tank fuel indicator is saying you have still 100 kilometers. What do? You have 50 kilometers. You run to the petrol station. You have 20, 10, 5. The point is, what is the error of your prediction? Because if I'm going to tell you, you have 6 months, plus minus 6 months. So is how big is your error? And how much you are confident, the confidence interval of your prediction. So it's not the number itself, it's not the prediction itself, but everything is related to how good is your prediction. And this leads to the last one. Okay, complicated picture, but I'm nothing else than tell you exactly that. Walk through with me. TP1 is the first time when you do an assessment, And the prediction horizon is nothing else than the time to failure, the distance, the time distance from the fault, okay, the error. First time is 6 months, plus minus 1 month. Is enough? Yes. Is order of magnitude bigger? Sorry, I said 1 month. I wanted to say 1 week. Okay, it doesn't matter. But you got the gist. The second one is indeed you are getting closer. And we are saying that if your PI is nothing else than the prediction error interval, if your prediction itself is similar, in the same order of magnitude of the error, then you are in an uncertain situation. So the remaining useful life, it may not be sufficient. And of course, if the remaining useful life is smaller than your error, well, in that case, really, yeah, you're lucky that there is no fault in the system. So I think that is a nice conclusion of the working group discussions, that we linked the intrinsic nature of predicting maintenance, the statistical approach, and as any statistical approach, the key point for me is how confident you are, what is the error, what is the confidence interval. So the key performance parameters of this technique with the possible metrics of the functional safety concept. So how to use this in context. Okay, this is my last slide, and I have 40 seconds.
Very nice presentation. So can we use open software also? Open source software? Yes?
No.
Questions? One question at the end. Oh, too many questions. We have to leave.
Thank you, Andrea. Mohammed again. Andrea, have you looked at IEC 61508? Because when they do the probability of failure on demand calculation, they look at quite a lot of what you've described in here, including mean time to repair, the test interval, and the diagnostic coverage, and the fault and the failure rate that we look at. And then they calculate, and based on IEC 61508, you come up with a maintenance schedule that allows you basically exactly predictive maintenance that allows you to maintain the SIL level, because every time you calculate SIL, it's a snapshot in time based on the time when you did the assessment.
Yeah.
So you do that, and it's well documented since 20 years. Have you looked at that in what you're describing here? Because that will be very relevant to compare and contrast and see where are the similarities.
Not that I recall this particular standard, so I think that I will be in touch with you later. One of the standards that we have discussed is the IEEE 1856, that is a very lean and new standard that describes prognostic and health monitoring. And again, I think that the key word is monitoring. So as we've discussed before in many different panels and presentation, one of the key things is that right now there is new techniques, new solution, and data are becoming cheaper, let's say. So prognostic is not new, as you mentioned. I definitely expect that there are already existing standards. The point is that so far, think about it, in cars, to put a sensor, just one sensor, it's a lot of money, typically, right? I mean, in the exhaust pipe, I worked intensively in the diagnostic for exhaust after treatment. Just putting a sensor that may cost $20 ultimately for the end customer, I will not disclose how much it costs. So the point is that now indeed we are the data and the sensor and the ability to also, as we have seen with the digital twin, to remotely analyze this data, it becomes more convenient. And so this make possible something that it before maybe was too cost prohibitive, let's say. But the key message, once again, is also in the mentality, right? We discussed that, for example, regarding cybersecurity, shifting from the ability, so the mindset of detecting something that typically is also after the event. Think about software library test or LBIST in Silicon. They typically detect stacked faults, but this means that in the time between the two tests, the fault is in the system and you are not seeing it because you are not testing it. Here, indeed, the idea is you monitor the system in normal operation, in normal behavior, and then you predict something, right? So you anticipate, and well, prognostic is like in medicine, is much better than cure, right?
Fault prevention. Fault prevention. It's not fault reaction. We're not mitigating. We're preventing faults by doing preventive maintenance. It's the key word. You know, in functional safety and in safety in general, you don't want to deal with the consequences. You don't want to get to the failure event, because usually that is where the consequences come, and you start to reduce airbags and fire ambulance. If you work the way you are prescribing, it's shifting the mindset to fault prevention rather than fault mitigation.
If you want, is a kind of, you put a mechanism to systematically prevent something, right? But we're mixing kind of words, right? Typically, you do systematic analysis before, and then you do detection of random faults after production, right? After design freeze. Here, indeed, we are kind of putting something that systematically could do prevent a fault, but in the field, right?
So Marzana Khatun from Bosch, I have one simple question, maybe because from my previous experience, not from Bosch. So the example that you have used mainly looks to me, you talk about performance and so on towards SOTIF. So do you think that it has also any impact in the functional safety? Specifically, the reason I'm asking, when you talk about availability and degradation concept, it depends on application, in my opinion. What's your, because all the example is only with the sensors and stuff that focus to me on the SOTIF. So do you think functional safety has no impact?
No, the contrary. In this case, performance is intended to be very generic word. You could even call it health or whatever is the KPI that you are measuring. So if it reflects the status of the degradation of the system, is an interesting KPI that you can monitor. So for a mechanical system, it can be anything. The stiffness of a rod, the thickness of a disc, the frequency, the noise frequency of a ball bearing, anything. In silicon, it could be a change in the impedance, in the noise on some power lanes, anything. Performance in this case is generic. Whatever you want and is suitable for your system that defines the status of the system
Based on use case, you make
is performance. Yeah, you can call it health.
Okay.
In the standard I was mentioning before, they call it health, typically health indicators or condition indicators.
How you relate this with the reliability?
Yes, this is the point, right? It linked very well. So now we didn't explore this in the working group, but what I can foresee is also what has been discussed in another presentation here, right? So by our colleagues from Iveco. If you have the ability to predict a fault, then you can calculate your base failure rate. And with this estimated base failure rate, you can validate your assumed base failure rate. So in their approach, they were looking for DFT signals and such kind of information. So this means that they were looking for the result of diagnostics. Again, a safety mechanism detects something, they analyze it, is a fault, okay, is a fault, then increases the counts of failures and so on. Now here, we give you even one tool more. You do not wait for faults to happen. If you have the time to failure, you can predict if this fault is going to happen during the useful life. So if it counts for your base failure rate.
Thanks.
So thank you, Alexander Mattausch. I also have a question to your prediction and the graphs you had. So the degradation you model there is, the graphs at least, it's a linear degradation. And for the time, where you say this time horizon, this is a Gaussian distribution that you have here. And actually, to be frank, I would like to question that this is a linear. Can you replace this with other distribution functions, or how is this intended to happen?
Yes, in the sense that it was just to illustrate a point. The Gaussian distribution, the normal distribution of the faults is just an example. Typically, actually, they show also a binormal distribution for that. I mean, it's just an example. It's just an example, yes. So I think that most of the time we will find out that a normal distribution is a reasonable assumption. Sometimes not. It depends on the system. It depends on the failure mode. It depends on the degradation. But the point is that, again, we are talking about intrinsic degradation or aging or wear out effects. So a breakdown, by nature, is not typically predictable. So, for example, just to come back to the silicon, purely random events like soft errors, right? These, of course, are unpredictable by nature. We're talking about gamma rays that are hitting the right transistor in the right moment. That is not something that you can predict. It's not related to the intrinsic degradation, but other things, yes, they are feasible.
But also for the degradation, we want to predict it. So this really depends on the prediction function. So if you don't have the correct prediction function, it's basically random what you get.
Yeah, it depends on the nature, the physics behind the phenomena. Because there are phenomena that are predictable.
Okay, I would like to go to the, I think it is a question online, no?
Yeah,
And
there
then
is
we have
one
to close.
online question from Bjorn. Is there an estimate how many monitoring points, KPIs, are necessary to cover degrading faults in a multi-million gate design? How to identify faults which are considered critical for degrading?
Okay, I guess that the question is about silicon. In this case, it depends really on your approach. You may have a data-driven approach, you may have a physical model approach. So I think that, I mean, it was just very, let's say, not in the scope of our work to review existing techniques or propose anything specific. So if Bjorn is interested, he can contact me and we may talk about silicon solution, but this is not, let's say, the scope of the IEEE white paper.
Thank you. He can also see your email on the presentation. So
Yes.
yeah, thank you.
Yeah, I mean, his company is also doing this. Or you can ask ChatGPT, maybe you get an answer.
Of course, of course.
Okay, many thanks to be also the last presenter. Okay, so we made it to the end of the second day. Yeah, yeah. So I don't plan to now extend by half an hour or keeping here in the room. I think you are really tired and you are tired also of my voice. Hopefully you enjoyed this conference last day and today. You can bring something back home and accept a few kilos more because the food was really great. So I think the discussions were very nice and it was a cozy, really environment with a small group. I mean, I know we also had the guys online, and unfortunately we cannot really interact as needed with those guys. But really, the interaction here was really good. The panel, so I really wanted to thank all the panelists for open discussions and accepting some also tricky questions from my side, but I think that is the nice of being here in this kind of conferences. I think we touch many topics. You can see that we have a jungle of standards. We have the concept of CARAT is changing completely, moving to open software, moving to predictive maintenance. Techniques that we had to do already before, like safety case, that are still in big discussions, how we should really do proper safety cases. So really, we still have a lot of challenges, and the best way is to keep discussion and keep improving and think about safety, not about compliance. That is also the key. So I really hope to see you next time. Hopefully I will be also here. And again, thanks a lot for coming.